Good morning, JuliaCon. Welcome to this Friday morning's keynote from our sponsors, Boeing and Julia Hub. To kick off, we have Gary Mansouri, who is the Technical Fellow and Chief Architect of Systems Model-Based Engineering and a Boeing designated expert and advisor on model-based systems. Gary will talk about breaking the non-recurring cost curve using model-based methodologies. With Gary today is Viral Shah and Chris Rakokas. Viral is the CEO and co-founder of Julia Hub and one of the creators of Julia. And Chris is the VP of Modeling and Simulation at Julia Hub and the differential equations guru across all of Julia Lang. So thank you all for being here. Gary, I hand it over to you.
Can you hear me? Yes, I can hear myself. Well, good morning, everyone. Thank you for spending your time this week. It's been an amazing experience for me looking at the passion and the size of people that have come here because they want to be here. And that's been genuinely inspiring for me. So it's made the heat kind of not be as important anymore. So once again, welcome and good morning to you all. I wanted to make this a little bit more interactive to give you an insight as to why breaking the non-recurring cost curve matters and what does it really mean to break a cost curve. So let's start with something simple. Can you raise a hand if you know what was the average price of jet fuel in 1996, 30 years ago? Just a guess. And we can make it a little bit easier. So if you have any Americans here, we can do it in gallons or we can do it in liters. But so just a guess. No, much lower. So that's a good guess, though. So in 1996, the average price of jet fuel was about 78, 76 cents a gallon. And any guesses what it costs today in 2026, like in August? What is the average price for? No, those are good numbers. So it's actually $3.78. So average. I'm sure some places are $5, right? But the average is $3.70. So that's roughly about 4 times higher. Now, in 1996, I bought a ticket from Sweden to Colorado, and I paid $1,200 for it. And last month, I bought a ticket from Seattle to Sweden, and I paid $1,200 for it. So as passengers, we want to pay cheaper for flights. Flights are expensive. It doesn't mean that they haven't gone up. In fact, they have gone up. But if you look at inflation over the last 30 years, not 3 years, 30 years, we're talking about, I think my microphone, no, it's still working, thanks. If you think about inflation over 30 years and the price of the ticket I just mentioned being about the same, while fuel has gone up by 4x. And pilots, I'm sure, make a lot more money now than they did 30 years ago. Flight attendants make a lot more money. Staff, runway people, the flight deck crew, you just compound everything together. Everything is a lot more expensive. And in the meantime, the airplanes are also more expensive. So they're not 4 times more expensive, but they are about twice as more expensive, which says a lot. To have to pay twice as more money for an airplane 30 years later, that's actually very impressive. And so what does it mean then to break a non-recurring cost curve? We, collectively in this room, we are customers. We want to fly cheaply. We don't want to pay a lot of money to fly. Right now, flying is no longer a luxury thing to do. I mean, it is for parts of the world, but for the most part, it's not a luxury thing to do. It's part of travel, and especially with economy flights. And so the demand in the market is that, hey, I want to fly and I don't want to pay a lot of money. And so that is really the business model for the modern commercial aviation. So what does it do to companies that design and build airplanes like Boeing? Well, we have to be competitive. We have to make airplanes cheaper, but they have to also be safer. And safety adds complexity and cost. So it becomes essential to find a way to do things differently, more smartly, to actually make the design, make the production, make the non-recurring, meaning the development cost, more cost effective so that airline customers and passengers can benefit from that and have cheaper flight tickets. And so this is a topic we're going to talk about today. So how to break that non-recurring cost or non-recurring development cost. And so now you know why. And I think a lot of you are surprised to learn that 30 years ago, the tickets cost about the same as they do today. And yet we complain if we have to pay, I don't know, 10 euros for a beer or 20 euros for luggage to be up there, because why shouldn't it be free, right? But if you think about everything we just talked about over the 30 years and inflation, it is actually very inexpensive, relatively speaking, to do that. And so next time somebody's on an airplane and they want you to pay 8 euros for some snacks, you understand that, well, in the greater scheme of things, it's actually very, very cheap. So now I want to shift it to the development cost and how model-based engineering can revolutionize that, and then ultimately why we're talking about it today and how does it tie in with Julia Hub technologies, in particular diode. I'm going to focus on diode as the main child here. So let's go back to the Wright brothers. This is going to be like a quiz. Unfortunately, I don't have any prizes with me today, but I'll be happy to take your name and maybe we can do something later. So hopefully everybody here knows who the Wright brothers were. And on December 15th, 1903, they sent a telegram to their father. And the telegram, it had a few short sentences, but it had 2 key words in there as a message that they sent to their father. So again, December 15th, 1903. This was 2 days before the first flight, before the actual flight that changed history. So can anybody tell me what those 2 words were that they sent to their father? Without checking, without going online. That would be really a good telegram, but no, they actually had already spent their money. They were ready. So, all right, let's give it one more chance. So these are 2 sons who sent a telegram to their father, and then they said 2 words followed by "keep quiet." So, can anybody tell me or guess what they told their father? Those 2 words plus "keep quiet." All right, so I still like to have a conversation about this with somebody afterwards, regardless of the right answer. So they said "success assured." So the telegram was "success assured, keep quiet." Now they sent that to their father before they actually had the successful flight. And so why were they so confident that they would have a successful flight? So they initially invented the predecessor of model-based engineering. Instead of designing, building, then testing, and finding out that there were problems, which was the norm back then. And back then, in the US, we had the so-called War Department who was funding to build an airplane. And that was unsuccessful for 6 years. But then the Wright brothers, they thought differently. They said, well, we cannot just design, build, and test and find there are problems. It's too expensive. Before we actually build it, we have to have high confidence that it's going to work. So that's what they did. They tested smaller systems as concepts, as prototypes, and then once they had success assured, they would then go and integrate it. And so 2 nights before the actual flight that lasted 12 seconds, they sent that telegram to their father, "Success assured, keep quiet." So they were confident that they were going to have a successful flight before the flight actually happened. So that's really the predecessor to model-based engineering. So why does model-based engineering break the non-recurring cost curve, and why does it matter? We don't want to build an airplane, then find out that there are major issues and we have to ground the airplane and cancel flights and redesign things. And every now and then something catastrophic happens and something is learned. But generally speaking, we want to shift all of that design to the left. So from your view, we want to put that all to the left. What is left? Left means the early design stages, requirements development. We want to be able to have very high confidence that those requirements are so thorough, not more than they need to be and not less than they need to be, but just adequate, so that once we have a design that's going to be safe, that's going to be reliable, that's going to work without problems. And so when that is done right, then that also means that you have to spend a lot more focus upfront doing the right modeling. So now, talk about modeling. Laws of physics haven't really changed the last 30 years. So then is modeling a magical trick? No, it's not. And there were models before 30 years ago. Different tools, different methods, different analysis of formats. Laws of physics haven't changed. The tools have changed, and how we do design has changed. So what we model hasn't changed, how we model has changed. And how we use models in the design is really the revolution we're talking about. In other words, can we replace shall statements as requirements with actual dynamic models, so that instead of having engineers become authors in a given language, they actually create mathematical description of what they want to accomplish live in a model. So a tool like Diode that has a revolutionary capability of running different continuous or discrete time domains simultaneously, it opens up significant amount of opportunities to describe a more complex system as you want it to behave before you go and lock the design down, before you build it, so that you have those high confidence points in your decision. And in the industry for the last 20 years, the automotive actually has led this. The pioneers of model-based engineering are the automotive industry companies. And so on average, they have saved about 28% of their non-recurring development cost. That's a lot of money, roughly 1/3 of the total cost. And that's essentially an untapped business capability for the aerospace industry because of regulatory restrictions. And so that's a lot of money. If you think about a large airplane that costs many, many billions of dollars to develop, saving 1/3 of that is very dramatic. And those savings translate into lower prices of the airplane, which then lead to airlines being able to offer lower ticket prices. So we all want, what we are doing is part of that breaking the non-recurring cost curve. At the same time, something that's very important is that it's not just about breaking the cost, it's about this methodology will lead to significantly safer and effectively higher confidence in the operational capability of the airplanes than ever done before. So the first pass quality, rather, becomes a lot higher. And what that means is that you don't want to pass flaws and issues down the line to a flight test. You want to catch them before the design is done. And so that makes the test phase significantly shorter and more confidence inspiring. And so that's what the non-recurring cost is about, and that's what breaking it is about, and why. And so I am increasingly more enthusiastic about seeing tools like Diode that I'll get you in a second, that have really revolutionized how these technologies have changed, not what we model, but how we model. Again, people have modeled mathematical systems for decades, but how we do that today is really, really different, even compared to some of the more broadly accepted tools. So there was a question back there. I'm going to make sure that I give you a chance to ask you. So that's a very good question. And the truth is, yes. Yeah, so it was a long question for me to repeat verbatim, but basically, can you use model-based engineering to try different concepts and do optimization or sub-optimization? That was the essence of the question. And that is done, you're right, iteratively and very frequently with this capability, so that you can iterate tens of configurations, tens of optimization scenarios daily, and so you can fine-tune what you think you want before you know what you want. In other words, when you define a requirement, if you don't do model-based engineering, you just define the requirement and you think that's what you want and you go and build it. But with model-based engineering, you can test drive it. You can see, is this exactly what I wanted? And then you have aha moments. Like, oh, if I make this improvement here or this change, that's a better outcome. And sometimes it's a compromise. That means some other system has to be heavier or more expensive, and some other system gets to be lighter. So it's the integrated outcome that's the case. That's really the essence of this capability, is the overall airplane product or whatever system it is, the vehicle that wins. And one topic that I'll just touch on quickly, and then I'll hand it over to our Julia Hub friends, is so the primary expense in developing this complex system really comes to become certifiable or airborne flight software. And the methodology that we're talking about here is about, if you define your requirements as mathematical models, so that instead of having complex shell statements, you actually define mathematical equations as your requirements, they become parental requirements, then can become coded, auto-coded into flight software, so that you can generate millions of lines of code without actually writing them manually and without writing significant amount of text. You can write very high-level text about a functionality, then you build that functionality with mathematics in a tool like Dyad. And Dyad is working hard to breaking that barrier of becoming a flight software tool. But basically, then your mathematical description of that model becomes the parental requirement. It becomes an artifact, a certification artifact. That's mathematical model. And then that becomes the requirements trace of as a parent to the flight software. That is really the leading edge of technology, about converting thought into mathematical equations and let that become the parental requirements to flight software that flies the airplane, instead of having actually manually writing code. That doesn't mean there won't be any manual code. There will be things like very low-level detail code or embedded integration code that has to be, still for now, manually done, only because the equipment hasn't been standardized. And so you cannot have automated code for hardware that's not standardized. But the main bulk of the code, the flight software, that is mathematical, functional, behavioral, that can become automated. And so that's really where we are at that edge of technology. And so in the greater scheme of things, we're talking about creating millions of lines of code by click of a button, and just sit back and let the compilers do that and then create those functionalities. And it's deterministic, and they don't make, I mean, if there's a mistake in a model, yes, that mistake will propagate to the code. But if there's no mistake in a model, then the code is basically flawless, right? And so those are the actual low-hanging fruits of how we can break the non-recurring cost curve, so that the development becomes significantly better first-pass quality product, and so that tools like Dyad can essentially not only break that cost curve, but add more safety and higher quality. And I'd like to pass the ball over to Viral as a transition for the conversation with Dyad.
Thanks.
Thank you.
Thanks, Gary. Can you guys hear me? OK, that's working great. I will actually have to use the slides, so I'm going to jump up here. All right, so I have a few slides introducing Dyad. Many of you who've been here, been to the last JuliaCon, have probably seen some of the early demos of Dyad. It has come a very long way. So one of the first things I wanted to do is is share an amazing piece of news. Many of you might have already seen it on social media, one of our announcements, but we are excited that we raised a $65 million round of funding. This is really exciting in terms of bringing Dyad to the market, in safeguarding all the work we do on Julia, and in building sustainable and reliable business over the next several years. All right, so why Dyad, right? And everyone here has seen us talk about Julia. Julia solves the two-language problem, or sometimes even the n-language problem. Well, what's Dyad really, right? So Dyad, I like to say that Dyad solves the n-model problem. And what does this mean, right? So when you look at product design, when you look at sort of everything Gary just spoke about in terms of building a new aircraft, you find that vendors, folks at companies like Boeing or any industrial firm are using many, many different pieces of software as they go through different parts of the design cycle. And some of them are writing models in the form of code, some are using diagrams, some are using natural language increasingly with agentic tools. And often, you have to build a digital twin, you might have to build embedded software, you might have to build testing and validation. And all of these things are often done in different tools which operate in their own silos. And so the same model often gets built over and over again. And wouldn't it be nice if you just had one definition of your model for all the different parts of your design process? And that's what we refer to as solving the n-model problem. So if you look at the Dyad product, right? So by the way, Dyad is free to download and is free for academic and non-commercial use. Please feel free to go to juliahub.com and just download it. One of the key things about Dyad's design is that it has three ways to interact with your models. It has code, it has GUI, and it has an agent. And many of you have probably seen this at the Lunch and Learn or some of the various talks that our folks have given, so I won't dive too deep into it. But you can either use the agent to modify your model, or you can change it in the GUI, or you can change the code itself, and you get a single representation that is in sync across all these three different modalities. No divergence, no drifts, all right? Now, the really interesting thing about Dyad, which we think is going to be amazing and will differentiate it from all the tools that have come before us, right? So if you look at a tool like Simulink, for example, or a tool like Modelica, or a tool like AimSim, right? Like, what makes some of these tools successful versus others? And I think you'll get different perspectives from different people, but I feel that the integration that Simulink offers with MATLAB is an important part of Simulink's success. The fact that Simulink has embedded inside it the full MATLAB programming language, it really makes it powerful. And I think this is something that many of the other engineering modeling software are missing. Dyad, embeds Julia fully. In fact, Dyad goes one step further. It's fully built in Julia itself. And that allows us to really benefit from all the power of the Julia language and the Julia ecosystem. And so if you look at the Dyad stack, right, you have the open source foundation with Julia and SciML under the hood, and all the, the scientific ML, the scientific AI, and the generative AI capabilities that we bring in. You have all the agentic design models and all the, Dyad compiler tools, as well as the standard libraries and a bunch of domain-specific libraries. So we have hundreds and hundreds of components in the standard library, but if you wanted to do something very specific with HVAC or with battery design or automotive, we have all of that, and it's very easy to build these things with the Dyad agent. If you have any questions around Dyad's design or the architecture, find Chris or Mike Tiller after the talk. They're here all day, and they can tell you a lot more than I can. But the real powerful thing comes after you build the model, right? Because what are you building a model for? You want to do something with the model, right? And that's the analysis or the workflows. Whether you want to discover missing physics or calibrate these models or build control systems or build surrogates, or do something else that you haven't, that no one else has thought about, and you can pretty much pull up your model in Dyad, write a bunch of Julia code, and have it do any kind of analysis on the model. And Chris will talk a lot more about this, so I'm going to move on from this point. But this is the architecture of Dyad that really sort of takes the power of Julia. We like to say that Julia gives us superpowers, right? That you can do things that you could not do before. And it is this same idea that we want to bring into Dyad for engineers building physical products, building hardware. So here's an example of a real problem that we did. And some of you might have seen this on our YouTube channel. This is the NASA HL-20 personnel launch system. It was a concept vehicle that NASA built, but never designed, but never built due to shifting priorities. But it's basically a lifting body design, no large wings. The body generates lift. It's intended to be a safe, was intended to be a safe, flexible alternative for crew transport. A bunch of aerodynamic data was published from wind tunnel testing and a bunch of CFD simulations and stuff. In fact, Rajiv here, if you want to just raise your hand, Rajiv, is the person who worked on this and can tell you a lot more about it should you be interested. So this is what the inputs look like, right? It's a bunch of PDF files, and as you know that if you have old PDF files, they should not be scanned straight. They usually are scanned tilted just to make life interesting. But the models are fine with it. The LLM models are fine with it, and they can read all this stuff. And then you upload all the data as well. You got all the math in there. And we essentially just take all of this, craft the prompt, and put it into Dyad. The Dyad agent chugs away for what is effectively a couple of hours and builds out a complete validated flight control system that matches all the tests that are published in the NASA spec. We built this, I think everyone here believes that we are good at building compilers. I think, that maybe we can kind of take that as a given, right? But the interesting thing is, what happens with agents, right? As agents are beginning to write code and agents are building models, how does, why do we need a Dyad agent? Like, isn't it just good enough to have Claude code, give it the compiler, give it all the command line tools, and then have it go at it? And this is the first thing we tried, in fact, that, hey, let's just use Claude code. And it turns out it did not work out very well. And then, Anas and the team out here, if you're here, please, just raise your hands. Oh, there's our AI team, right? They're building the agent. And they built a harness that incorporates everything about Dyad, or everything about product design into the Dyad agent. And that just works and takes the problem to completion completely automatically, right? So imagine an agent with the right prompts, writing the code, compiling it, looking at the error messages, making sure that all the physics are in place, and then going ahead and running all the analysis afterwards, doing all of this unattended. It's pretty impressive. And I'll have a video that I can point everyone to. But this is not a product that is going to be ready later in the year. This product is already ready, and Chris here is going to talk a lot more about many of the details.
Hello, hello. Yeah, so Viral talked about this new agent that we had that come out, and I really highly suggest if you haven't seen the Dyad agent and you do a lot with modeling and simulation, especially if you say, oh, I don't believe that agents can do my problem, I've tried it with differential equations and stuff, give this agent a try because it has a specialized harness. The accuracy of agents for being able to do problems is definitely correlated to the way that the context is used. A lot of the context for something like Claude Code is built around building software. But if you want to do differential equations, if you want to build models, if you want to do engineering, right, you need the context to be able to, you got to throw everything out there about web servers. You got to say all the context has to be all about doing math and physics correctly. And that's basically what we've done with the Dyad agent to be able to make it do this. But now the next thing is to go from just building a model and bring this to something where you're going to building something out in reality, right? The next major step that you have to take into account is discrete time. Right, and you might go, okay, well, but the real world is all continuous time. It's like, well, the real world is in the continuous time, but all of our devices work in discrete time, right? You have a clock on your computer, right? You go, oh, gigahertz, right? That's the frequency of the clock on your computer. Or there's a clock, you can even see if you look closely at the screens, like it's blinking a little bit, right? Because it's not sending out continuous light; it sends light out at given time intervals, right? Every single device that we build is a clocked device. And so if we're going to start to build hardware, we need to go to and speak in the language of we have continuous systems and we have discrete systems, right? These are these event-driven and these hybrid dynamical systems, right? And so this really matters for the way that you're building models because you can think about, my control problem. When you think about your control problem, you can go, okay, if I observe let's say I'm trying to drive a car at that wall, right? You might just go, you're going to drive, you're going to hit the brakes once you feel like you're close to the wall, right? But if you now say, okay, I have a 1 second delay between my observing the wall and my ability to make reactions to it, you'll probably say, whoa, maybe I need to brake a lot sooner because of this delay, right? And so, if you just look at an idealized control of a motor, right? You can make everything work out perfectly, very easily, if you have no delays, if you have perfect view of the system. But in the real world device, you have to take into account you have delays in your sensors, you have delays due to the fact that the computing power is going to take a while. And if with all these delays in mind, how do you make a control system that is going to accurately, make a plane, be safe, right? You cannot just look at just the physics of the problem. You have to look at all of the discrete time hardware that is going to be involved, and to make sure that the interaction between those two domains leads you to something that is going to be a safe interaction. And so what this leads us to is we need things like synchronous programming languages, right? And I think a nice example of this is to think about a drone, right? So if you think about a drone, you don't just have one discrete world, you have many discrete worlds. You have a whole hierarchy of them, right? So you have very fast controllers you have a controller on every single wing, every single propeller, right? That is, how fast does this propeller move? I give an electrical signal and I move a propeller, right? So every single propeller has its own control on there. And that's clocked to be really fast, right? It's reading the propeller and it's moving really fast. But at a higher level, then you have a higher level control, which is, okay, how high do we want the drone? What level do we want this to be at, right? And then you have another level to your control, which is, well, let's do path planning, right? So you want to be able to say, the drone's right here. I want to send it to the back of the room, right? So you have one control that is doing a very high level. How do I move from the front of the room to the back of the room? You have another one that is saying, oh, let's stabilize it. And you have another one that's saying, here's how this single propeller moves. These are all moving on different clocks. They're all on different time scales, all in different frequencies. But you want all of these to synchronize together to be one system that is making the drone very easily move from the front of the room to the back of the room. And so this is what we call synchronous programming languages, or synchronous types of models, right? They are models of continuous systems like this drone that then have clocked systems where you have different clocks. You have some running at very fast frequencies, some running at very slow frequencies, but you have all these different discrete time behaviors, and you want all of this to line up to give you one system that is then driving a real world device, right? And what we're doing then with the dyad modeling language is we have both of these systems together. We have the continuous features, which it comes from this acausal modeling world. So if you're familiar with tools like Modelica, we pulled a lot of great ideas from there, especially great people with like Mike Tiller, to bring in all these ideas to be able to take this into modeling toolkit and give you differential equations which you solve and compile. This is our continuous world, right? And then on the other side, we have these synchronous features, right? These clocked domains, which go through something that we call sync toolkit, and then sync Julia, right? Which is a Julia-like language for clocked dynamics that can compile down to Julia and C as well. So what does it kind of look like? I just kind of want to, we're all language people, we're all compiler people here. I just want to at least throw a little bit of code so you can see, right? It's very Julia inspired. In fact, a lot of the language and the semantics are created by the same people who've worked on the GPU compilers for Julia itself, right? So if you're familiar with CUDA.jl and such, it comes from the same lineage. And what we've been able to do is we've been able to say, what would a synchronous programming language look like to someone who's used a lot of Julia? And if we want to be able to carry over all these ideas, like Julia's type system, if we want to carry over, if you want to be able to copy paste a code over and have it mostly just work in a synchronous embedded programming language, what would that look like, right? And this is effectively what we've gotten to with Sync Julia. It's a clocked language, so it acts very differently from imperative languages because, again, it's designed for this domain and for embedded coding. But if you look at this, you might understand very easily, like, oh, this has an output type of an integer, has an input type of a bool. I feel like if I know Julia, now I feel like I can do embedded programming, right? And this is really what we wanted to get to with this synchronous programming language. And yeah, and if you want to learn more about synchronous Julia, find Tim Bassard. Again, he's the same person who does a lot of the Julia GPU stack. So you'll find him around for many different things. This is why we have a whole compiler team at Julia Hub, and they're working on Julia and Sync Julia and all sorts of language type problems throughout this. Then we have a higher level here, which is Sync Toolkit, right? If you know Modeling Toolkit, then this might look very familiar to you as well. It's very close to Modeling Toolkit, except it has clock semantics in there where you can say, hey, look, I have a shift index clock, so I have a discrete time delay, and now I have a discrete system that is mixing with a continuous system. It's very similar to Modeling Toolkit, except now you're able to mix things with a synchronous discrete time behavior with your continuous time models. And now one of the things you can do is you can say, hey, look, I want to create a simulation of this. So give me the Julia code. And you can see it spits out all this Julia code. And you can use this with all your Julia tools. So you say, hey, I want to do automatic differentiation of it. Boom, forward diff, enzyme, all these things will work on there. So you can do all of your advanced, scientific machine learning, understand, optimize all your code. All the Julia stuff can be done on this. But at the end of the day, what if you actually want to make this actually fly the drone? What if you want to make this fly an airplane? Well, then you just do you do the sync julia.backend C, and there you go right there. This gives you the C code because again, sync Julia as a language is able to target both Julia and C. And so this is the kind of code that you can then go directly onto an embedded device and be actually running devices in the real world. And this is actually what we're developing to go through a regulatory path as well, right? So all these cases like aerospace engineering and automotive engineering, these require specific types of C code, Mishra-compatible C code that has, the ability to do cyclotomic complexity calculations, be able to make sure that it has MC/DC testing, all these extra details required for regulatory, we are doing through the Sync Toolkit path, and to be able to make sure that we can guarantee the safety of the C code that comes out, and all of this is going on within the Julia Hub compiler team to make sure that this is a complete programming language for these types of domains. And if you want to see an example, there actually Tim Bassard and Kieran will have a talk later. I would say if you're interested in seeing this all as it comes together. Their talk from graphical block diagram to Julius executable will actually be later today. So please go see this talk for more of this example. But what you're able to do is you're able to say, hey, look, here's a real hardware device, right? It's an inverted pendulum, right? It's a pendulum, and what we want to do is we want to drive a motor to be able to make the pendulum just stick upwards, right? Basically it's an unbalanced system, but we want to balance it by having a motor. And here's what it looks like using the multi-body components, using dyad. So you can build this visual model. Again, there's the visual model that has the code underneath. And this is actually then a real system, right? This is a real model, which then is actually driving the system, right? So you can see here's a simulation of the system. We can actually build this out using the tools that we have. It builds Mach-E animations. But then here's the actual hardware where we actually say click a button and you get the C code, and now you can actually run this code on the hardware and show that hey, look, it's actually solving the real world control problem. We have demonstrations. I think some of the demonstrations got stuck in the mail, so not all of them actually arrived to this JuliaCon. But we have different demonstrations where we're showing this. And again, the full synchronous toolkit will come out with the next release of Dyad. So this is going to be in the next month. And we'll have different kits for people to play with. If you want to be able to buy some of these robotic devices, buy some of these tools, and we'll have tutorials for you to be able to do this and play with robots at home, right? So if you've ever thought, oh, I want to do the Mark Rober-like thing, but I want to use Julia for it all the way through, this is how you'll be able to do it. So follow our YouTube channel. We'll have a lot of materials coming out. And we have all sorts of different models. Oh, I guess the excavator is not showing here, but we have all sorts of different, more complex models showing that you can build all sorts of detailed devices like excavators and robotic systems using our new multi-body library, which is coming out with the next release as well, right? So what we're aiming for is, again, this is bringing Julia to this real world where we're able to model these real world devices very easily, but then also generate the embedded the C code that will go into the embedded hardware. So this is about bringing Julia beyond being a programming language for computers to being a programming language for hardware. And I think that we'll end there. That we're changing the design V. We're really taking Julia away from just being something that is about your computer to being something that's now about building airplanes, cars, trains, and everything that you can that runs on software. So yeah, we'll take questions. Thank you very much.
Thank you, Chris. Thank you, Viral, and thank you, Gary. We have time for a few questions for either of them. Gary, would you mind coming back to the stage and maybe sharing a mic?
Hey, thanks for the presentation. I was a bit intrigued about the fact that you can target the C as a backend. To me, that sounds like a step backwards because with Julia we can target native code. So why have a C intermediary?
That is a very good question. So the question is why target C? Because there's a lot of things that Julia can do with native code and Julia C, right? In fact, a lot of the same compiler folks have been working on Julia C, right? Well, one of the issues is that in a lot of regulated domains, you need C code for regulatory reasons, right? Also, there are certain embedded chips, embedded hardware, where the chip designers only give you a C front end, right? And so we need ways to be able to interact with all these different devices out in the world, and generally the best way to do that is through C. Now, because Sync Toolkit actually can go through Julia as well, right? And Julia is an LLVM compiled language. There's other tools that are being developed which prefer having LLVM compilers. In which case, we are kind of the only tools that is well situated to say, yeah, if you prefer an LLVM compiler, we go here. If you want to, if you need C code, we go here, right? But our goal here is, again, there's with the embedded world, there's extra constraints on the types of code that is allowed to go through. And what we wanted to do with Sync Julia is be able to make it so that we could support as many devices out there as possible.
I think Gary should chime in on why C in the regulatory context, right?
Sure. Yeah, I mean,
It's fine.
Chris did a very good job basically giving you the context. The regulatory world is very, very slow. We are running at speed of, let's say, speed of sound, and they are just walking on the ground. So pushing the envelope is really not the part it's easy to do, but is to change the regulatory climate and bodies. And it's not just FAA for the North American airspace. You have EASA for Europe, there's Chinese, so they all have to basically come along. C has been the standardized programming language for embedded safety standards. And that's basically what it's for right now. C isn't perfect. It has many issues and challenges, as we all know here, right? And so I think we can influence the regulatory agencies about what is more optimized, more readable, and in terms of memory leakage, memory handling, in terms of performance, compile time, robustness of code, and embedded performance and all that. Frankly, I think if there's a body to standardize emulation and flight hardware, just like the automotive industry did for ECU development, for engine control unit development, if that's to be done for aerospace, that will open the door for onboarding new capabilities like Julia, for example.
Thank you for this talk. I have a question about the V diagram you have there. So typically, model-based design tools are, I would say, more associated with the lower half of the V, things like Modelica. But you've got Diet there in the upper half of the V. So I'm interested in how Diet integrates with requirements management and also with hardware verification tests.
I think, why don't you address the first part of it?
I'm going to take a very first quick shot at it, and then I'll let our Julia Hub friends talk.
Can I?
So the systems engineering V is very important for a tool like a Diet, because if you recall my earlier comments about making requirements being model-based, and that's the top left of the V. So that means that your model actually starts at the top left tip of the V, because you want the model to be the descriptive spec of your design before you get to the embedded systems dynamics, which is the tip, as you said.
Maybe, yeah.
I'll pass it over to Mike in a second here. I just want to say I did not show the requirements handling because it's not something that is going to be in the next release of Sync Julia and Sync Toolkit. But the requirements integrations to be able to integrate with tools like IBM Doors and be able to carry all the way through all the traceability from the requirements down to the C code and everything. These are planned features within the roadmap of our synchronous toolkit. We're working closely with the folks at Boeing to make sure it meets the regulatory standards. So while you have not seen that yet, definitely the requirements handling is a part of our very near future roadmap.
So I'll just try and address this question of where diet is on this map. So the thing is, typically, I mean, I can't speak for the aerospace industry, but in the automotive industry, when you look at this diagram, the top is really looking at the entire system, just looking at the vehicle as a whole, and then moving your way down. And this yellowish sort of colored area in here represents a point at which geometry becomes a key factor, you know, the detailed geometric parts. So dyad is above that line because it's largely a lumped system approach to doing modeling, right? So it's good, it's actually quite good going all the way down the V until you get to sort of that area. And then you transition into other sorts of systems that are built on top of PDEs rather than DAEs and ODEs. So I tend to look at it from the point of the mathematical problem. So sort of above that yellow area is the area where you have ODEs and DAEs, and then below that is where you transition into PDEs because of the geometry. So that's sort of why we see dyad as being in this sort of purplish region that you see on both sides of the V, I might add. So the design side is to be able to predict, if you have a design idea, being able to actually build a model of it without building hardware and deciding whether it's going to meet your requirements or not. And then after you've actually done the detailed component design, you have to sort of verify that on the other side once you have sort of a better understanding of the behavior of the individual parts. And so that's why it then flips over to the other side of that.
Where does embedded software fall?
Well, so this is an interesting thing when we talk about system engineering Vs, because there's sort of two. There's one for the hardware and there's one for the software as well. And so again, Gary is more conversant in this than I am. I haven't done this stuff in a while, but basically you have both the hardware design and you have the control system and ultimately the software. So the embedded stuff is going to tend to be on the right side of this diagram, where you're actually generating code and you're testing the code. And you tend to have more the dyad style graphical diagram representations on the left side as you're sort of building that out.
Thank you.
So the easiest thing or way to answer this probably, I think from my mind, is imagine your platform, whether it's a vehicle or an airplane, split that into different tiers: airplane, systems, subsystems, components, and each item then has its own V cycle. So the flight software has its own V cycle. On the top left, you have requirements development for the flight software. And so then you can replace that with a mathematical model. And so, and what Mike was talking about is the V for the entire product. But if you split and decompose your product into different components, you know, vehicle or airplane or whatever, and then you have system, and then you have subsystem, and then you have component, which regulatory calls item, then each one of these can have, or tiers can have its own V cycle. So you have mathematical modeling for requirements, and then you basically debug, you find problems early on in that top left of the V cycle before you get to implementation, which is the tip of the V, which is where you actually implement your code in this example. So that would be my, that's the state-of-the-art way of doing this.
Thank you. Any other questions? Yes.
Yeah, so having worked on space observatories, after you go from the operational phase, you go off to the right. And kind of the assumption is you know, once your hardware is built, it'll work perfectly forever, which it never does. Things start to fail. Particularly with space observatories, you launch the Hubble Space Telescope. Well, that's not the good example. Well, it's the James Webb Space Telescope. You can't go up and fix it, right? So, you know, in NASA, we model the shit out of stuff, right? Because we know that we can't go and fix it. The only thing we can fix is the software. And, you know, and so what it ends up is the software people fix the hardware issues if they can. But the other aspect is modeling failure, okay? And I just thought that would be something to consider in the future, right? If something fails, how do we mitigate that issue?
I'll take a quick shot at it because that's very aligned with what I'm working on, minus the NASA part. But so in an embedded system software, approximately 78%, statistically speaking, 78% of the faults are introduced during the early design. And so, and then you remain roughly between 18% to 20% of bugs post when you're done. So the end product ends up having bugs, but about 80% of them are introduced during early design. And so to your point. And so that's why model-based engineering is a lot more powerful methodology to be able to test drive them before we build the product, before we lock the configuration, before that gate comes, before we actually build hardware. So in reality, I'm not going to say that maybe someday we can eliminate all bugs, but in reality, we try to eliminate the majority of them early on so that we significantly reduce so-called problem reports. My experience so far has been that using model-based engineering, we reduce problem reports or faults or errors, right, roughly by 14x were implemented. And that's just the first generation implementation. So 14x reduction in problems is a very big number.
I think just to chime in very quickly for the people who may not have caught on to the point you made about the Hubble Space Telescope being a bad example, is that there was a problem with the telescope in focusing, and there was actually a mission sent by, on the space shuttle to fix the lens, which is an incredible feat of engineering. So I just thought I would add that context. Yes.
Yep.
Yes. So the point you made is Hubble could be fixed, but the other ones that are much further out, there is no hope of sending anything to fix them.
Yeah, I think the big thing here is, I mean, the word is predictive maintenance, right? Actually, one of the biggest areas of growth within Julia Hub and within our consulting division has been through predictive maintenance, right? So Dyad is finding a lot of utility for that. And I think that there's a good reason for that because, I think predictive maintenance might be one of the strongest areas for scientific machine learning, right? Because the idealized device is the device that you built. And then after you put it in the sky or after you fly the plane for a few years, right, you will get a slightly different engine. You'll get a slightly different, because it will wear down, right? And then after you have all the data in the field, you want to say, hey, look, I need to fix this thing. Well, how is my physics different, right? Do we have any methods out there that will tell me how the physics has changed given the data that I have? Well, this is the scientific machine learning that we developed for Dyad, right? And so I think one of the things that we're seeing is that this world, this tool is really finding a lot of pieces in deployment, right? And we might think like, okay, the design and the deployment are different worlds, but we're kind of seeing that with the way that the EV industry has gone, that being able to be able to mix the design and then use your same models in the deployment phase is actually very useful. We saw this, for example, with Rivian, where they deployed their car, and and then a few months later, they actually had a over-the-air update that improved their active suspension system, and so suddenly it was like, whoa, the car's more comfortable, right? Their hardware got more comfortable because of a software update, right? I think that this is the real world that we're looking at, right? That if your model improves, then you can improve the software and you just send it out to someone, and now hardware gets better, right? And so yeah, we're really looking at this world with predictive maintenance and how it also interacts with all the things with scientific machine learning. Like this whole story really comes together, and I think in a really nice way.
Thanks. I think we have time for one last question here.
Yeah, I was interested in programming with the clock in synchronous Julia. If I already know something like Verilog or another HDL, does that give me a good entrance into synchronous Julia?
Probably. I'm not actually familiar with Verilog, so I'm not sure I can comment. But I mean, this notion that you have gates and so on in a system is going to be quite similar, I would say, to the synchronous aspect. The synchronous aspect in these languages is very much tied to essentially either some sort of scheduling loop that's happening where the controller is being called at some rate, in some cases physical events that are happening that cause something, or some actual hardware clock that's triggering. So.
Yeah, I'll say that because we have a lot of programming language nerds in our crew and everything, right? There's a foundation that we pulled a lot from, which is the Lustre language, right? So Lustre is one of these languages that has like some provable, type verifiability and such from the synchronous programming kind of world. And so like folks like Ben Chung, who you might have seen at a lot of previous JuliaCons, he worked with Jan de Vitek's group and a lot of the group that did a lot of the type systems of Julia, all the proofs of that, and Cody also has been highly involved in this project, right? They've had this strong influence from the Lustre compiler. So I don't know as much about Verilog and its semantics there, but if you want to kind of know something, the semantics that stay close in some sense, Lustre is where a lot of it comes from, but also some ideas from the Medallica world as well have also been incorporated in there. Yeah, I mean, we can definitely talk in more detail about the language itself. And again, it's not released yet. It's going to be within the next release and more details to come out. But this is the lineage from which has been pulled on.
Thank you. Let's thank our speakers, Gary, Chris, and Viral, and Mike for answering questions.
you.
Thank you.
I'm just gonna go.
Time for a break, and we'll be back at 10 o'clock with talks everywhere. Thank you.
All right, hi. Welcome to this morning's session. This is Mridul. I have the pleasure of working with Mridul all the time. He's going to talk about securing the supply chain for the Julia ecosystem, which is something that he has been working with Matt Bauman on at Julia Hub for a while now. It's been quite a journey and a bit of a slog, but it's a thing that needs to be done. It's very important work. So I'm going to hand it over.
Let's go. Hi. Okay, let's start. So we're going to talk about securing the supply chain for Julia ecosystem, and by the end of 30 minutes, I'll try to explain all the machinery that we have built to make our ecosystem a safer place. But what's fascinating is how the community has come together, helped with the advisories, security advisories, help bring all the policies in place and all the scanning practices. So we're kind of there where we are now ready to scan and protect the ecosystem. So a talk is kind of based on the background, why it's required, all the policies that we have in place that helps to enforce this. And at last, somewhere we'll talk about preventive methods, which is very simple, but will go a very long way to protect our ecosystem. So what is a supply chain vulnerability? So basically, when we work on any project, we write a code, we ship it. But we are not just shipping our code. We are shipping the dependencies that are there in the code. And I guess that we are aware till there. But those dependencies might have another dependencies, and they might pull in some more. So we don't know about all the dependencies that we are shipping. And in one of those multi-layered graph, there might lie a vulnerability that can cause a problem later on that could affect a lot of users. So this entire thing is a vulnerability and how it enters a supply chain, how it affects a very broad audience. Did we have something recently? Like, is it worth spending time? Is it worth protecting the ecosystem? What are the things that have happened in the past? So for example, last year, September, there were like 18 packages affected, around 2.6 billion weekly downloads were affected. And it was just because the maintainer got pitched into a two-factor reset. And every account that manager, like all the packages that manager's account touched were affected, as simple as that. Then later on, there was a worm, which basically siphoned out the NPM tokens and republished itself through them, affecting 500 plus packages. 2 months later, a more sophisticated version of that surfaced, affecting around 800 packages. So this was something from last year. Most recently, people working on SciML, deep learning, would have noticed that Python package index, around 26 packages were affected. So it is there, and we have to have something to protect our own ecosystem. So something to notice is it's not something that the developers did. Nobody wrote a wrong code and shipped. It was through getting access to the maintainer's account and then creating havoc. So the question arises, why not we just scan it and get rid of the vulnerabilities? The question to that is, most of the vulnerability scanners just work on 1 layer or 2 layer. They'll scan your code. They'll scan the dependencies associated to them. But what happens here is we have a multi-layer dependency system. And so as you can see in the diagram, it's scanning the code, but it's not able to reach as deep down where the vulnerabilities actually lie. So one example is a CVE 2024-3094. It was XZ utils. So there was a backdoor hidden into the build scripts So a maintainer spent years gaining access, and then he later on slightly slid in a backdoor into the build scripts. So when the release will take place, it would be out. So it was caught by luck because somebody was investigating benchmarking and noticed a 0.5-second delay. And when they dug in deeper, they found out there was a backdoor. So it was caught by accident, not by a scanner. So you would have seen, I have talked about a number here, CV something something. So what are these? Let's talk about them. So for example, you're working and you find a vulnerability. Somebody else is working and they find another vulnerability, and they might find the same one. So there has to be a system which categorizes them into a common nomenclature so that it's easy to be referenced now and later. If there is a fix to that, it could be linked. So it's basically a system where we just bring in a common standard to particular vulnerabilities so that it's easy to find. There are certain agencies which do that. It's called the CNA, CV Numbering Authority. So one thing to note is CV is just the identification. It's not the severity. We have CVSS, Common Vulnerability Scoring System. It ranges from 0 to 10. Higher the number, the more vulnerable, like the severity is that high. It's more critical. So basically, then we have OSVs, NVD, GHSA. So these are different databases or places where we publish these vulnerabilities, and they are cross-referenced. So basically, when we find a vulnerability, it's reported, it's taken care of, and then published. So when we come to know about a CV, it's almost towards the end of its life cycle. Now coming to our own ecosystem, where are the structural risk factors? So I've been talking about deep graphs, so I'll not talk about it again. There are binaries in our graph. So basically, we have several wrappers. The binaries are the real strength. Like they build fast, they save the time, but they are a wrapper on C and C++ codes. So if there is an issue there, it gets just shipped with our product. So there's a problem. The other thing is everyone loves to download from general, and if there is an issue in the general, everyone downloading will have a problem. So in past examples where I've talked about a lot of vulnerabilities, those were the structural flaws as well. And we are learning from them. We are building a system where we can take care of all that. So the content of a resolve manifest. So when we make a project, we have project.toml that has the dependencies. When that gets resolved into manifest, so it pulls in all the dependencies that those packages depend on. So for example, a package.toml has around 12 packages, but a manifest.toml at the same time will have somewhere around 180, where this extra things come from. And a lot of them are binaries. So we need a system that not only scans your code, it goes deep down into till the last layer of the graph and scan everything, including the binaries. Fortunately, we are at the stage where Julia now tracks the vulnerabilities in its own ecosystem. So now we track the binaries. And how do we know that we are able to do it? I've listed just some, like there are 4 here. I'll not go into like a lot of detail what they are, but as you can see here, they have a CVE number, they have a JLSEC number. I'll come to this number a little later, but they have a critical a scoring system attached to it. The higher it is, the more critical it is. Now, coming to the Julia Security Working Group, how do we scan and find out about the vulnerabilities? It's because of this. Any scanner is as good as the data behind is. So that the database needs to be built. We have Matt Bauman here. He has a talk later today at 3, same tent. He pioneered building this. He'll talk in a great depth of how it's created, how it's maintained, how community is contributing to it. So it will be an amazing talk. Please be there. So basically, this is a place where we can report, a place to publish. It is something which machines can read. It's not a blog post, not a mailer list. It is something which machines can consume directly, build on it. And it has its own unique identifiers. We don't have to depend on CNA. That takes time. We can have our own nomenclature for the vulnerabilities that we find in our ecosystem, somewhat similar to CV nomenclature. So we are at a very nice stage. Now I'd like to hand over to Venkatesh. He'll walk you through all the technical depths on how the scanner works, where it gets its data, and so on. So over to Venkatesh.
Hey, hi. Thanks, Mridul. For the rest of the talk, I'll be basically discussing about how do we discover these advisories for these vulnerabilities and what can we do, what actionable things that we can do to prevent damages due to this vulnerability. So so in this slide we have mentioned that the repository where we will be publishing all the advisories. So it's julialang/securityadvisories.jl. Let's go a little bit deeper into what it has. I mean, among the source code that is required to maintain and publish these advisories, there is a folder where all the advisories are stored in a Markdown file. So each Markdown file essentially has information about the vulnerability that is essentially the vulnerability, information about the vulnerability. So here in the screen, you can see basically the structure of the Markdown file. We have the one-line description of the vulnerability and in-depth description of what it is. We have a metadata section in TOML. So let's look at some of the important, interesting fields, I guess. So it starts with an ID, which is a unique identifier assigned to this vulnerability in our database. If you see, there is aliases, which is essentially the same IDs assigned to the same vulnerability in other databases. Like, for example, the most popular one, the CVE one, and we have the GHSA, which is GitHub Security Advisory. So these advisory databases will have their own cadence and methods to ingest or publish these advisories. So not all. So that's one of the reasons why we have JLSec, right? We want to do it at our own time and help our users that way. So the other section is essentially a severity, which basically it's a special value. It's called a CVSS vector, which is a common vulnerability scoring system. What it is essentially a string. If you look, it has multiple parts, and each part describes the kind of attack it is. Like, for example, it could be something like whether a network is involved, or maybe whether a user interaction is involved. And the organizations and user will decide based on their requirement, like what sort of score to assign to it, how important that is. Okay. And the other most important section is what packages are affected by this vulnerability. We have a list. We have a version ranges. You can multiple version ranges within a package. And so you can see this is just a simple Markdown file, which is our own sort of format in some sense. But we want our external tools to also discover this. So we have an open standard document for it. It's called OSV Open Source Vulnerability Spec, which is basically a JSON schema of essentially the same information what we see in Markdown, but it's sort of standardized. Now let's look at some of the tools that users can use to discover it, rather than going to the repository and browsing through the Markdown files. The first tool that I want to talk about is the Julia Hub platform package server. So Julia Hub platform, among tons of other features, has always had a package browser. Julia Hub, currently on juliahub.com, hosts general registry packages and other Julia Hub proprietary registries as well. But the package browser itself, users are able to discover new packages and versions and browse with, They can, of course, they can connect their own PKG client to the package server to ingest this. But let's try to get an information about http.jl in the screenshot. So you search http.jl and you get the result. And upon clicking the result here, the top one, I think you'll find more details about the package, like things like the license, number of downloads, maybe page with the README that you find in the repository itself. We have data about the dependencies of the package, the packages which are dependent on this particular package. In the enterprise version of the Julia Hub, we'll have more information, like we generate the docs as well. Recently, we have added a new tab to this section, which is vulnerabilities. Let's see what is there in there. So as you can see, for a particular package, this page would display all the vulnerability advisories which are attached to this particular package. This page is typically associated with a particular version of the package. So in this case, if you see the top right side of it, it says that the version is not affected, which means the latest version that I've chosen here is not affected by any of these advisories. Let's look a little bit into detail what each row has. So it's essentially the same thing that we saw earlier in Markdown, but in much human-readable, prettier way. All the aliases have now hyperlinked, and so you can directly go to the websites of the other databases to find more about this vulnerability. The other tool that you can use to discover is the JH, which is a Julia Hub command line tool, which is a relatively a recent thing we have, which helps you basically manage and interact with the Julia Hub server. It's for the most part is in feature parity to the web interface. So as you can see, you can do the similar thing what we did in the web interface, but now with the command line. The client itself is open source, and you could find that tool in the repo listed in the slide. Yeah, so it's another slide which displays when you can also look at the dependencies as well, and the same thing. Now we have added the vulnerabilities option as well. Like you can scan and display the same vulnerability information. Now again from your terminal, again you can do it. You can use this tool programmatically as well to interact with Julia Hub server. One more interesting option command in the JS tool is to scan. So given a Julia source code, this tool basically uploads the project and manifest files to the server, and the server does the scan, and it basically refers the database that we have to list out all the vulnerabilities that is present in this current project. This is currently more of an enterprise option. We might make it available in future on juliahub.com itself. So the other tool, which is also uses this security advisors database to provide the information, is called Trivi, which is essentially an open source vulnerability scanner. It scans images, file systems, etc. Recently, in 2024, we added support for parsing, going through the Julia project and manifest files. At that point, it was just able to enumerate them and put it in a format called Perl, which is a standard to identify every package. Like it's a unique identifier across all package ecosystems, like in all languages. So basically, starts with the ecosystem name. In this case, if you see Julia / the package name and the version, and some optional identifiers. Like in our case, we have something like UUID. It's primarily used for SBOM generation, which is like software bill of materials. It's essentially an inventory of all the software components which are present in a particular source. Yeah, so this also provides a way to scan as well, which is similar to what we saw in the Julia Hub scan. So this was added last year by Matt Bowman, and who, as Mridul said earlier, we'll have an in-depth talk later in the afternoon with more details. So now we have the list. Now what do we do with the list, right? So there are sides of things. The client can go through the list and assess the impact themselves and choose not to use the package or not use the package. Essentially, in some sense, every project if it in an enterprise setup, every project or every developer will need to manage it themselves. So this is prone to human errors. Like people may not choose to do it, or they might forget it or something. So the better alternative is to somehow enforce this on the server side itself. Like there is a certain authorized people in the package server who decide like, okay, this is not good for the organization, and they can set policies, and the user need not know anything about it for the most part. So let me quickly go through so what the server means here. Essentially in Julia, when it comes to Julia, it's the package server. So Julia packages don't directly interact with GitHub. It has this intermediate system called package server, which sort of is repo agnostic. You can store it on any Git repositories, and it provides a very simple interface to access resources related to Julia, like the registry list, registries, packages, and artifacts. So you could set your Julia client to a different package server using the environment variable. So for the rest of the talk, I'll be mostly talking about the Julia Hub's package server implementation, like how we have implemented to use the vulnerability information to enforce this stuff. So essentially, the Julia Hub package server, as part of its ingesting resources, has this 4 essential steps, which is first is to pull the registry from the upstream, the mirror all the resources that is published in the registry itself. And we have this enforce step where the package server will have policies surrounding what packages the user should see. This could be based on something like licenses, like certain GPL licenses, maybe we don't want the users to install. And of course, this is where our vulnerability information also can feed in, and we can apply policy and publish to the user. This is somehow, this is typically the interface what our administrators of the package server will have. We'll have list of all the advisories that are present in the database, which gets synced frequently, and which provides almost the same information that we saw earlier. But now the administrator has a control to apply a policy which essentially blocks all the affected versions of the vulnerabilities. Sorry, versions of the vulnerability. And so once this policy is applied, so essentially during the next sync cycle that we saw earlier, all the new, essentially those blocks will get yanked, so the users will not basically install it. So there are certain limits, even with this approach. Is like there will be, of course, for any issue vulnerability out there, first it has to be reported, and there has to be an advisory, and sometimes people don't. I mean, there could be people might miss it, or maybe the user who notices it might try to hide it and do some try to exploit the system. So that's what similarly happened with the XC util system that Mridul spoke about earlier. It was basically, it spread through a lot of, if not lot, many of the some of the distributions where it was supposed to go, and but it was accidentally detected. So what do we do about something like this? So the simple approach, I think the easiest approach is something like we enforce a cooldown period on updating the registry. And a cooldown period is basically we don't update the registry for a particular period of time. This works surprisingly because malicious releases are quickly identified. Someone will notice it, and it takes like a couple of days or weeks. And newest releases are rarely worth it because one is the reason what I just said, or B, you don't want to have things breaking out there. So it's always good to have be conservative when it comes to updating stuff. General registry sort of applies this principle in merging stuff into general registry itself. Like we have a 3-day cooldown period for the adding a new package, as well as like a 30 minutes cooldown period for the new versions itself. and many registry distributions have done. There is a con with this, which is basically if there is a hotfix, then we'll have to we have to do somehow cherry pick it, but that comes with own issues when it comes to Julia, because now it has the depths associated with which also needs to be backported. But so in the end, so the summary is that we have discussed the process, what is there to report vulnerabilities and to discover it. I've gone through a few of the tools that you can use to discover this, and a mechanism to enforce in the package server, which we can maybe do it in the open source package server as well, and a simple measure to not be a little bit conservative when it comes to installing things. I guess that's. Thank you. That's it. That's all I had. Any questions?
Thanks for the great talk. It's really nice to see this because a lot of my colleagues who are less Julia enthusiasts have been talking about what are you doing about supply chain attacks for ages, and I haven't really been able to tell them anything until now. I can, which is excellent. I think it would be really wonderful to add this to the general Julia package manager as well, to have the same kind of functionality, because otherwise the open source pieces of Julia just get left behind, and that would be really bad. I had just two quick questions though. To generate the Julia specific advisory, are you also monitoring like the CVEs and the other advisory publishing things? Because we're not going to generally discover things ourselves. We're going to discover things because somebody else noticed them in another package. That's one thing. And the second thing is, could we maybe consider as well doing an impact assessment on current packages in the registry? Because often we might lock versions and we might discover that my package is now dependent on another package which has a vulnerability in it, and I haven't allowed the latest version. So as a maintainer, I'd really like to get an email to know that, oh, you should really update this particular package, put the work in, because otherwise I'm shipping something that implicitly contains a vulnerability.
Yeah, so on the first question, I think Matt would be a better person to answer this, because I would generally think that we are scanning the other databases, and we, when we find it, I think. Yeah. On the second part, yes, I think an email would be generally nice, and with the Julia Hub platform itself, that is the case. Like typically, when there is a critical vulnerability, also, all the users of the system will get a notification as well, and even including the administrator, so will be able to enforce it. But maybe the open source could do something similar as well, I guess. Yeah. Thanks.
It's much harder to do this sort of thing in open source because, the enforcement is against a specific policy. So then you have to have like a way for people to give their policies, and I mean that's not really what the open source project is going to do. But I mean all the open source packages that are registered are on the Julia Hub, package search thing, and you can go look at them, and all the security vulnerabilities are listed there. So it is available, and the database that Matt has built is all open. It's available for people to look at and work with. We also have a security working group that meets every other Friday at it's 11 Eastern. I don't know what that is in this time zone, but I guess that's 5 p.m. Fridays. I think that's right. Any other questions? Yep.
Sort of related to that, I don't think, or I don't want to say I don't care about security as much as I think a lot of people do. So I'm not going to join a working group. I'm not going to. But if I have a vulnerability in my package, I would want to know about it so I can change things. But it's not the kind of thing that I'm going to like go out and look for. Whether my pack, because I'm doing biology, I'm not thinking about security. So it would be nice to have some kind of well, I don't know if opt-out is the best way, but some more advertisement around, like, if I'm a package maintainer, can I just set up a CI job that's part of a normal thing that will occasionally remind me if any security vulnerabilities or something pops up?
One thing we might be able to do, at least for packages that are hosted on GitHub, is just open issues automatically. That could be possible. Other questions? All right, thank you.
Thanks, everyone.
All right. Okay, we'll see how this goes. I'm not used to not being able to see my own screen, so you guys will have to scream if you can't see anything. Well, welcome everyone. Thank you for coming to this talk, and I'd like to thank the JuliaCon organizers for inviting me again. My name is Joshua Belenko, and today I want to talk about using Julia to solve the no language problem. We've all heard about Julia solving the two language problem, and this is the next step. All right, before we dive in, this is actually my 4th time presenting at a JuliaCon. I don't bring this up as a brag, but I did just kind of want to give you sort of the theme that my talks over the years have sort of had. The first time I spoke, I made an assertion that Julia would take over from Python as the primary language for scientific development. That was 10 years ago. 3 years after that, I thought I had found Julia's killer app that was going to convince all general-purpose programmers to switch over to Julia. And last year, I gave a talk about REPL-based development that I called Julia's secret superpower. I tell you this because this is your giant grain of salt to take along with you on this talk, because I have found myself getting a little over-exuberant on this subject, but I really, honestly do think this time, there's something truly magical happening. Okay. All right, so I wanted to start off by taking a quick look at a brief history of communication. We'll start a couple 100,000 years ago when humans invented spoken language. Now, why do we start with spoken language? Well, we like to think that we humans are special because we're capable of abstract thought, that we can imagine things that don't exist and ask questions about things that we can't directly observe. But honestly, you know, maybe other animals can do the same. You know, maybe my dog is the world's greatest philosopher. I would never know because my dog can't talk to me, right? So what really makes humans unique is the fact that we can actually not only have abstract thoughts, but communicate these abstract thoughts with each other. Okay, so we're going to fast forward 100,000 years or so to the advent of written language. Now, why is that on this timeline?
Well, spoken language allows us to communicate abstract thoughts with each other, but spoken language is ephemeral. It's not until we can write that language down that we have the ability to distribute abstract thoughts widely in both time and space, to revisit abstract thoughts, refine them, and sort of study them. Right? So it's another very important advance in human knowledge. I'm gonna skip forward a few millennia to 1947. Now, why do we jump all the way forward to assembly language? Certainly there were multiple advances in between there, but I picked this time point because up until 1947, language was only used to communicate abstract thoughts from human to human. Assembly language was the first time that we made an attempt to communicate an abstract thought to a machine. Of course, if you've used assembly language, you know that those thoughts are not horribly abstract, so it didn't take very long before high-level languages like Fortran and Lisp came about that allowed us to use more powerful abstractions to talk to the machines. And since then, we've had a bit of a history of more and more powerful abstractions. I'm going to skip forward a little bit to February 14th, 2012, the first public release of Julia. Now, why is this on the timeline? Well, we're at JuliaCon, and if this weren't on the timeline, you wouldn't be here. But I also think that Julia represents a very interesting and unique opportunity in this history of communication of abstract thought. We'll get back to that. After this, I'm going to jump forward a decade or so to November 24th, 2025. Now, why is this on there? Well, by show of hands, I'm curious how many people here over the last 12 months have gone from writing 100 to 1,000 lines of code de novo per day to 0. If your hand's not up, I'll be back to JuliaCon 2027, and I'm pretty sure the entire room will be raising their hand. AI is not coming. AI is already here, and it is already having very profound, fundamental impacts on the way that we program. You don't have to take my word for it. You can take the CEO of GitHub, who casually happened to leak a couple months ago that in 2025, GitHub hit a watershed mark of 1 billion commits in a year. And in the first quarter of 2026, they were already on pace to do 14 times that much this year. If it was linear growth, which it's not. So we're talking orders of magnitude more code in the last 12 months. I often think about this quote from William Gibson. The future is already here. It's just not very evenly distributed. So if you aren't using AI in your day-to-day today, you will. So why was Opus on that timeline? Well, in talking with friends and colleagues, I found that Opus 4.5 kind of marked a very interesting sort of before and after period. Because before Opus, you know, lots of people, myself included, considered AI coding as glorified autocomplete, you know, or capable of doing the same sort of, you know, code monkey tasks as a junior developer, filling in function bodies once you've already designed the method signature. After Opus, we have AI generating full code with tests and specs that you'd never bother taking the time to write. We now have graduate student-level research assistants. I happen to have left academia before I got a lab of my own, so I never really got to know what it was like to have graduate students, but I can imagine what it would have been like, and Opus is that for me. And we're no longer just asking it to fill in method bodies, we're asking AI to design entire full architectures. But it's still written human language. So I think the problem with the coming advent of AI-based coding is not so much that it's going to be flawed or it's going to be error-prone or it's going to hallucinate. We're resolving all of those issues. The real problem is that if you look at the history of communication, we're taking a giant leap backwards if we restrict ourselves back to written language. We've spent millennia having more and more accurate ways to communicate with each other that we've just kind of erased because communicating in written language is convenient or what have you. Okay, so what would a talk about AI be without a crudely AI-generated animation? So it turns out we actually have another way of communicating that we've developed over the last couple of centuries. Science. And science has given us ways of taking these abstract concepts like gravity, right, and putting more concrete definitions to them. You can even have something as complex as general relativity expressed in a relatively terse set of symbols. So I think the answer is not to go to more and more verbose written prose, but to double down on the abstractions that we already began developing with programming languages. And this is where I go back to that famous Abelson and Sussman quote, that programs must be written for people to read and only incidentally for machines to execute, right? But I would append agents and people. We need to write programs that our agents can read and understand, not just us. Okay, so why is Julia the perfect language for this? Well, for all the reasons that I'm sure you as attendees at a Julia conference are very well aware of. It is an extremely powerful language, capable of very powerful abstractions, has a wonderful community, and oh yeah, it's fast. Okay, so go fire up Claude Code and point it at Julia, right? Talk done? Well, not exactly, because I think we can do better. I would obviously encourage you, if you haven't tried using Claude Code with Julia, go ahead and give it a try. It's a rather enlightening experience. But I went ahead and developed a thing I call Wink. Now, that's the GitHub URL, but it's not published yet. Haven't quite got around to that. But let me see if we can read that. Okay, so what Wink does is it adds a new REPL mode to Julia. So now I can trigger AI. And this is just like Claude Code, except it's running in my REPL. So, hey, Wink, can I get you to auto-eval so I can keep going with this talk? No, you didn't enable auto-eval. You just thought you did. All right. So occasionally it hallucinates, but once in a while it'll get it right. OK, so Wink just figured out that it has a setting, it knows about its own settings, and can introspect its own modules and documentation. And it figured out to turn on auto-eval. OK, so I'm going to save you the trouble of watching me type this all out. And we're going to now ask Wink to generate a blog engine for us. We're going to ask it to go ahead and set up a Julia package, create an environment, bring in some packages. And while all of that's going, I'm going to go back and talk about agent harnesses. So if you're not familiar, Claude Code is an agent harness. And after code models, or LLMs, got capable of generating code, code generation with a model became more of an engineering challenge than a theoretical one. So you need to give these models harnesses so that they can actually affect the outside world. They need to be able to edit code, run shell commands, look up documentation. And because LLMs work within this context window, where they can only think about so much at a time, they need to be able to store memories for when that context gets too large, and they need to be able to compact that context eventually. And yeah, of course, they need to connect to a model as well. OK, so let's see. Okay, so what did Wink come up with? So it's going to come up with a context, comment struct, a post struct. Wants to know if it should go ahead. So I'm going to go ahead and let it write out some files, give us some types. OK. So what is Wink doing? Well, for editing code, we just use write. We give it a tool that it can use to write files. And oh, it knows what revise is. So it knows that when it writes a file, it should go ahead and trigger revise to go ahead and reload that file. What about running shell commands? Well, Julia has command objects and the run function. So if Wink wants to run a shell command, it just creates a command object, and then it evals run, right there in the Julia process, right? So this is all happening inside of that REPL process. What about looking up docs? Julia REPL has docs, right? You can use get doc, or if you want to do something more complex, I went ahead and threw on a quick vector store in memory, and you can do a little bit of RAG as well, right there in process. Here, let's see, how did we go? Yeah, OK, so it's going to give us a nice, yeah, that looks good. All right, so how are we doing? So, you know, it's generating some functions and structs for us, so pretty good so far. We'll let it keep going. All right, so what about memories? Right? This is where there's massive competition between, you know, Claude Code, Codex, Cursor, all these various agent harnesses. At some point, they break down or, you know, really stand out in their ability to manage memories and compact context. And this is where I really like what we can do with Julia. So how do you store a memory with Wink? You write code. Because it's living right there in the Julia process. If it needs to remember your name, it can write a function that says your name that returns Josh. And then the next time it needs to know my name, it can look at all of the functions available, because again, we can list the functions available in our process, and it can see the one that says name and just simply call it. And we have instructions that instruct Wink to do a 3-tier compaction. So tool calls, because they're happening in process, can always be reproduced. If we do a tool call to list out documentation or list out functions or list out a method signature, right, we get a response back. If we start running out of context space, we can just erase that, because Wink can always go back and get it again, because it's in the same process. Then if there's more compaction that we need, we can do a little bit of summarization. But when we start to really feel pressure of context, we instruct Wink to go and build more software. Take these ideas and turn them into code. Turn them into higher and higher order abstractions. Build functions, build types, build macros if you need to. So that's what it's doing over here. And oh, and by the way, because this is all happening in process, it actually has full access to the full Julia error types. So when it evals something incorrectly, it knows exactly what it did wrong, and it can make those updates and fix itself. So last bit. What about connecting to a model? Well, there is this package out there called Prompting Tools. It allows you to connect to OpenAI or Anthropic models. And I used it in Wink to make initial connections out to the host of models. But in fact, see if this one comes up with a little better. OK, so now we have a database store that's being built out. And some test content. Seems to have duplicated our source directory. So it's not perfect yet. But what's really interesting about all of this is, let's see, can you load the Postgres package for database connections. So it's going to search for packages. We have a package index that also is based on a RAG. And this is the fun little joke. So the secret here is I haven't been connected to the internet this whole time. So this has actually all been running on a local model on my machine. This is Gemma 4, 24B, what is it, A4B, quantized to 4 bits, running on my machine. I'm not paying OpenAI or Anthropic a dime for any of this demo. So, yeah, I started off with a prompt. I told Wink to be in on this little joke and say, I can't do that, Dave, when I got to the point where it needed the internet and it couldn't connect. So, anyway. So I really believe that Julia and using Julia not just as a target language for a harness, but as the harness itself, with the model running in process, with tools that connect directly to Julia's own introspection routines, represents something really amazingly powerful for agentic coding. Right now, we have a whitelist of what Wink is allowed to do without asking for permission. But it wouldn't be that hard to hook that into the language as well. We already have this concept of assume effects and side effects that we document for various routines. We also have that fixed list of tools that I gave, right? So this is the ability to do some introspection, some editing of source, searching and whatnot. But you could imagine it wouldn't be too hard to allow Wink to expand its own set of tools, since the tools are just function calls in the process that Wink is running and evaluating code in. We could also potentially, if we have checkpointing of a REPL process, allow for checkpointing and rollback of an agentic coding process in that REPL. We could also, in the future, I might explore the possibility of doing some more codifying of the types and multi-methods that drive Wink to allow for extension. And like I said, right now, I'm generating my own vector store of documentation for methods and packages that are used in this RAG-based lookup in memory. But if package maintained a vector store, we could just ingest that directly. To be perfectly honest, it doesn't take that long to generate it. I think the full list of methods takes around 30 seconds to generate the vector store, and the slow part of generating the package index is GitHub's throttling. But ultimately, I hopefully see this being the start of millions of easy-to-understand Julia types, functions, and macros developed in conjunction with AI. So, and with that, any questions?
Hi, thanks so much. I found this very cool. When you have this toolkit, right? So in several programming languages I've seen, they have they also have REPLs.
Yeah.
There's MCP servers that can go into the REPL and give you, information about the, I don't know, memory and whatever's going on in the VM or whatever the process. Is there something that you would consider in this case here? Like Julia, I've seen is Gaimon JL or something? I don't know.
You don't need it, actually, because because it's running in process. So you bypass a lot of the machinery that other languages need to lean on, like LSPs, like MCPs, because you're actually running the agent in the REPL process. When the agent says eval, it evals in the REPL process. In your code base, yes. So, you know, I come back here, right? Just hit backspace, I'm back at my Julia prompt. Say post, there's post. I say, create a post, and yeah, or push a post. Well, okay, didn't do that, but. Okay, yeah, so it's telling me I need to actually provide some. But yeah, I mean, there's no need for any connections. This is the REPL process.
Yeah, first of all, very cool project. I wanted exactly this, to have the same Julia session to run the agent. I was wondering if you have done any benchmarking on how token efficient is this compared to MCP server or something like that?
I haven't. I mean, like I said, you know, so I do have an M4 Max with 48 gigs, so it's not, you know, it's not a small machine that I have, but, you know, within reason. In fact, the Gemma 4 that I'm running is, this is overpowered for it. So you can run Gemma 4 on a machine with about half the capabilities. So I haven't done any actual benchmarking, but I mean, so far, just in using it and iterating on it, I haven't really noticed a huge slowdown at all. So, yeah.
No, I meant more token efficiency in the sense of, like, you know, when you pass a lot of context with an MCP server, like, there's usually a cost in tokens.
Yeah, so
more efficient, but I don't know how much.
Yeah. So I mean, so I guess there's two answers to that. One is I have not connected this to a frontline model in a couple of days. I suspect, though, that the frontline models, this would be far more token efficient, because like I said, because we're doing the actual eval directly in process, we eliminate certain kinds of hallucination that harnesses, other harnesses need to guard against, right, and protect against. You know, you have like a Python script, for example, that you're generating, and if you watch what Claude Code does, right, it will generate the Python code, and then it'll immediately fire up the Python interpreter just to make sure it didn't make any syntax errors, right? You don't need to do that here, because if you don't eval it correctly, then it just doesn't eval, and you immediately get the error right back out. So,
I actually had a quick question. The saving code as memory thing sounds cool, but I don't quite get what it buys you, what the real benefit is.
So the idea is that when you're working with a coding agent, right? So I guess first of all, I should mention, so this Gemma that I'm running locally, I've got a token context window of around 32,000, which is kind of small. If you've been paying attention, you know that like the latest Opus model, it'll give you 1 million token context window, right? The reason I do that is because Gemma is actually tuned to up to 200,000, right? But there's this degrading capability that happens as you get closer to that limit, right? So you want to keep your token budget much smaller than what the actual trained limit is. But anyway, to answer your question directly, the idea is that that context, right? You're not, when you're doing this as a coding agent, right? And not just, you know, ChatGPT out on the web, presumably, you're doing this because you want to accomplish some coding task, right? And so the idea would be that instead of having to save off prose memories, right? Which is what most of the coding agents do, right? You say, oh, I want to work on a blog engine, right? And Claude Code writes out a memory. We're working on a blog engine, right? In prose, right? But instead, what Wink does is it says, great, let me make a module called blog engine, and let me write some documentation in that module that I can look up later, right? So rather than saving off memories in a memory file somewhere in prose to be pulled back as prose, we're immediately codifying everything that we're trying to do in code and driving the abstractions, right? So one of the problems that I think a lot of coding agents and AI-generated coding has is that because most of the training set is relatively small functions, the coding agents tend to generate relatively small functions. They don't work at higher levels of abstraction. And most of that has to do with the fact that there's no pressure for them to, right? They have a million token context. So why not generate 200 three-line methods, right? When you can fit it all in context and think about it later, and you know, the humans are never going to read it, and I don't need to worry about it because I've got a million token context, right? But if we squeeze that down, right? If we force the context to fit much smaller, then we drive the model to actually do the abstraction that you want to do anyway. Because the whole idea, right, is that we don't want to write 200 lines, or sorry, 200 three-line methods that we're never going to read. We want to write 3 macros that if we want to understand what they do, we go and we look at the implementation of that macro and the functions that it calls. And if we want to understand what that does, we go and we look at that specific function, right? So.
Yeah, thanks for a talk, very inspiring work. The harnesses usually also provide some sort of sandboxing. Do you have anything in place that we don't shoot ourselves while giving it a try?
Everything that the Julia REPL does and doesn't give you. So. It's as sandboxed as the Julia REPL.
There is a thing Keno made called cloudbox.jl, which provides sandboxing, unrelated to this, but you could maybe use the two together.
Yeah.
I think that is all the time we have for questions.
Hello, everyone. We're ready for our next talk, which is Kiran and Tim giving a talk on graphical block diagrams and turning them into Julia C.
Okay. Good morning, folks. My name is Kiran, and Tim and I are going to give you a little look into Dyad's new synchronous capabilities, or how we go from a graphical block diagram into an executable. So let's dive right in. We will give this talk in the context of this device. This device is a Furuta pendulum made by Quanser. They call it the Cube Servo. We'll use this as a representative example. This device was invented in 1992 and is very widely used in control systems theory as an example of a complex nonlinear oscillator. So we've built a model of this device in Dyad using the multi-body components library. And you see the diagram there on the right of the device. It has one input, which is a voltage, and it has two outputs, which are a shoulder angle and an elbow angle. So the model itself has a revolute joint, which is the joint here, and it also has upper arm and an elbow joint. So this model essentially represents the device in its entirety, and it is, as you can see, a block diagram. However, in hardware modeling, real systems have not just the continuous mechanics that you see in the block diagram of that device, but they also have sampled sensors, discrete controllers, which have modes. A controller, the terminology often used is plant and controller, plant being the device and the controller being, in essence, the software that interacts with the device. And the control in this device will handle things like homing, the swing up, LQR stabilization, out of bounds recovery. And you can see the block diagram of the entire system in this picture here on the right, where the cube pendulum over here, the little picture over there is the actual physical model, and the rest of it is the controller. So you see that there is a sampler for the shoulder and elbow angles and a periodic clock. And the control system over here is what handles the logic for the homing and the swing up. Commonly, it is the case that the simulated controller is hand-coded after the model is built. And so people end up with essentially two implementations, the visual implementation and then the hand-coded implementation, and they have to keep it in sync, which is not ideal. And this is, in fact, what people mostly use Simulink for. You draw the controller as a block diagram next to the model of the plant, you simulate it, and then you generate the code that runs on the device without handwriting any C code. And that is the ideal, where you have the same model that allows you to do the simulation as well as deploy. And here we see Dyad doing precisely that. On the left-hand side, you see the simulation, which is generated using the wonderful Maki. And that is a video that has been produced, but when you are doing this interactively, you can move a slider to position exactly where you are in time and inspect the model. On the right-hand side, you see the actual device alongside a Raspberry Pi and some cables for power and for the USB controller. The very same block diagram simulates both against the multi-body plant, and it also deploys to hardware. The QR code there on the top right links you to a YouTube video produced by Frederick Carlson, who was a significant part of this work. And it goes into a lot more detail and walks you through exactly how these models were built. So here we see two views of the same model to go a little bit into more detail about the simulation versus deployment. On the left, of course, is the simulation, as we saw previously. On the right, you can see a different view where the model has now been replaced with the actual hardware. And there, the control system is still in the center there. It gets measurement information from the sensors on the device, and it does what computing it needs to do, and then it issues commands. There is a diagnostics block, a logger block, and both of these are the exact same model. So we'll now, Tim will now go under the hood a little bit to see how we go from this diagram on the right to the actual executable that runs on that Raspberry Pi.
Thank you. Yes, I'll have a look at how we go from this diagram to something that's executable. However, the model as a whole is much too complicated to show on a single slide, so I'll be zooming in first, zooming in into a block that we can analyze. So here we have the whole model. I'm zooming in on the control system, zooming in on the homing block, and then the homing block contains a velocity estimator, and the velocity estimator contains a discrete derivative, which is finally something that's small enough to fit my slide. So again, the goal here is to go from this model, from this discrete derivative, to something that's executable. The model itself is implemented in discrete dyad, as has been shown during the keynote. And in order to go to executable code, we go over something called a synchronous program, which is a program that's implemented using a synchronous programming language, which is a programming paradigm that offers you a way to express discrete behavior in code. And there's a variety of languages. Lustre is one of them, and we've designed a language in Julia that makes it possible to express these semantics. But again, we start at discrete dyad code. So this is dyad code, as you've all have probably seen a couple of times at this conference. I'm not going to go into the details, but it is discrete because at the top there is a input clock extends discrete that makes this model a discrete model. And then we have the typical things. We have an input U, an output Y, a couple of parameters, and two relations. One relation describes the derivative, the other relation describes the initial condition. And one of the advantages of this being discrete allows the relations to point at previous value, which is the at clock minus 1 syntax. In any case, this is compiled down to a MTK model, an MTK component. This is a fairly literal translation, so we still have our variables, our parameters, and our two equations coming from the relations that we had at the dyad code. And this is then compiled down to Julia, which is the programming languages I mentioned before, making it possible to write synchronous programs in Julia. So this is a DSL for synchronous programming, implying that it's a data flow language. You can, for example, see how the upref is only defined after it's used in the Y equation. So because it's data flow oriented, that doesn't matter. We have temporal operators, for example, the pre-function, which corresponds to the at clock minus 1. And this pre-function makes it possible to fetch the value of U at the previous clock tick. We also have clock syntax, which is the caret clock 1, and some clock operators to perform clock sampling, clock subsampling, and so on. Of course, this isn't executable. This is a Julia DSL. It has all of the familiar idiomatic behavior that Julia normally has. So you can use redefinitions with this, you can use types with this, but it's not executable. And in order to make it executable, we compile it first down to a data flow IR, where we perform a bunch of analyses, such as clock inference, causality analysis, and then we schedule the data flow language into something that's imperative. So we have an imperative IR, where we don't have data flow expressions anymore, but we now have statements that can execute. I'm going through this quickly because the whole goal of this is just to be able to go from this imperative IR to a whole bunch of backends. And of course, the prime backend that we emit code for is the Julia backend. So here we have a step function and a reset function, which is typical with synchronous programs, matching the dyad model I showed before, matching the Julia code I showed before, where clock expressions have now been lowered into branches. and the temporal nodes have become accesses of a state object that's passed down to subsequent invocations of the step function. This is then executed using compiler caching, which is a package that we've developed also for the purpose of the Julia ecosystem as a whole. For example, the Julia GPU ecosystem is already using this, making it possible to use revise, pre-compilation, and also crucially package compiler and Julia C with these synchronous programs. And this is very relevant for us as a company because, of course, we want to be able to deploy these synchronous models. And for example, we can do so with Julia C. So with Julia C, we can include our SyncJulia code, we can instantiate a synchronous executable at top level, and this will, as a result, be entirely statically compiled. And then we have a main function, which is our driver function, using the executable, for example, to drive the Quanzer controller we showed at the beginning. And then we can compile this with Julia C, and we get a 1.6 megabyte binary implementing the control logic that was originally implemented in Diet. So this is nice, but actually not usable for some customers because, as you can see, the whole bundle is still 50 megabytes. But also Julia C implies that the hardware we're deploying on supports Julia and supports LLVM, which is not always possible. So for those customers, we also have a C backend, which makes it possible to compile our SyncJulia code into C, as you can see here. And this code is fairly similar to the generated Julia code. It still has the branches for the clocks. It still has the state argument for the temporal operators, but it's generated C. And for regulatory purposes, we also support certain things like provenance tracking, where every line of generated code can be tied back to a definition in the original model. The generated code is also MISRA compliant, or at least it's relatively, we're working towards getting MISRA compliance. But the whole benefit of generating the C code is then we can export our whole model into a directory with C code and compile this down to a 35K binary, which is still a huge difference over the 1.6 megabyte binary that Julia C produced. Of course, this has limitations. Cross-compilation to C does not support all of the language, so it's always a trade-off. But at least in this case, we managed to compile the whole Quanzer model into very portable C code.
So to wrap up here, this was just kind of like an overview of the whole thing. There is probably a lot that we could discuss and expand on. But to summarize, we've shown a model for the Furuta plant. We've shown the clocked controller as well, both of them in a singular diagram. We showed that you can simulate those, and you can also compile that, produce synchronous code with explicit state, with clocks, and then you can deploy that to an actual device. And check out the QR code. This is another kind of what we're doing, what we've said over here. That I must reemphasize, because this is a key part, that the deployed controller is compiled from the same model that was simulated, not some transcription, not some hand-created bit of code. And under the hood, of course, is SyncJulia, which is built on the open source Julia compiler ecosystem. And anybody who'd like to know more should come and talk to us.
Great, we have time for one or two quick questions. Okay. Everyone's questions are answered. Great.
The switch is off there.
Yeah. Is it working? Okay, great. Cool. Hello, everyone. I'm really happy to be here. I love to see Markey being used for all this amazing science here at JuliaCon. And yeah, well, these are the core contributors for Markey who have been working full-time sometimes on Markey. I'm a freelancer, and I've been managing to work on Markey full-time for the last years. Frederick as well, who has been doing a lot of amazing work for Markey, also in his free time. And a lot of the stuff we are actually presenting here is also has been written by Frederick. And with that, I give to Julius.
Right, I'm Julius Krumwiegel. I currently work as a senior product engineer for Pumas AI. And I have been able to work on a lot of this stuff also for adjacent packages like Algebra of Graphics on their time. So thanks to them for letting me work on this open source stuff. And of course, we also have a lot of contributors, currently 277 and counting. So let's jump right into one of the largest changes that we had in Markey in the last year or so, which was our change from observables in the internals to the compute pipeline. I did a small graphic here to show what the main point of this was. So in the upper row, you can see that with the observable structure, when you had something where observables flow together in another observable, let's say like assembling points from two separate vectors, then when you updated one, you would get a size mismatch, and this errored out, and your plot was basically broken. There was, in many cases, no way to recover from this, especially if hidden in somewhere down in someone else's plotting code. So the refactor was to put all of these free-floating observables into a graph structure where you can traverse the graph and look which of these have been updated and which of these need to be updated still. So now there's an update function to which you can actually pass multiple things at once, and the graph will simply invalidate all of the nodes that have to be recomputed, and the backend at render time will recompute all of them going from the bottom up. So there's no possibility anymore to have stale values, and it has one other benefit, which is that each backend can register its own nodes that it wants to compute, but they will not be computed for the other backends, right? So where observables go eagerly from the top down, right now we have this lazy structure that updates from the bottom up. So in point 24, we updated all of the plot internals, so functions like lines, scatter, whatever. All of these had been using compute graphs then. In point 25, which is the upcoming breaking release, we have refactored some of the blocks too, which is like an invisible change for users, but it increases the robustness and performance too. But observables are still around, so we often get asked, like, what about my code using observables? You can still use them. It's just that if you encounter the same problems that we did with like the multiple updates and so on, you can refactor to compute graph if you want to. But for a lot of stuff like events, app logic, high-level things, you can still use them fine. There's no problem with that. So speaking of point 25, that's like a huge branch that we've been building on top of with a lot of things that are slightly breaking, but which we really wanted to get done before we tag 1.0 sometime in the near future. So yeah, a lot of this was Frederick's work, but some of these are not really simple to show visually. So for example, the dim convert mechanism, which allows you to plot dates easily or unitful data. This has been improved a lot, so it should work across all plotting functions now, no matter what they do exactly. Then nested attributes are great for building composable plotting pipelines where you make parts that you combine again together, and then if you nest their attributes, it's much easier to keep track of what belongs to what, instead of redefining all of these attributes all over again. Then the data inspector had a lot of rework, so now it's much more robust when you scroll through your data and select points of interest and want to have tooltips that stay there. So this was a bit broken before and is much better now. So the following points, the block recipes, text extensions, mesh stroking, and GUI elements, I have some visual examples for, so we'll go through them quickly. So the block recipes, the main thing whether we were always asked was, how do I add an access title to my recipe? And people are just used to be able to do this from plots, and it was never possible in Marquee, and people really didn't understand why. So I added this graphic here once more to show that if you have your box standard plot, like a scatter lines with an axis and it's in a figure, then the scatter lines plot that is the dashed circle there in the graphic, that's the level of the recipe in Marquee. And it's really something that lives in one scene, and the axis as a whole is like a much bigger object that encompasses a lot of plots and scenes and so on. So there was no way for the recipe to affect the axis really, because it was living on a whole different level. That's why we always said, like, no, you can't do it, just use normal functions. So now we have actually found that we kind of had this structure, like we've always been calling this complex recipes, and we're wondering, like, how can we do it? And in the end, we kind of found we already had the architecture. It was just in need of some refactors. So all of our objects like axis, button, slider, whatever, we'd been calling them blocks, and their ability was to be placed in the Marquee layout and then act like these rectangular objects that all kind of work the same but have different constituent plots. And now this will become like a public mechanism that also works like recipes, where you can then use conversion traits like you did with the plotting functions, which allows you to like hook into all these predefined conversions, right? Like a function over an interval or whatever. This all works immediately. And as you can see in this little initialize block method, which might be called something else later, but that's how it's currently, you can basically plot into this block object as if it was its own little figure, right? Like you have a grid layout available there. You can add axes, other blocks to it, even recursively if you want. Kind of, well, doesn't really make sense, but yeah, you could. And plot inside there, and you can use legends and color bars and all that. And then plot, at the bottom you can see that I'm calling this on 2 arrays, which then goes through the conversion mechanism that I mentioned. So why would you do that over normal functions? Because I've always been saying, like, just use normal functions for your complex plots. So you can use the theming mechanism in Marquee if you do this. You have our internal docstring generating functionality available. So like you'd only document your little attributes and the rest gets generated for you. The conversion mechanism is powerful. Then the spec API means that you can like build these dynamic GUIs or assemblies that change on runtime values and rebuild themselves, and you do less of this manual plumbing. So it opts into that automatically as well. And like adding, deleting stuff, which you often need if you build something dynamic. If you had previously plotted 10 elements, you would be responsible for deleting 10 elements yourself if you did that. And with the blocks, you can just use our normal machinery for that. So yeah, it has a bunch of benefits. Okay, the next thing that I kind of like is this text layout extension thing. So a lot of people ask us, like, how do we make our plots fully look like the LaTeX document that we use them in and so on? And the answer was always, yeah, you can use the fonts, but there might be some mismatch. MathTech engine is not really a LaTeX engine and so on. The problem was always that we had these 3 built-in types, strings, LaTeX strings via MathTech engine, and rich text. That was the only stuff that the text pipeline knew how to handle. And so what's going to be in 0.25 is that you can put any types into the text pipeline and register handlers, basically, which then tell you what to do with that, which allows this other package, MarqueeTech, to actually pass these types into all the normal places, like an access title, a legend, whatever. And you can actually set it up such that it grabs all the normal strings too and puts them through LaTeX. I mean, it's kind of slow, like you wouldn't, it's not a dynamic thing, but I mean, for plots for publication, that doesn't really matter if it takes like 10 seconds or what, because it LaTeXifies every little string. So maybe there's the update potential, the upgrade potential. But yeah, as you can see, like I'm passing like a Feynman diagram in a label, or yeah, it doesn't really matter. You're free to do whatever. So it's really powerful in that way. Then I have mesh stroking PR, which I really want to have for a long time, because we used to draw stroked meshes as a mesh plus a wireframe of lines, and these did like a lot of Z fighting artifacts. you can see that the pole is really messy on the left side, and it's going to be just a shader option in the future, which generates really clean meshes. And Kairomaki will also just get a software version of that shader. So for plots that are mostly vectorizable, but have a little bit of 3D stuff that should look clean, in Kairomaki it will be much easier to do that in the future. And then the last thing is that we have, the last thing I'll show here is that we have a bunch of new GUI elements, basically, which were requested a lot. So for example, on the left, you see like a table kind of widget where you can select rows and columns, whatever, select data that you're interested in. Then in the middle, you can see these 3 tabs. So that was asked a lot. How can I make a user interface that switches between different views? So we changed the scene event system a little bit to support that. You can see switching here. These modals where you can do settings in between that affect the plot and then go away again. And then in the end, there's also like a little saving kind of widget where if you want to save plots or whatever during your interactions, you can easily do that. And with that, I'm passing over to Simon for ray tracing stuff.
Yes. Did we get into this weird not full screen thing? Okay, cool. Yeah, I want to start with a shout out to Renko, who has been paying for quite a bit of open source work in Marquee for me, partly for some of the GUI features, and also for polishing Bonito a bit and making it faster. And they're doing fluid simulations, which are pretty cool, and they're building pretty complex dashboards with Marquee, and I'm helping them to support this. And speaking about GUIs, I had this pet peeve and this dream of making a video editor in Marquee for a really long time. And with a GUI polish, I thought, okay, I really want to try this out, what we can do with Marquee. So, of course, I made a little video editor in Marquee. And the fun part is I didn't spend the most time on the GUI. I spent actually the most time on moving everything through the GPU. So you see all these little filters here, for example, which are running on the GPU. And you're seeing all these kind of new widgets that we've been adding. And this, for example, is a deep neural network for removing the background, which also runs natively in Julia on the GPU. And that allows you to do really fun stuff, like copying a crow and overlaying it. This is really weird how you exit the full screen. So yeah, the DNNs, that was a fun side project. I wanted to try it out to run the whole thing in Julia. We got really close to PyTorch performance, as you can see. And I put the robot on this. We started at very far away from PyTorch, and by porting quite a few kernels, we got pretty close, which is pretty amazing. And yes, surprisingly, there's a lot of stuff you want to do on the GPU for plotting. Obviously, the graphics. But then if you have like doing more of these video use cases, you have a whole effect graph that you want to run on the GPU. Obviously, the neural networks, the ray tracing, which we've been teasering. And I already had a talk about that with a bit more detail. And of course, the whole apps and GUIs should also run there. And then the big thing is also simulations. They usually need GPUs to be fast. And it would be really nice if your fast GPU simulation could be directly fed into the plotting library in real time. I don't have a good it's a bit of a detour here with the ray tracer because, yeah, it's one of the heaviest GPU user for the new ray tracing backend. It needs to be really fast because a slow ray tracer takes half an hour for a single frame. And that's already relatively optimized. And a really fast one can do the same work in 10 seconds. So it's really difficult to get good performance. And we wrote one in Julia. And when I started this, I was like, OK, I'm super happy if we are like 5x of the state of the art on all backends. And it turns out we got actually really close to the state of the art by using a new Vulkan backend that I got nerd-sniped into creating. And of course, we also support AMD GPU, CUDA, and Metal because it's all just Julia functions. This is the first image here. It's a really nice rendering of a cloud created with breeze.jl. And that already shows you what it can do. These are actually the same clouds from a different perspective over geometry I created with Tyler, which is kind of the tiles service for rendering in Marquee. I also made a black hole little use case, which shows off how you can actually create a Julia material for the ray tracer, which you can't do if the ray tracer is written in C++. And there you can really bend the light with your own Julia code. Worked out pretty well. It's of course not physically accurate, but it shows the effect. And then we did a little demo with Trixie particles, which turned into this really nice water render. Yeah, so talking about this new Vulkan backend, it's kind of the dream I've been having for a long time to get this GPU platform where you can actually do compute and graphics in one language and in one framework. It's pretty far, so it passes the GPU array test suite and does everything kernel abstraction can do. So if you have a code that uses kernel abstraction, it will also work on Vulkan now. But on top of this, you have all these new shaders, which are only available in Vulkan, which is like these geometry, vertex, and fragment shaders, which you need for a normal GPU-based graphics pipeline. And then Vulkan is also the only platform that allows you to actually cross-platform access the hardware acceleration for ray tracing, which can be 2 to 3 times faster than implementing your own ray tracing, because it actually uses hardware to do the ray tracing. It's cross-platform, although so it works on every GPU. Although Apple is a bit weird, it goes over Molten VK, which kind of re-implements Vulkan on top of Metal, which also points to the fact that we could actually just plug in Metal directly. And that brings me to another new package, because Vulkan is incredibly complex. It has a really crazy API. The hello triangle in Vulkan is 1,500 lines of code, which just renders a simple triangle. It's super complicated to do all the memory placement and allocations, aliasing barriers, and scheduling. And yeah, but there are simpler APIs, which are usually graph-based. And they're relatively similar to Metal, because Apple was like, OK, Vulkan is a bit too complicated. We want a simpler graphics API. So from Metal, it should be really easy to just say, OK, on Apple, we might as well just use metal.jl to compile our Julia functions. I think we still need to port a few constructs there, but as soon as we've done that, it should be a very easy target to support also the whole graphics and ray tracing and compute on OS X. For everyone else, we will be using Lava. And then I thought, OK, it should be very easy if everything is just a Julia function that we compile on the GPU. We might as well just also have a CUDA and AMD backend in there because there are some super cool libraries in CUDA and for AMD which are super fast and optimized that you might want to use there as well. Then it only becomes interesting how you do the barriers to the graphics pipeline and how you convert it. But the graph can handle that for you. So it could also be a very nice integration for some existing CUDA or AMD code. This is kind of the state of Mantle. Claude Code wrote a little deferred renderer. I'm guessing not everyone knows what deferred rendering is. It's a pretty modern rendering technique for rendering a lot of lights. It's used in a lot of new engines. And the fun thing is with the Mantle API and Julia, the whole deferred rendering pipeline, I mean, it's simplified, obviously, but it's still less than the Hello Triangle and Vulkan. So it's a very nice API to work in, and I'm not sure there are many other high-level languages that can do this. There's some C++ library which can do similar things, but now it's all nice and concise in Julia. And what's next? We want, of course, a new Marquee backend using Mantle. I first wanted to call it Vulkan Marquee, but now that maybe stuff runs on metal behind your back, Vulkan Marquee is not the best name anymore, so we still need to come up with a name, but yeah. We also need to really test on a lot of hardware because writing a new compiler for hardware that runs across lots of platforms gives you quite a bit of a bug surface. I've already been testing on 4 platforms a lot, and on these it's pretty stable. But yeah, when we put it out there, I'm pretty sure we will have a few months of bug finding. And the cool thing is Ray Marquee, of course, will be working with Mantle, and that means you can really easily then switch on ray tracing in the new Mantle Marquee or VK Marquee backend. And it should be really easy to switch between those. So imagine GL Marquee, but you can just turn on ray tracing and suddenly it looks super cool. And with the flexibility of Mantle, it will be also easier to experiment with new rendering techniques. So I'm pretty sure the real-time preview rendering will also look a lot nicer going forward. And finally, Vulkan is actually on a relatively similar stack to WebGPU. So it's somewhat easy to compile from Vulkan to also WebGPU. It has quite a bit less capabilities compared to Vulkan. But I hope with some smart high-level abstractions, we can actually reuse all our Vulkan Marquee shaders also on the web. And then it just becomes about having a new WebGPU backend, which kind of transfers everything to JavaScript, and then we can just upload our shaders that we already have. And that could also include compute shaders, because you do have some compute shader support in WebGPU. So you might even at some point be able to be like, OK, I have this Julia simulation running on the GPU. And now it runs natively in the browser and is natively visualized in Marquee. So that's kind of a stretch goal for the next 2 years or so. And then I have also pretty good news. We got an investment from the Sovereign Tech Agency. It will feed us for the next 1.5 years on a half-time basis or something like that, and will also pay Frederick. So we will be working a lot on this. This is not like the last times where it was like, OK, we want all these cool features, and then nobody paid for it, and it didn't happen. So I'm pretty confident that we will do a lot of this work going forward. Yeah. Thank you, everyone. I'm always really happy if anyone reaches out, talks to us. So just write us. You can also find our LinkedIn and GitHubs here. And yeah, thank you.
Okay, yeah. We have plenty of time for questions. Next speaker should probably start getting set up soonish, but
Thanks, guys. This looks really amazing on all fronts. I'm particularly excited about the dashboard stuff and the interactive stuff. And I'm curious, almost all of the time I'm developing on a laptop I'm SSH'd into a server. And so I'm wondering how well that's going to work. I know like that has always seemed to be like a little bit of a trick. I've now got like terminal plotting for Kairomaki going, but having some kind of communication over SSH for doing interactive stuff would be really amazing. I kind of got it working with WGLMakey, but it's still tough.
Yeah, so that's a bit of a blind spot so far because I'm not really used to that workflow as much. I've been recommending to use just WebGL-Marquee for this. I actually also have a prototype for a remote GL-Marquee because we have all the infrastructure for WebGL-Marquee to just communicate all the graphics to the browser, right? And you might as well actually use this transport layer to communicate over an SSH connection and then just render it in GL-Marquee super fast on your client. So I'm not sure if I will ever have time for this, but it's there, and maybe Claude Code or whoever will pick it up. So it's definitely possible. I got plots to run with it, and but it's a bit of a mess. So maybe it will be out sometime.
Really excited to be using Vulkan for compute from Julia. I had one question. Were you able to compare with what the Mesa people are doing with Rustical? Because you can call that from OpenCL.jl. I imagine there's a bit more overhead than with your approach, but were you able to compare those two?
I think, I mean, it's kind of, there's this split between more OpenCL-like workloads, which are also a subset of Vulkan. Not a subset. I mean, there are two sets. There's like OpenCL, Vulkan, in a way, which uses SPIR-V, the intermediate representation for compiling the shaders. And then there's like the one for graphics, and they're sadly not combined. And initially, they were supposed to be the same thing, but the graphics vendors didn't like that, so they cut it. So Vulkan Compute has a lot less capabilities than the OpenCL variant, but it's surprisingly complete at this point. So I'm not sure if that answers the question, but we haven't been directly comparing to the Rust stuff, but because it's a bit hard to transfer it to the graphics stuff.
Hi, here. Over here. Can you comment on the spec API? Like, what is the state? How is it intended to be used?
Oh, yeah. The spec API has been sitting there quite a while, and I think it's in for a little cleanup. And I think it's, we have a lot of maintenance hours from the Sovereign Tech Agency. And I think we will definitely put some of those maintenance hours into improving the spec API, because it's definitely a core feature, and it will only improve from here on.
So just a question here. This might just be a user skill issue problem, but I'm often finding that when I call plot functions, I mess up my arguments. Would you ever be able to or willing to implement a way to know all possible combinations that are valid for a plotting function?
I'm not sure I completely got the question. Like, mess up your arguments how?
So the combination of arguments are not valid. Like if I, for example, give an interval and a function, sometimes it works, sometimes it doesn't, stuff like this. If, for example, you use volume, you just can give a 3D array, right? It works. But if I also give different description for how the limits should be given, it doesn't work. Again, it might be skill issues, but just a quality of life question.
I think we try to improve the docs around this, or Frederick did some work on this as well, to reorganize the doc strings. Sometimes it's a little difficult to fully automate this, as if there are 100 conversion methods and you splice them all into the doc string, then it's just a mess. I mean, we were striving for a system where it's kind of intuitive what you can pass, but we seem to find again and again that everybody's intuition differs a lot. And it's like, why can't I use a tuple for an interval, or why can't I use, I don't know, like, it's a hard thing to decide which thing to support and which you don't, because otherwise you just like have so many conversion methods that it gets kind of crazy.
Yeah, and we will definitely put some time into better error messages. I'm really annoyed by the Marquee error messages since our compute pipeline refactor. It's they regress a lot and they need to become nice again.
Great. Let's give our speakers another round of applause. And our next speaker is Ashutosh, who's talking about the Dyad Agent Bench, which is an evaluation framework for Dyad.
Hi, everyone. So we'll be discussing the Dyad Agent Bench, which is an infrastructure that quantifies how well we are doing on the Dyad agent. If you have attended the workshop, you might have got your hands on the agent, and what Dyad Agent Bench does is it provides you an infrastructure and a workflow to run evals. Now, what do we need evals for? So an eval is a repeatable performance suite for AI systems. So basically, if you there must be a way to for me to say quantifiably that I am doing better than the previous iteration of the agent. Uh, so uh, so yeah, when do we need an eval? So there are multiple scenarios, but the two important scenarios is when you iterate towards a shippable feature. So you need to measure if your feature has improved the agent, or we have regressed in that sense. And second is comparing LLM providers. So the iterations with the basically, if you want to compare, let's say Opus 4.8 with the Opus 5, it's not necessary that Opus 5 will be better just because it's a newer model. You have to measure the performance, and you have to reason about it. So there's two ways to judge an agent. One is the deterministic way, and one is the non-deterministic way. So deterministic ways usually are mechanical checks. So you have, for example, you can measure how much did it cost you, or how many calls did the agent make. And the non-deterministic part is the LLM as a judge. So deterministic is basically quantitative assessment of how the agent did. The score would be similar if the result is reached. Like if two separate LLMs or two separate agents reach to a similar result, the scores would be same. However, in non-deterministic scenario, it might not be the case, because there we might run LLM as a judge. And in that case, you qualitatively measure how the agent did. So it might be possible that the first agent took a longer route to reach the same conclusion, which the second agent did in a shorter time. So in that case, we are qualitatively measuring how the agent performed. So here's how the AI system development cycle works. So you define a task and you define a grader for it. So a task would be, hey, I want to do I want my agent to be good at something. Now grader is what defines what good means, right? You have to assign a score for it. Again, it can be deterministic, it can be non-deterministic. Then you take this task and grader and run it in a sealed environment. Uh, you have to make sure that the agent has no access or knowledge that it is going to be graded, or in fact the access to the grader, because a lot of times the agent tends to cheat on the task if it knows that it's going to be graded afterwards. And the third, and this is where the diet agent bench is important, is okay, once you have run the task, once you have run the grader, it is important to explain the behavior. So you log and capture how your agent did throughout the run. For example, I asked it to work on some task. Now I have captured all the things that the agent has done during that run, and then I have to explain, reason, or diagnose what the behavior was actually. If an agent has reached a certain result, there must be some reason behind it. If it has failed, there must be some reason. If it has passed, there must be some reason. So, yeah. Then you take those insights. For example, there's a failure. Now you have all the insights on why, hey, why my agent was failing. Now you take those insights, you go back, you iterate on your agent, and then you come back to your task again. You run it again and again until you're satisfied with the result. So this is what the diet agent bench provides. Diet agent bench provides a contract for you for writing the task and the grader. You can write multiple tasks and it scales horizontally. Second thing it provides is a secure and isolated execution. Like I said, the agent while running should have no idea of that it's being graded or it's going to be graded. So you have to manage the permissions. You have to manage everything such that the agent has no access to the code that is going to grade it. And logging and diagnosis. So once you have logged, and you need explanation about how the agent performed. Now, this is a case study about a problem where we asked the agent to build a race car. We provided certain components pre-built in Diad, and we asked it to assemble the race car and write a controller write a driver controller for it. And so the goal of this problem is probably the second scenario that I discussed, which is we are comparing it across multiple LLMs. So if I go to the infra, you can see here are the multiple attempts listed by how the per LLM. Let me click on one of these. So this is what Chimic A3 did. Notice it has 221 tool calls. We get a diagnosis of how each tool call went. We have access to the whole transcript. But oh, there we go. Is it fine now? Yeah, sorry. Yeah, so like you can see, there are multiple attempts listed by the LLM that has tried to solve this task. We have a score written for it. I'll come to the score and key insights later. But what I was trying to show was this. If I go to one of the trials, there are 221 tool calls. And then I can see which tool call failed and what was the total time of each tool call. This is the diagnosis part. And then I could individually go into the transcript and look how this model performed. But as you can see, the transcript is really huge. So what usually we do is we start agent, we select, and we hit compare. So it runs. And when it's finished running, let me. Yeah. So when it's finished running, it gives you a detailed report on how each attempt did. When I say attempt, it means some LLM took a crack at the race car problem, where it was given some race car components and it had to assemble those, and it had to write the controller for it, and we simulate it on multiple testing tracks that the agent does not do, that the agent doesn't know, and so it produces a report for us. This is all right. So as you can see, for this particular eval, Claude Fable 5 wins, Kimi K3 comes second, and Claude Opus 4.8 comes third. So the key insights are, and probably the insight number 2 is one of my favorites, since I'm running low on time. So design over brute force. So what Kimi K3 did was, I showed you 221 tool calls, right? Fable does it in 17 minutes, and it does not require that much, because Kimi K3 literally started a grid search on which parameters it needs to tune the controller on. So its approach was pretty much brute force. So if you see, Fable has almost the least number of Julia evals as compared to Kimi K3, which has the highest. And there's Insight 4. The best car was also the most expensive to build. Like you can see, Fable, in terms of cost, stands towards the right side of the plot, and the Kimi, that is the second one, is towards the, I'd say, mid of the plot. You can actually watch them race. So you can actually go to this site. You can go to a track. You can watch them race. So these are real simulations from the race. I'll share the slide with you. Yeah, you can scan the QR code. You can go to the site, and you can. There are 8 tracks on which these agents were tested. You can actually go and watch the race itself. Yeah. Yeah, that brings us to the end of it. It's not all of the infrastructure is built by the Diet AI team. There are other people part of it too. So yeah, questions?
Great. Next speaker should start getting set up, and we have time for 1 or 2 questions. Okay.
All right.
No questions.
Thank you.
I'd wait a minute just in case anyone's coming.
Okay. Hello, everyone. I'm Rajiv Voletti. I'm on the DIA team. What I'm going to be talking about today is pretty much a bread and butter workflow in GNC, which is you start with a nonlinear equation-based model of an airplane, which in our case is going to be the F-16. And we're going to linearize we're going to find a trim point, linearize, design an LQR controller, and then explore some of the options that our synchronous toolkit gives us in terms of code gen. So I'm going to skip on a little bit of the stuff about dyad, but the key idea here is to demonstrate the workflow with one dyad model. The entire workflow can be done using that one specific model for a simulation analysis in continuous time, continuous discrete hybrid simulations, demonstrate SciML capabilities like surrogates, and finally deploy an FMU or generate C code for a specific controller that we're synthesizing. So today, the plant model is a nonlinear 6-degree of freedom model of the famously statically unstable F-16. So statically stable implies that in the absence of an active control, an airplane would just stably glide to safety. But for something agile, requiring capabilities to engage in dogfights or artillery, we would want the airplane to be unstable. So it's much more maneuverable. But this also means that the control scheme must be more robust. So we have position, attitude, velocity, heading, side slip, and their rates as the states, and the 5 controls. So the thrust, elevator, aileron, rudder, and leading edge flaps, which are auto-scheduled and not pilot-commanded in this specific case, are utilized in the plant model. So for this workflow, we only assume longitudinal motion, which is longitudinal, and no lateral. So pretty much the plant model is, the first step in the workflow is to calculate trim, which what we essentially mean by trim here is that we find a set of control inputs such that the plane maintains an altitude of 3,000 meters and a speed of 500 feet per second, or 152.4 meter per second. We define what we don't know here in our dyad model as missing. So the model on the right is just illustrative. You can define this within the plant itself. And when you do that and just run a steady state problem at 0.0, it solves an initial value problem, giving us a trim point that can be exported. So if you've worked in GNC a lot, there's a lot of wrestling involved in terms of setting up the nonlinear least squares problem in order to even get the trim point. Dyad just makes this one simple initialization call. So LQR control design does not work on the nonlinear plant directly. So near trim point, the tangent is an excellent approximation. And that tangent is a linear state space model. So this is the goal of linearization, which is to find a local approximation of our nonlinear plant around the trim point that we just calculated. We approach this problem by using these constructs called analysis points. An analysis point names a signal edge, and analyses inject, measure, or sort of cut the loop there without modifying the physics. So that way, your closed loop model can remain undisturbed while you extract specific subsystems to do your analyses on. So here's what the named points buy you in the actual design model. An analysis can take any slice of this diagram, and the model itself doesn't need to change. Nothing is duplicated. Nothing is forked into an analysis-only variant. With these specific analysis points, this is, again, also illustrative. You don't really have to blow it up. But all you have to do is define analysis points for your inputs and your outputs, and your closed-loop model stays undisturbed. So small introduction to LQR here. It stands for Linear Quadratic Regulator. LQR is an optimizer and not a tuning exercise. You hand it a linear model, matrix Q, saying how much each state error bothers you. a matrix R saying how much each actuator costs to move. It returns the one feedback gain that minimizes that cost, so which is obtained by solving the Riccati equation, which is stabilizing by its construction. So the animation explains the effect of changing R, which is our control cost. So if control is deemed too expensive, that is weighted a lot higher, you will see more conservative control action. And conversely, if it's cheap, then you will see a lot more control activity in order to stabilize the F16 plant model. So this is a representation of the closed loop system. The gain L is obtained from our specific LQG analysis. We assume full state feedback. We don't assume noise for now, although we're working on it. So the gain is valid and useful around a certain envelope around the trim point. Now, using dyad synchronous features, we can express the whole LQR loop as a hybrid model with a continuous time plant model and a discrete time state space controller. So the dotted lines represent a connection that is on a discrete clock. And the little clock icons represent the rate of the input and output connections of the block. We convert the continuous signal to discrete using a sample block. The sampled discrete signal is fed to the discrete time controller, which links to a zero-order hold to move things back into the continuous time domain. And the clock you see at the bottom propagates the information about the rates or the sampling time to all of the discrete blocks. Each discrete block, intuitively, can only be on one clock. And this information is inferred and propagated using that clocked connection that you see at the bottom. So when control systems do what they're supposed to do, they look kind of mundane. So I've initialized the F16 at a 10-degree offset from trim, which is far beyond the linear envelope assumption. But the LQR stabilizes the plane, and we see the discretized zero-order hold output of the elevator command. So the airframe is rendered using our multi-bodies shapefile visualizer tool and is a direct output of one of the models. And some cool things you can do with the AI agent is you can give it a design, like this cool-looking slide, and it wires things into the model to see the effect of choosing the cost of the elevator to the control characteristics of the model, which I think is pretty cool. Another artifact of using analysis points is we can compile to standalone C for the specific subsection of our discretized state space controller. And yeah, this is useful in sort of deploying your controllers onto embedded platforms. So this was a very quick overview or a speed run through how you use one closed loop model to go through a typical GNC workflow of trimming, linearizing, finding an optimal controller, running it in closed loop, discretizing that controller, and then possibly deploying it. So yeah, this repository will be available for anybody to play with, and I can provide that info for whoever needs it. Thank you.
We have a good amount of time for questions, so if anyone has any questions, we have about 6 minutes for them. And yeah, our next speaker should start getting set up if they haven't already.
Hey, Rajiv, how would you handle that problem if you needed to do that controller over the entire flight envelope? Is it possible to do multiple linearizations, multiple controls, and move between those as you fly, or is that?
That is actually the realistic solution of the problem. So whenever you're designing a flight controller, you want an envelope. You create a grid of linearization points, and that grid is valid around like the local envelope or where the sort of state lies. And based on where that state is, you decide which LQR controller you are going to sort of provision for that specific situation. And yes, that is very much possible. And the next iteration of this will probably scale to like about 10,000 linearization points and sort of have an LQR envelope that sort of moves from one to the other as the sort of plane is transitioning.
Okay, let's give our speaker another round of applause.
Okay, excellent. Sorry about that. Yeah, that computer worked in the other room, so apparently this one is not happy. So thanks for sticking with us. I'm going to give an overview of some work we're doing on data center system modeling with Dyad. My name is John Batey. I'm Director of Modeling and Simulation at JuliaHub. So what is a data center? I'm sure everyone knows about data centers. You may have different opinions about data centers personally, but what's inside of a data center? Why do we care about them from a system modeling standpoint? And since we're talking about data centers, we might as well ask AI to make all our images. So yeah, keep them busy. So inside a data center, there's really a couple of many critical systems. One is the power side. Where is the power coming from, right? The objective is you need power to deliver to your GPUs, CPUs, servers to do the compute. So that power can come from the grid. It could come from local power if you're generating your own. And there's a whole bunch of equipment starting from generation to distribution, regulators, transformers, switches, battery backups, system stabilizers, all the way up to the machines themselves. The machines themselves are responsible for doing the compute, but all the compute that we do results in heat. And that heat has to be managed. It's a substantial part of the energy in data centers. There's different ways of managing the cooling, and we'll talk about some of those. That cooling is obviously required and obviously a pretty large power consumer as well. And there's all the other ancillary parts of networking and all that, which I'm not going to talk about today. So we're going to focus a bit on the power flow, and that's sort of what I just described. We start from the grid, go all the way through various systems, switch gears, substations, UPS, batteries, potentially backup generators or actual generators if you're making your own power, all the way down to the PDU and the busways that actually powers the server. The server does the compute. That's what you're getting paid for if you operate a data center, is that compute. And inside the server hall, the IT load, that is your compute, and what comes out is heat. And that heat has to be managed. That could be air cooling, liquid cooling. We'll talk about a couple of different ways to do that, and some of the equipment that does so, and ultimately you end up rejecting that heat to the atmosphere. So this is the power flow inside the data center, and this is what we're going to try to model on the Dyad side. Why do we care about this for data centers? We obviously want to optimize their performance, and I'll describe why you might want to do that. It's pretty obvious, right? You have capacity, you have cost savings depending on your power level. We want to optimize energy, right? Even though it's a data center, right? We want to be the best data center possible in terms of the compute. So how do we get optimal compute for the lowest amount of energy? We also want to mitigate risk and improve reliability, right? Downtime is lost revenue for a data center. So if we can do things on the modeling side to look at maintenance, predictive maintenance, look at what-if scenarios to mitigate risk and improve reliability. Ultimately, we have to manage all that heat, so we can look at the design of the thermal management system, the airflow, and also look at some architecture exploration. So what happens if we switch to the next hardware? Is our cooling infrastructure sufficient? Do we need to upgrade? Do we need larger fans? Do we need to switch to liquid cooling? These are all the things that are relevant questions for operators of data centers. So let's start with the electrical system. So we are looking to model the electrical power from power generation all the way to the chip. We did this using a library called OpenIPSL in Dyad. It's actually a Modelica library that's been implemented over many years by Professor Luigi Vanfredi and his students. We translated that library from Modelica to Dyad, not all of it, but a substantial part of it. And if you're interested in that work, there's a paper at the upcoming American Modelica conference regarding that work. But OpenIPSL is one of those tools that, if you look at this graph here, it tries to show different timescales and what timescales are important in electrical systems, and also where OpenIPSL operates. OpenIPSL uses phasor time domain simulation, so it's good for time scales like this one, which are roughly the kind of transients that we're interested in our system. So what did we do on the electrical side? So we needed a large number of components from OpenIPSL, so grid, transformers, generators with controls, the buses, switches, lines, loads, events, faults. You see a couple of models there. The one in the middle is actually one of the implementations of the turbine generator in OpenIPSL. And if you look at the Modelica model and you look at the dyad model, they're basically the same, although we did add some pieces in here to simulate turbine faults, and I'll show you that in a minute. And then once you have all these components in dyad, you can go ahead and graphically build your system. This is system with multiple generators, 2 generators, a grid, transformers, multiple feed lines, and also this is a representation of the fault. And then you get down here, another transformer, and then the loads. So why do we care to do this? Multiple reasons. One, we want to be able to look at efficiency all the way through the system, right? So if we're going to go from chip to power, we need to get the efficiency of the system to know how much power we need to generate. That's one aspect. The other aspect is really looking more at the dynamics and the transient scenarios. So for example, what happens if you have multiple turbines and one of them fails, right? Will you lose frequency to the grid, or lose frequency on your lines? Will you trip relays? Will you have to shed load? These are all relevant questions. The simulation you see on the left is one where the load is being met by 6 generators. One of them trips, and actually you don't see anything happen. The other 5 absorb the load, and the generator stays connected in the system. The one on the simulation that you see on the right is the one where only 5 generators are carrying that same load. Now one of the turbines trips. It's more of a disturbance to the system. You see that the load shedding occurs, and you see relays trip, and then the turbine that tripped is disconnected from the system. So these are the kind of simulations that we can do with the OpenIPSL library in dyad. That was looking at the load kind of from a high-level standpoint, but if we're talking about data centers, we want to look at the load as an IT load. So something where we can say, what is the electrical power draw based on these particular GPU characteristics, this particular rack setup? So that gives us the connection between the GPU and the loads. And now we can start to play games like change the parameterization. What happens if you go to a high power mode or low power mode on the GPU? So these, I know that sitting in the audience, the dark background is not friendly in this very bright room. I apologize for that. So I'm sure some of these things that are on dark backgrounds are not super visible. But what you see there is kind of the parameterization of the model, like number of racks, the power of the GPU in idle mode, max power, if there's fixed power, how much the compute changes based on its activity, what are some of the efficiencies. And ultimately what this gives us is a utilization input, so it's a normalized signal from 0 to 1. 0 is idle, 1 is max compute, and from that we get compute metrics. That's going to be important later, but we also get the power draw. So then with information like that, you can sort of put together a model of a data hall at kind of whatever granularity you want. This is a model where we have sort of 3 different units. Those can be multiple GPUs, multiple racks. It's supposed to be a scalable model. They can have different characterization of the GPUs, different setups, different utilization inputs. And what you see on those graphs are basically the fluctuating utilization on those 3 entities, how much power they draw, and then the total power for the system. This is on like a 600-second time scale, so these are not, this was just to put everything kind of on one time grid. So once we've connected power to GPU compute, now we can start to assemble a full system model. And that's what you see here. This is a dyad model for the data center, thermal system operation and control. And I'll walk you through the parts. So this is the data hall itself. This is where the compute happens. There's two liquid loops here. This is the chilled water loop through the data center. And then the loop that you see here, so here is the chiller. The loop that you see here is the condenser water loop, so out of the chiller to the cooling tower and back. So, so here we have representations of the chiller, cooling tower, could be many, multiple chillers, multiple cooling towers, those two water loops, and then what's inside the data center, I'll show you in a minute. This is the controller, I'll also show you that in a minute. That's driven by these GPU load profiles, and then you provide some ambient conditions for the cooling tower. So what's inside the data hall? So this is where we get to the level of detail where we look at what exactly is the cooling approach of the data center of interest. So what you see here is a scalable model for a thermal system with air cooling. So this is scalable. You can change the number of racks, GPUs, number of C-rack units. That's the unit that goes between the cooling water and the air that actually cools the GPUs. So the water comes in here, goes here, and goes out. So cold in, hot out. And then the air loop is internal here. So it gets cooled here, gets distributed to the GPUs via fans, all comes together, goes back to this unit for more cooling. So you've got a water loop, which also connects to the outside, controlled fans, the GPU, which also has a dynamic thermal model underneath. And this is a kind of a pictorial representation. There's many different ways of routing the cooling inside data centers, but one typical route is the cold air goes under the floor, goes up through the racks, out the top, and then gets routed back. So that's what you see happening here. And you have these cold aisles and hot aisles, and you try to keep them separate, right? So you don't mix the air and take cold air and get it contaminated with hot air that's already gone through the racks. So you try to keep them as separate as possible. So we have representations of that on the thermal side. And then we have a representation of the whole controls, right? And you can't run these systems without some level of controls. So the key controls are what's the set point for the chilled water temperature? What is the flow rate of that? Is the chiller on or off? Is the cooling tower on or off? What's the fan speed? What's the condenser water flow rate? And then what load are you trying to run the chiller at? So this is all that logic is underneath this component, and you see this is just the icon that's represented in the system. So now let's go on to a daily simulation. So we want models that are fast running. We want to simulate over long time horizons, a full day, a month, a year. We want to be able to do optimizations with these models as well. So the inputs that you see below are just a single day showing different kinds of GPU utilization profiles, 3 different ones. So one in zone 1 in the blue represents AI or ML training. So you see some fluctuating up and down. You also have an inference load, which kind of starts off low, goes up in the middle of the day when people are working, and then also tails off towards the end of the day. And then the green is just some HPC batch stuff, right? You can make up your own utilization profiles, ultimately, whatever you actually need to compute. And then what you see on the bottom is a synthetic temperature profile. So this is nighttime, temperatures are low, temperatures increase during the day, and then cool off again, right? And you use real weather data. These are just synthetic profiles. So when you do that, you get all kinds of plots, and I'm not going to go through all of them, but you can get plots of the GPU temperatures, the air temperatures in the data hall, the condenser water temperatures, and you see all the bands of stuff that you can't really distinguish. It's because those GPUs are going on and off, and I'll show you how you can see that in a minute in more detail. So that's why there's so much fluctuation here. The coefficient of performance of the chiller, this is how efficient the chiller is operating, the different flow rates. So this is our goal, right, is to be able to simulate this whole system, understand how it's operating, and then be able to do things with it, right? So in this particular case, you see the controller responding to load changes, and the ambient temperature tries to increase the chilled water set point, get it as hot as possible because that improves efficiency. And then when the loads pick up, then you have to drop that temperature to manage the cooling. This is not a video that's going to play now because it's not on my computer, but this was supposed to show you that those same plots, but kind of with a moving graph, so you could actually see some of some of the details. So that's unfortunate. So I apologize for that. But now let's talk about other kinds of cooling, right? So the chip power densities that we're seeing now already require liquid cooling. But if we want to go even further, and which is happening, now we have to move into the realm of two-phase liquid cooling. So you can sort of think of two-phase liquid cooling as the difference between, say, taking a cold bath, right? You take a cold bath or a shower, water's cold, it heats up, you have to manage it. In two-phase liquid cooling, it's kind of like sweating, right? So that's a very efficient way to cool. You use the latent heat of vaporization, and the temperatures that you have to manage on the cooling side are not as high. So I'll show you a model for that in a second, but basically what you do is you take in liquid here, the GPU actually heats it up and vaporizes it. It leaves partially vaporized, goes to a condenser where it cools down to liquid because you want it to be liquid to pump. Then you have some kind of reservoir, and then you pump that back to the GPU, and that's your cycle. So we can handle that as well. This is a model of a GPU with two-phase liquid cooling. This has a GPU dynamic thermal model. It has a cold plate with two-phase liquid cooling underneath and a controller for the coolant flow. So what you see in this simulation is the utilization profile going up and down as a function of time. What you see here is the temperatures of the various parts of the system that are part of the thermal model. So the GPU temperature is actually this red one, and then there's other thermal nodes that are part of the GPU. They go up and down with the load. This is what we're actually trying to control, the exit vapor quality, so how much we've vaporized the incoming liquid. And you can see there's disturbances as the load changes, and then they recover as the controller changes the flow rate. So we can handle all the different elements of the thermal systems. And this is, we need to be able to do this because each one of these thermal systems, each one of these different ways of cooling takes different amounts of energy, and that's all part of the story for the data center. So that's great. Why do you build these models? Who cares, right? We want to target these models not just for design, but also for operational impact. Data centers are huge, big business, right? And the decisions you make have both short and long-term impacts. So if you operate a data center, you want to maximize your revenue, maximize your efficiency, lower your costs as much as possible. If you're making your own power, whether that's natural gas or you're buying electricity, right, to do all this power generation and cooling, that costs you money. You need to be robust in operation, right, because your ability to win and serve workloads is a function of your uptime. You want to manage your capital expenditure, and there's a lot of issues with sustainability and regulatory exposure and reputations. So what can we do, right? Can we help manage the IT loads and the total power required to do it? By modeling, right? Modeling the power capacity, modeling the cooling, modeling the environment, modeling the thermal limits, the power draw, looking at the actual job profiles, looking at how you schedule those jobs, and even economics. So that's our goal with what we call a digital twin now. So now it's meant to be something that's actually tied to the data. I was going to show you that on that machine, which unfortunately I won't. There's a picture of it here, but I was going to show it running as an app on that machine. If anyone's interested, I'm happy to show you later. But what this allows us to do is look at the workload, tune set points dynamically based on what we see happening, simulate lots of scenarios to try to find the best way to operate, and then dispatch that. That could be changing the compute, changing the controller set points, changing the cooling, right? With different goals in mind. That could be goals of maximizing efficiency. It could be goals of maximizing revenue. You decide, right? That's what we want to be able to provide. So what is the available compute at the current time? What kind of jobs are being scheduled now and in the future? Do I have flexibility in scheduling those jobs? Do all the jobs have the same economic impact, or some have priority? What's my available power and cooling? What happens if I change the set points? Will I be able to maintain the appropriate thermal operation in the data center? How does that respond dynamically? Are my choices now operationally robust to future environmental conditions? If I know it's going to be hotter later in the day, does that change what I decide to do right now? Do I leave enough space for jobs to come in? Maybe they're high priority jobs that come in later in the day and I want to leave space to do that. How much space do I have based on the environmental conditions? What happens if the power capacity changes? What if someone takes down a turbine for maintenance? How does that impact my operation? And how should I dispatch the compute to the available racks? What are the local temperatures? Will the local power draws trip our logic circuits? So I showed you kind of each of those pieces in isolation. What I was hoping to do is show you the actual digital twin, but at least a mock-up of it, because it's not connected to a real data center in the current state operating, but it kind of looks like those things that you see on the slides. Those are screenshots from the digital twin. So what that digital twin does is you set a particular power capacity. Jobs come in. There's actually an optimization scheduler underneath. They get scheduled at every 15-minute intervals. They're thermally aware. They're aware of the environmental conditions. You can see jobs come in, get scheduled. If the day's hot or the power capacity is low, you'll see you miss a bunch of jobs because you can't actually schedule them during the day. So you'll see jobs kind of pile up and never get executed. And then you get all the operational characteristics of the data center. How much power was drawn? What is the PUE, the power utilization efficiency? How much of my total power is dedicated to cooling? How much compute did I do? These are all of the things that we can answer with these models and in sort of this digital twin format where it's all kind of distilled into this operation. This digital twin allows you to change set points on the controllers. It allows you to pick different locations of the world. It pulls in real weather data. It tries to look ahead and predict what the weather is, and then it corrects itself as it goes along. So it kind of has a bunch of cool stuff. I'm sorry that it's on a computer that apparently does not want to display but did yesterday, but I'll happily show it to anybody that's interested. In addition to the digital twin itself, this digital twin actually operates in conjunction with our AI agent, so you can actually use natural language to interface with the digital twin. So you can do things like, can you find days in my locations that are going to be the worst, or that will show the impact of ambient conditions on the available compute budget. So you can actually interact with the digital twin from the AI agent. And the goal is that the AI agent also will look at the results and then start to help you understand what's happening and actually operate more efficiently. We're not at the point where we're changing anything on the actual hardware, right? These are all informational things. So now data centers are upon us. They're extremely fertile ground for model-based systems engineering. Hopefully I convinced you that on the dyad side, we can support multi-domain system models to do architecture exploration, component sizing, controls development, and look at the impact of environment. And the digital twin space is very interesting, depending on what you want to do in terms of optimization or cost savings. But these models feed from dyad to Julia into web apps to create these digital twins. So yeah, thank you for sticking with us as we tried to find a machine that worked. I will work on that one for the next one. Hopefully we can get it. But yeah, I'm happy to take any questions that anyone has.
Great. Okay, question right here.
So how flexible is the modeling in terms of adding new components, or which you also need new models for, I guess?
Yep.
And to explore how could this, if you see it as a whole energy system, the entire data center, including the cooling, including the power, then there are a lot of options that you all could explore. But this is usually in a planning phase before anything gets actually built. And this digital twin, this is more on the operational side when it's all finalized and you know what you have, so to speak. So is this modeling good for both, or is this really more focused on the digital twin side?
Yeah, it really, that's a great question. And I would say it's good for both. Even the digital twin itself gives you some of that exploration stuff because we do propagate through the digital twin information about the GPUs as well. So you can start to say, well, what happens if I switch to Vera Rubins and they have this power profile and things like that. But yeah, certainly on the modeling side, like what you see here is where you would tend to do a lot of the architectural exploration, right? Do I need multiple chillers? How do I dispatch them? What happens if my cooling tower is different? What happens if my thermal architecture under the hull is different? So yeah, you would swap in, you would build different systems to be able to swap in components. What you see here, and I didn't really kind of cover it, is that we have an efficient library for handling incompressible fluid flow. So all of these components that kind of have this orangish color are actually components that we provide as part of our library. And then you can obviously use them, build your own, change them underneath, create new assemblies, and build from them. So there's nothing that you see here that you can't see underneath or build if you want to do something different. And even underneath the data hall, these are also built with those same components. But yeah, you can make anything, make your own components. That's the goal. What we try to provide you with some, but yeah, the environment is flexible and you're on equal footing with us in terms of implementing your own components.
Okay, if there aren't any other questions, I think it's time for lunch.
Sorry. Yeah, so this is good. So our first speaker is John Batte. He's the director of modeling and simulation at Julia Hub and has over 25 years of experience in the field. He's going to be talking about practical perspectives on the use of AI agents in engineering system simulation. So let's welcome our speaker.
Thanks, Dario. I appreciate it. Yeah, so my name is John Batte. I'm going to take you through a little bit of my usage of AI for the first time. So just some background, just so you can kind of understand where things are coming from. I've worked in system simulation for over 25 years in different engineering domains. I'm kind of old, so I've used languages like Fortran, MATLAB, Python, worked for many years in the Modelica community. Tools like Simulink, AimSim, Daimler, other Modelica tools, but absolutely no usage of LLMs or AI for engineering work prior to joining Julia Hub in 2025. And so I was exposed to some of these workflows starting late last year, and I kind of wanted to give you some perspective. So am I unusual in the engineering space? Oh, goodness, that looks crazy now that we converted it. No. From the engineering side, there is a significant lag in adoption of AI technology. You can see this is, some of you may have seen this in previous talks. This was a study done by Anthropic looking at AI potential and AI adoption in different fields. So if you go over to the architecture and engineering space, you see potential for AI quite large, 83%. Compared to software, where adoption is already maybe in the 40% range, if not higher. You come down here and you see AI in engineering at 4%. And like my colleague Mike Tiller, when we showed this slide on Monday, we're kind of online with grounds maintenance in the current state. So clearly, lots of opportunities. So what are the challenges, right? There are really great agentic coding tools that are out there now. They're not built necessarily for physical modeling, but they're absolutely wonderful at generating code. On the other hand, you have lots of legacy simulation tools, which have been trusted for many years in engineering space. Traditionally, those tools are built for desktop usage, no agentic capability in them, but accurate physics and tools that are trusted in the industry. So how do we bring those two together? I'm going to show you my journey a little bit in this talk. It's a little bit indulgent, but I hope it's useful for others on the that are similar to me. And I think there are a lot in the engineering space. The Julia community is different, right? This is a lot of software developers, and there's a lot more scientific computing and usage of these technologies. But in engineering, you go to lots of companies, and you'll find a lot of people like me that have not been exposed. So this is going to be my experience using the Dyad AI agent. So everything that I'm going to show you in the next slides is with the Dyad AI agent, but I'm not going to focus on Dyad AI agent versus all the other ones. Just wanted to show you some workflows. So we'll show some specific prompts, outputs, give some commentary on some of the things, and hopefully they were of interest to me the first time I tried them, and I hope they'll be interesting for you and maybe give you some ideas to try. It's a little bit dangerous to do this talk. This world is evolving rapidly. I tried, as I was going through and using some of our tools, to kind of capture things along the way, and I realized even the stuff that I had captured at the beginning after committing to do this talk was A, no longer interesting, B, out of date relative to our tools. So this space is evolving rapidly. I'm sure this won't age well. Things that don't work now might work in 6 months, might work in 6 weeks. But anyway, let's go on with it and see what we can do. So one of the very first things, let's start simple, right? Help me understand. We get lots of code, right? In different libraries, different things that we get. First thing, look at this library and help me understand it. Let the agent do the work, right? Go through, look at all the libraries. These are the components. This is the organization. This is the way, these are some of the assumptions in this library. Agent's awesome at that, right? And now, yeah, I want to push that work to the agent, right? I don't want to have to write an email to my colleague like, I built this model for you. It does this and that. You should do this and that. Here's the interface. Just like, agent, document it. What does this have? Copy and paste. Put it in Slack, right? If you want to know, obviously, specific things, how is the chiller implemented? What is the pump characters, obviously you can ask for that. But if somebody gives you something you don't have knowledge of, just ask the agent, right? And I apologize, I've sat in that seat, and the dark mode was a bad choice. And so I'm sure a lot of the stuff that you see there is just black and not visible, so I apologize for that. But that's output from the agent saying, oh, this is this particular library. It uses these connectors. It has these components. It's organized this way. Like, super great information, great way to get started with something that you don't know. What do we love to do? Let's generate models, right? That's like the first thing everyone wants to do is let's generate something. This is actually something that I did with my colleague actually just a day or so ago. I wanted to use this discrete components library. You may have heard of it in some of the earlier talks. So we just gave a prompt, read and understand discrete components based on this library, build a cool continuous discrete hybrid model using it, right? Don't know what, I mean, that's ridiculous, right? I didn't say what I wanted to build. So what did the agent build? This discrete, this model of a satellite that has some thermal response inside of it, and then some discrete controller to try to regulate its temperature. Okay, like, that's fun, right? I mean, but realistically, that's not the way we work. We don't just say, like, build me random stuff. But it's fun for demos, like Christmas, right? Like, let's see what you get. But, you know, after that, I got something. I didn't know what this thing was, right? Can you help me understand the thermal model? The thermal model architecture, right? Agent goes through, makes little schematics, says, oh, there's these nodes, heat's coming in here, heat transfer here and here. You can even say, you know, build me a nice picture of that, right? And you can get stuff like this. So, you know, these things seem a little bit like toys, but they're helpful, right? These are things that we need to know, right? To continue to work with something, to make it better, to figure out our starting point, to help explain to someone else, right? And, you know, I could have made this graphic, but why should I, right? Like, I just ask the agent, and I get something nice out of it, and I can iterate and make it better. But, you know, these are the things that are just super easy to do. How should we build, right? I mean, rarely are we starting with nothing, build something random, right? We have some models that exist. We want to build something from them. So the right way is, right, conversationally. And I think you heard a lot about this in earlier, right? I'm interested in building a controller for this model. Propose some formulations, right? And then you have a conversation with the agent. You get some formulations proposed to you. I don't like this. I want this. Can you do that? Will this work properly? Will I have to tune it? Is it going to be discrete? Or, you know, whatever, right? Those are the kind of things you can ask the agent. Refine the formulation, iterate, not generating any code, right? Because as soon as you generate code, right, then you're going to go into a much slower iteration cycle, right? You're going to modify the code, test the code over and over again. That's what our harness does. So iterate conversationally when you like the formulation, implement and test at that point, right? So this is combining your knowledge with the agent's knowledge, iterating and sort of planning in a conversational way, but no code generation until you're happy with the formulation. And then you say, generate it, and obviously you can be as specific as you want regarding interfaces, naming, graphics, whatever. And so this is some output from the agent when I asked it what other controller could it build for that discrete model. And it said, oh, you know, that other controller is, you know, on and off, hysteresis. You know, you could implement it with a discrete PID, and it, you know, had some stuff. I didn't say build it, but, you know, that's the next step. Another fun thing to do if you're in the thermofluid space is we always need property models. We call them medium models. This was some work that we did recently where we needed to generate a new property model for a fluid that we didn't have. So the prompt was implement a medium model for this particular oil that's called out there based on the tables and images in the folder that I gave it. Should be a polynomial model with the lowest order possible to get good fits. So those are the tables and graphs that were provided to the agent. Agent read that information, extracted all the data, did the fits, implemented the medium model, and then generated these curves below, right, showing the fits to the data. Is this hard? Could I do it myself? Of course, right? I mean, these are things we do all the time. But how long would it have taken me to extract the data, generate a fit, get the valves back, make the plots, right? Like, this is literally 2 minutes of work, right, for the agent. I had to give it images instead of the PDF, which was the actual source. That's coming soon. I know there are a lot of agents that can read PDFs. Maybe we can by now. But I had to give it images. That was like the downside, but that took like 2 minutes, right? And then probably as long to generate the images from the PDFs as it did to do the fits. You can build completely from documents, right? What is the source of that, right? How would you propose building the system in this image using the components in this library, right? Give it a picture, give it a library that you're using, and let the agent go and propose what it's going to build. And what you see here is kind of the bill of materials. Said, oh, I can see it's got a chiller and a pump. I see these components here. They're in your library. I can see them in the image. Here's what I'm going to build. And it actually went through several phases, building loop by loop, part by part, just like I would have manually, actually, to build it step by step until it got to this. And it identified like, oh, I don't think you have this component. What would you like for me to do? What should I put here, right? But this is awesome, right? In engineering, schematics are everywhere, including models from other tools, potentially, right? We can build directly from them. Just hand that information to the agent, ask it to build. Schematics in different domains are often standardized, even better, right? Because then after we've done this once, we can create a skill and say, hey, when you need to build a hydraulics model, right? This is a four-way valve, this is whatever, right? Like, no longer do we just like, oh, here's the schematic, I'm gonna drag a pump and I'm gonna drag a valve. Just let the agent build in one shot. And if you wanna see that, like a much more substantial build, you might have heard about that HL20 demo in the morning, which was a model built wholly from technical specifications and the raw data. So that link there will take you to the video where you can see a much more substantial build than just from schematics. But this was pretty cool the first time that happened. You can build from source code, right? So if there are models that you have and other formalisms, you can give those to the agent and have it build models for you. So for example, we have a lot of code in Modelica that we would like to have in Dyad. So you can make a prompt like the one that's shown there. How would you propose building the model 2-winding transformer.mo, which was in its resources, using the components in this library, right? Agent goes, looks like, oh, I see these equations, I have these connectors. If there are things that it can't do because there's no matching formalisms or you need to make choices, right? You'll get information back from the agent where it'll ask you what you want to do. But yeah, perfectly reasonable to translate models, whole libraries, from one source into another. If you've got existing IP and some other tool that you would like in Dyad, you can bring that IP along and get Dyad models out. The agent will set up test cases using Dyad, using the regression testing frameworks. You can test the exact same thing in one tool as in another. Yeah, so this is great. And if you want to translate lots of Modelica code, I would suggest you talk to my colleague Avinash over there. He actually has a transpiler which can generate massive amounts of Dyad code from Modelica code very quickly, not one by one like the agent here. Parameterization, or what we often refer to as the data safari, right? So you build a model, how are you going to parameterize it, right? So in this particular prompt, we built something. Look at this system and suggest parameterization changes that would make sense for a system of this size, chiller, and tower. So agent goes, looks at the model, says, oh, yeah, this thing is too big, this is too small, the chiller is sized like this, you probably want this amount of heat. Like, that's awesome, right? Getting a model parameterized, at least a first cut reasonably, without having to go off and find a bunch of data, so that you can actually just get something running reasonably as a start, is a huge time saver. It's easy to build models, especially if you have these libraries, but actually parameterizing them reasonably can take easily much longer. Agent's great at that. Don't forget, you might not have actually set the parameterization for the system because the agent did it for you, so be sure to go back and revisit it. In fact, ask the agent to document that you did this, right, and that you should go back and revisit it. Testing. Like, this is, yeah, certainly one place where agents shine, right? Like, you build something, what test do you propose for multiple generators looking at the controls and faults? You see the output from the prompt here. I'm sure it's not readable. Like 7 different tests that the agent's going to set up for you. This is amazing, right? Because one, I'm lazy. Maybe lots of people are lazy. You want to build. You don't want to test all the time. Our agent harness requires unit testing. You'll get them without prompting, but this is even above and beyond that. And as we rely more on agents to generate the code, right, we're spending less time by hand writing the code and more time reviewing test results. But the agent can set up regression tests in Dyad that feed directly into the Julia testing framework. You can even ask the agent when your tests don't pass, why aren't these tests passing? And you'll get output like this, like, oh, looks like you're referencing the sign of Q, looks like it changed from positive to negative. I mean, you get all kinds of information, right? Not just, oh, the test failed, why did it fail, right? But actually going in and looking at the details, right? And the agent's not limited to just the equations and the physics. It knows the metadata too, right? So you can ask the agent to implement an icon for a new component that you created. Here's a bunch of different icons, an icon for a controller, a certain kind of heat exchanger. This is a dryer. You can tell the agent to do things with the graphics of your model. For example, a lot of times when you build something agentically, it will not, of course, it's not going to put the graphical metadata there, right? But you don't want all of your connectors on top of each other so you can't see what's going on, right? So you can say, align the inputs equally spaced on the left, the outputs on the right, the connectors wherever you want, right? And the agent will then go and take that and do this, right? So professional looking graphics, no effort required, right? I'm not going to draw that. I shouldn't draw that. I'm horrible at it, right? But agents are really good at it. Any style you want, matching what already exists, make it look real, make it look blue, you know, whatever you want. Metadata is just code and the agent can do it, right? So this is great, but we haven't actually done anything but built, right? The amount of agentic use is so much fun, like to generate, but really, I think the value is actually on the backside, which is on the engineering side. What are we going to do with these models once they're built? It's great to build them, and of course, we're going to use the agent to help us build, but what are we going to do once we have models available? This is the easiest, but most probably the thing I do 50 times a day. Simulate, model, and plot the key results. I'm so lazy, I don't even tell it what to plot, right? Just plot the interesting things, right? Of course, I can tell it what to plot, and I will when I need to, but just that command gets me this, right? Cool plots of, this is the satellite with the thermal control, what are the temperatures, what was the heat duty cycle, what was the command. I would agree, those are the key results to plot. That just comes out, right? It's lazy, but super effective. The time it takes to make something, run it, post-process, make a graph, put the labels, right? Forget about it, right? Just ask the agent to do it. And when you're happy with it, tell the agent, save a script so that I can plot it just like this in the future. And if you forget and you just have the image, tell the agent, hey, run the sim and plot these things again just like what you saw in the image, right? So excellent plotting and visualization packages in Julia. Let's take advantage of them. And we're not limited to plotting, right? There's amazing graphical packages in Julia for animations, right? So you can do stuff like this. Like this was just me being silly, right? Generate an animation of the thermal loops so that I can understand what's going on, right? Like this is, of course, not something professional, right? But yeah, like this is something you can just ask the agent to do. And of course, you can iterate on it and do it in a better way. But like this was, I didn't do any of this, right? Like I just asked. Of course, if I want specific things, I'll ask. But you know, this is the power of having Julia on the backside, right? The agent knows how to use it as well. Multiple simulations, no problem. Just as easy as running one, right? Do a parameter sweep, generate the Pareto front, compare this result to the one that I had in my snapshots, whatever, right? Like super easy to do. Ask the agent, get your results out, decide what you want to do. Monte Carlo, sensitivity analysis, right? You don't have to there's all these packages in Julia to help you do it. Agent can use them. Calibration, right? How easy is it to set up a calibration? A prompt like that. Use Dyad Model Optimizer to calibrate the motor parameters using this test and using this data. Be sure to save the analysis, generate a plot of how the calibration went, right? So you get this analysis, you see that it was able to calibrate, and it makes this plot for you, right? This is a quick start, right? Because you can control all this stuff, and you might need to. This is a super easy problem. You take full control once you have this, but calibration is kind of a pain, right? Like it's work, but maybe not so much with the agent. This one, I didn't put a bunch of output because nobody wants to see debugging, right? But models go wrong. Debugging is important. The agent is awesome at helping us with debugging. Why won't my model compile? Why is it running slow? What are the states? Why won't it initialize? What guesses do you really need? Help me understand the structure of the problem. Run different solvers and tolerances and suggest the best ones, right? Super easy. Just ask the agent, it'll do all these things for you. It knows how to use MTK, it knows how to use all the debugging stuff, right? So no arcane debugging settings that generate volumes of data that you have to parse through, maybe in an hour, and maybe you figure out what's wrong. Just ask the agent what's wrong, get real language back, and the agent will probably say, hey, I found this, do you want me to fix it, right? And then you can go on and do that if you want, right? So other useful things, I just kind of put a big list of them there. There's way too many to talk about. Restructuring, creating new subsystems, implementing controllers, seeing the agent, try to tune them out of the box. What happens when I upgrade? Can you help me make a skill? Can you help me make a minimum working example? Can you create a dyad model from MTK? Can you help me create a web app? All these things I've done with the agent, and it's been amazing. So looking ahead, like how has this impacted me? I have to admit, like I sit down in the morning, the first thing I do is launch the agent. Not sure how many tokens I consume all day long, but I'm not sure I can go back. I'm lazy and spoiled now. The agent's like having an eager, bright, and tireless suite of minions who want to please and often make mistakes. But if you have people that have experience, coupled with increasingly competent agents, massive productivity gains. You know, my wife says, why do you sit down and use the agent all the time? It's like, because I can. Like, why would I not? Build skills in conjunction with libraries to even customize it even further. I mean, we're not saying that we're not responsible as engineers for this work anymore. We absolutely are. It just looks different now, right? The way we work, how we can work, and the people and processes will need to adapt. But yeah, I've had a ton of fun with our agent, and yeah, I hope others try it. And yeah, I'm happy to talk if anyone has any questions about different things you can do. If you don't think you can do it, just try and ask. You'll be kind of shocked. Like, it sort of works. So anyway, thank you.
All right. We have time for some questions.
Hi, thanks for the talk. Sorry, I have the impression that you're sugarcoating it quite a bit, because this is not exactly my experience with agents.
Okay.
I mean, they're very good at details. For me, when I have using them, they're like Rain Man. They very know about the details, but they don't know how to connect A to B. And they make a lot of mistakes, especially with Julia. They don't know how to run the PKG test. You have to teach them a lot of how to do that. And then at some point, they forget what we're doing.
Sure.
And it's very hard to bring them back to the correct path. So my question is for you is, how do you keep them in the correct path?
Yeah, and I have to admit, like I'm not super familiar with the uses of all other agents. I've had experience with our own agent, and I know from our AI team, right, that agent is very much tuned to working with dyad, so it knows very much about how to build models with dyad, how to work with dyad, and that specific harness, I think, from what I understand, makes a huge difference. Yes, you have to prompt. No, you shouldn't do, you know, poor prompting and expect to get good results. But yeah, I've found the dyad agent quite competent. But yeah, I think it's to some degree it comes down to
go ahead and try to respond to that question a little
Sure.
bit maybe for you. We do AI pretty heavy where I'm at, and we found that if you use basic memory, MCP, and use it, point it to the file system, and then tell the agent to read all your code and create a knowledge base and tell it to do a high level and a low level scan, and then store that file system piece into Git, and then you can share it with your whole team. And then when it comes up, you tell it use the knowledge base first. It'll have a very reasonable understanding, and we have great success having it write Julia code and do it the way our engineers are building.
Except for the fact that sometimes it forgets to read the knowledge base.
Yeah. So I know the very first thing that our agent does, because it starts with nothing, is it reads its own resources, right? Which is, it has skills for how do I do dyad and a whole bunch of other stuff that our super brilliant AI team does. So, yeah, I guess if there's specific questions, I can only say that I think it works pretty well, and I'm pretty impressed, but I'm also a newbie, so maybe it's easy to impress me.
Hi, it's not a question, but it's a reply to Jorge. So basically what I have found with agents, They are like monkey. They like to jump around. And the only way to put them in the cage is putting them in the right skills. Like Anthropic struggle with basic things like generating PDFs, generating XMLs. And the moment they guided them towards the right skills, they found extreme amount of success. And to build a harness that actually works is to teach them how to take a task and go towards the success. And I think the way everyone in the industry is doing it, and OpenAI, Anthropic, is by guiding them with the skills. Exactly, but then there's also a solution for that.
So one of the things in the dyad harness is that it's baked into the execution loop that it runs the dyad compiler and has to check. Can't skip checking that your model works. That's literally not a thing the agent has the option to skip. And so that helps a lot. That type of thing is like building in a harness that actually is specialized for the application at hand. It still sometimes has trouble with syntax and trouble with like whatever, but it just like it can't forget to make sure that your model works like Claude by itself could do. So there's many other bits of secret sauce in the harness, but I mean, getting that harness to work. And when we've done evals too, one of the things that's interesting is that, we're comparing different models. We're looking at Fable, GPT 5.6, and yeah, okay, Fable does better. GPT 5.6 does well, like very well, much better than Opus, for example. But all of the models do better in our, like, the difference between the models is nothing compared to the difference between our harness versus just a generic coding harness. Well, there was a good talk earlier here about a thing called wink.jl by Josh Belanco, and he basically has made a Julia-specific harness. So I haven't tried it, but it looked cool.
All right. Any other questions from the audience? Seeing none, maybe we can thank our speaker once more. All right, while he's getting set up, our next speaker is Matt Bauman. He is the Director of Sales Engineering at Julia Hub, and he's been ubiquitous in the Julia community for over a decade. And he's going to be talking about the Julia Ecosystem Security Advisory Database. So let's welcome our speaker.
Great. Thank you so much. I'm very excited to be talking about this. This is some work that I've been doing over the past year. It's been a lot of work, and it's very rewarding to be able to share it all with you today. I have a lot of things that I want to talk about today. Each one of these bullet points could easily be a 30-minute talk in and of itself. In fact, one of them was. So first, we'll do a really brief overview of the advisory landscape, what makes an advisory, what a CVE is, and what the Julia advisory database is doing. The third bullet point here was a talk this morning, and I hope you were all able to see that one by my colleagues Myrtle and Venkatesh, talking about how we can check for advisories and secure the ecosystem through these checks. I'll do a brief recap, but won't spend too much time there. We'll talk about how we can author, publish, maintain the advisories in the Julia security database, and then spend some time about JLLs, which is a hard bit of this. So what is an advisory? You might know some. You might recognize some of these logos. Some advisories have gotten really good branding. If you don't recognize them, that's fine, because most aren't that glamorous, and there are a lot of them. already, as of today in 2016, there are more CVEs that have been published this year than there were in all of last year. So we're growing the number of advisories drastically, particularly in part driven by AI discovery, but it's just also a very large landscape. At this point, there's hundreds of thousands of advisories. So what is a CVE good for? Why do we have them? Why do they exist? They are a canonical identifier. They're the identifier of a bug or an issue that someone thinks you should know about and you should care about. And it's kind of become the center of a security ecosystem. The thing that makes it very powerful is that it's all-encompassing of the entire software world. They try to cover everything from student projects to the biggest Google project there is. They rate these severities with a particular emphasis on critical vulnerabilities. Altogether, it is the notification mechanism for folks to understand that there's a serious security vulnerability in a particular piece of software. There are also some challenges with it. Kind of at its core, it's a semi-structured plain text. Sometimes there's more structure. Sometimes that structure is missing, which leads to some challenges when you go to try to figure out what project is this CVE actually talking about? What versions is it actually talking about? Partly because people are bad at versioning. Not everybody uses semantic versioning, and the number of versioning schemes out there in the world is wild. Like, there are so many different things that people do, so it can be hard to understand how you're supposed to just compare versions that are named in a CVE in the first place. It can also be hard to understand what the trust model is. Like, is it okay if you're treating some argument as untrusted or trusted? And also then, how does that impact the severity ratings? These things can be subjective and can be hard to understand. And all in all, it's a very opaque system. There's all sorts of bureaucracies built up around who can be a numbering authority and who can assign these things and how they get assigned and how they get reviewed, rejected, or not. It's kind of hard to understand sometimes. This is an example of a CVE. So this, I know it's small there. I'll blow up some of it as we walk through it. But how many folks know that there are CVEs that talk about Julia packages out there? It is a thing. We have CVEs against Julia packages. This one is identifying URIs.jl and HTTP.jl, and it says in its plain text description what versions of these packages it affects. It also says what the vulnerability is, a particular class of vulnerability. There is, on this CVE, structured information about it, but it's incomplete. It only names HTTP.jl. It has a vendor field, which doesn't really make sense. Julia Web is the GitHub org for HTTP. It does have the version information, but it's missing the URIs information. So it's incomplete. This is very typical. Most CVEs don't even have this structured information in it. There's a severity. This was rated as a high severity issue. But CVE and those three letters there, they are not special. There are a lot of ways that you can identify bugs, and there are many other identifier prefixes these days. The EU has its own vulnerability database. The US has a national vulnerability database as well, but they just reuse the letters CVE. There's GitHub's vulnerability database, and then languages have their own identifiers. Python, Rust, Haskell, R, Go, and these language-specific advisories are ecosystem-specific. They are highly structured using a very well-defined schema called the open source vulnerability schema. And now we have JLSec as a new advisory identifier. What is a JLSec? So this is the base CVE on the left, and on the right is the Julia Ecosystem Advisory Database showing the very first advisory we published last year, which is this CVE. So What does it do? Well, it adds that structured information. Now we exactly know what packages we're talking about. We're no longer saying http.jl because when you're using packages in Julia, you just say using HTTP. When package names end up in projects and manifests, they just say HTTP. And so that's the name that we use here. And we know exactly the versions. And we know that these are semantic versions. We can do comparisons. We know how to do all of this. So that's a huge benefit that we have here. We also link back to the originating advisory here. We know that this is the same issue or an alias advisory to the original CVE. And now our description, we can do more with it. We can do better than just plain text. We can have markdown, we can have code, we can format it how we want. So what is a jailsec good for? Well, it is our canonical identifier. It's the nexus of our security ecosystem, and it's all-encompassing of the entire software world that matters. So we're able to have a lot more control here, which means that it's structured. We know exactly the projects, or rather the packages that it identifies. We know how the version comparisons work, because we know that all of the Julia packages use semantic versioning. And it's no longer an opaque system. It's a GitHub repository. All of you are welcome, and please join us in helping maintain this. It's all open and available, and folks can work together on it with us. So this is the GitHub repository that holds both the code that can work with, identify, and manipulate the advisories, as well as the advisories themselves. The advisories themselves are just markdown files with a TOML front matter, very much like a Franklin blog post works, right? You have the TOML front matter there too. But the TOML front matter here is defined in terms of that OSV schema. So all of the fields are well-defined using the same industry standard sorts of definitions that everybody else is using. And we have now defined the Julia ecosystem to mean all of the packages in the general registry. So how do we check for advisories? There's lots of ways to do that because we participate in this ecosystem. Do check out that talk from Myrtle and Venkatesh earlier this morning, but I'll just fly through a few things here. You can go to the website itself. As of last week, we are now security.julialang.org. So you can go there, see all the 1,600 or so advisories that we've published. You can browse them by package. There are filters. You can look at particular advisories by their severity, or whether there is a fix available or not, whether they're deprecated in the general registry, which is a new flag that we're hoping to use more as we work our way through the ecosystem. But now that we work within this OSV ecosystem, OSV.dev, which is a larger project, they also ingest the Julia advisories here. So you can see right in the middle of this page is Julia itself with our 1,600 advisories. And you can navigate through there to find the exact same advisory named in the same way. We participate in this larger security ecosystem, which gives us a lot of power here. So there's the OSV ecosystem. We use OSV lint as part of our continuous integration to make sure that our advisories are doing what they need to be doing and participating well in OSV world and then get exported to OSV.dev. There's a spec called the package URL spec that has now a Julia definition for it. And so we use that thanks to Sebastian Selles. And he also has a package urls.jl library that can help build these. They're basically like URLs that identify a particular package. But because our advisories do this, that means that SBOMs, software bills of material, can use that when they embed this. So an SBOM is just a glorified JSON or some sort of a file that has a listing of all of the software components that you're using. Think of it as a glorified manifest, but one that can support all sorts of languages. So we integrate well with this through PKG to Software BOM by Samurai Aku, or Trivy as work that was done by Ryan Benasuti that allows you to create an SBOM, and then once you have an SBOM, you can take it to a scanner, and then you can run a scanner on it. This can include Julia Hub or Dependency Track or Trivia itself. Dependency Track I really like because we did no work on this project itself. It is just an OSV project. You just need to go there. We didn't do any changes. You just go and it says, the Julia ecosystem is available. You tick it on, and suddenly it can identify Julia vulnerabilities just as a result of participating well in this ecosystem. So we also support it within Julia Hub ourselves, and there's the reference to Myrtle and Venkatesh's talk. So now we have this database. How do we do something with it? How do you author or publish advisories or help us maintain them, edit them, clarify them? We've tried to document this as best as we can on the website. You can find on the About page information about how you can contribute, how you can report vulnerabilities. And the key thing to remember is that this is a notification mechanism for downstream people. It's not how we notify the maintainers. We want to make sure that we're notifying them in a responsible manner, especially for critical vulnerabilities. Those should be done in private to the maintainer, making sure that you're not giving people exploits as you're notifying folks how to do this. So we want to encourage best practice in reporting of vulnerabilities, but then once they are reported and ideally fixed is the point at which we can notify downstream consumers of this through a published JLSec advisory. Because we're in the OSV ecosystem, not only do we have documentation about how to do this, OSV themselves have this documentation pages that you can reference, or you can look to the other languages as well. And OSV have this nice documentation page on what makes for a high-quality OSV record. And they have 3 key things here, being valid, precise, and identifiable. Personally, I would add actionable, because these are notifications. Someone who gets notified of a security vulnerability is going to want to do something about it. And so ideally, the advisory itself would have information about what version they can upgrade to or how to work around the issue. Now, this is the hard part. What do we do about JLLs? A quick overview of what a JLL package is. They are packages that build and redistribute some upstream library. And they do that as a Julia artifact, so it can be easily loaded. They're wonderful and enable all kinds of great functionality. But that upstream advisory may have, or that upstream library may have published advisories. The problem here is that the only one who really knows what's inside that artifact is the person that built it, or the system that built it. In our case, the system that builds almost all of the JLLs is Yggdrasil, the world tree that holds all of the build scripts, and they're the ones that know what those artifacts contain. It is a special case, but it's the most common one of what an artifact may do, and it's the most common one that's going to have an advisory against it, because it's how we generally recommend deploying and redistributing some upstream software library. So I started on this endeavor almost exactly a year ago. This was August 8th of last year. I asked on the binary builder channel of Slack, I was like, hey, so how closely do our JLLs follow the convention of tracking an upstream software library? Like, you have curl JLL, is it version 3.2.1? Is that the same as curl's version 3.2.1? And is it like 99% gonna follow that? Yeah, it's close-ish. I was like, cool, we can run with that. Like, this will be easy. I can just do this. We'll make the link between a JLL and its package. Most of them are gonna track. This will be great. We're talking about 1,800 JLLs these days. There's a lot of them. And across all of them, we not only want to know things about their latest version, but we want to know about their old versions too. In fact, it's the old versions that are most likely to have advisories published against them. Ideally, the latest versions don't have advisories published against them, because we want people to upgrade to the latest version to not be using a vulnerable version. So, this is the scale of the problem. We have 13,000 versions that we would like to understand what version of the upstream do they talk about. So we need to connect these. How do we do this? This is about the third or the fourth way that I've tried to do this, and the previous three were all worse than this. They were all wrong, and this is probably wrong in some way, but it works quite well. The way that we connect these JLLs to their source project is, first we need to identify which commit on Yggdrasil built that thing, and because it's a Git repository, we have that history. We know we can go back and find it and see what the state of the build tarball script was. Because Julia is reproducible, and because Yggdrasil, for the most part, stored what the manifest was when it was building these things, we can actually just reevaluate it, and this works. This is a great testament to Julia's reproducibility story. Like, I went back to Julia 1.3, 1.4, 1.5, and it just worked. We could output what Binary Builder calls the meta-JSON that contains information about how these packages were built. I'm most interested in the sources that it used. So the tarballs that it downloaded, the Git repositories that it accessed, the commits at which it built those Git repositories. So now we need to figure out what those URLs do. And a good place to figure out that is through another open source project called Repology. They are a compendium of all of the package managers' different ways of bundling software projects. So for example, they have Debian's information about how apt stores curl and how you apt get curl and what versions they are, and also what tarballs they built that from, as well as Ubuntu, as well as Arch Linux, as well as all the, so many package managers, including distributions I didn't even know existed. But they're all there and they expose it. It's not all of this is exposed on the website, but it is exposed in their 15 gigabyte database dump that they provide, and you can go and look, and it's been wonderful to work with. So from that, we can extrapolate, look up, figure out what the URLs that we used in our JLLs, how they linked to upstream sources. We can figure out what the projects were in the namespace of Repology, right? That's part of the problem with CVEs is they don't have a namespace. They don't have a package manager namespace to work in. But Repology does, so we use that, we trust that. And then we store this in a Git repository that works alongside the security advisory database called General Metadata that has this updated nightly. So now we know something about our JLLs. In fact, we could reconstruct the metadata from all of these old build scripts 96% of the time, and most of the times that we missed were back in, 2020 when artifacts were new and Binary Builder was new and things were, breaking all the time and they were figuring out how to build the system in the first place. So that's great. That's working quite well. All told, these versions download from 6,300 unique different tarballs, 1,200 Git repositories at 5,000 commits. It's a large scale of things. And now we can ask, how well do we do? How well are we able to match JLLs against this Repology information? Well, we have 1,800 packages. The latest version having metadata is 99%, right? So like I said, most of the things that we're missing are from old registered versions. About 90% of those have exactly one upstream source. So sometimes, a JLL will bring in multiple sources, and then we need to track each one of those, and we don't know which name is going to be the one there. So I just looked at those that have exactly one source, and of those, about half of them we've now connected to a Repology project and have information about their version numbers, which is lovely. And there's always going to be a long tail here. And in fact, Repology doesn't have every software there is out there. And a lot of JLLs are very specific scientific engineering software projects that aren't redistributed elsewhere. And so I wouldn't expect this to ever hit 100%. So how did we do? How was that Slack post, right? Are we 99%? Not really. Comparing just the latest version, we're 72% matching of what they do. And when I started this, I was like, we need to have all of our JLLs match the versions. That's going to be very useful. Today, you ask me that, I say no. All of the JLLs should have radically different version numbers than their upstream sources because we use semantic versioning, and a lot of upstream libraries don't use semantic versioning. And it's powerful to have semantic versions. And so I strongly feel that JLL authors should munge the upstream version number in some way, so that way we can make use of package.jl's compat clauses. The part that Slack post didn't name, and kind of the naivete that it exposed, was that I just kind of blindly assumed that curl JLL is going to be the curl project, right? But actually, that is less common than our version matches are, right? The fact that the name of the JLL and the name of the upstream project might be different. And this is just representative of how messy the software world at large is. You just start looking at some examples, like, is curl the same project as libcurl? Is git the same project as libgit2? Is 7-zip the same as pzip and p7zip? And all of these different projects, they're wildly complicated. And so we're building and exposing some of that complication, but then we need to understand it, and that's what this does. So back to advisories. The advisories against JLLs, they are a different type on the advisory database. They are of the type upstream, and this confused me at first when I started building this database. I was like, yeah, but the same is true of the HTTP. We have that upstream advisory. No, that is an aliasing advisory because they're both referring to the same issue and the same package at the same versions. These, however, are upstream advisories because they're a vendored component, or a component from somewhere else that we are then exposing. And in particular, you can't have a aliasing advisory that has different versioning information. And we want to have different versioning information. So that's what the upstream type is on the advisory database. Now, how do we find these things from the originating advisory databases? My mantra throughout all of this for JLLs is to do due diligence for upstreams that themselves do due diligence, right? Like, we're not going to boil the ocean here. We're not going to dig and find every last issue. But if it's something that they've publicized and made easy for us to notify, well, we need to do the same for Julia users. So Repology also has data on the vendor product pairs that are used by the advisory databases, and then we can search for them. And we do this nightly, and it's taken me about a year to go through the entire backlog of all of these identified advisories. There's still some that I haven't merged yet because of issues with the advisories themselves, but a bot goes through and suggests found advisories that have been recently updated for publication. This is what one of those advisories, one of those pull requests looks like. I don't know, this is probably a little hard to see on the screen there, but you can see that there are version information that we try to show our work in how we connected the versions here. This is a good example. This is the GNU Scientific Library, and the version numbers sometimes match, sometimes don't. And you can see how we did this comparison. There is an outstanding issue, but it's a low severity one that's not going to really impact folks in many ways here. So a few key points. If you're using this, you want to make sure that your JLLs that you use are indeed ones that are well tracked, that we know about, that the advisory database knows about, and that we know how to publish advisories for. We intentionally ignore old versions, like versions older than what we have, just because we don't need to import advisories from 2010. Like, Julia didn't exist in 2010. We don't need to worry about old advisories like that. We intentionally throw those away. And tracking of the standard libraries within Julia itself, that Julia itself bundles, is still a work in progress, and we notify that that this is known to be incomplete and help us come finish it out. So on that note, how is it maintained? Come join us. I've tried to build as much automated tooling as is possible, and this is, automated tooling that's deterministic, working through the advisory databases, doing a nightly search. I've focused on those JLLs that we ourselves redistribute. I know there are others out there, and you can come join the working group, the community working group, on Friday mornings or afternoons here. Some key improvements that I know we still need to do are listed here, but in interest of time, I want to start taking questions. Thank you for your time.
All right. Are there questions from the audience?
So Matt, I'll ask you I've asked you this question before, so maybe, but for everyone else, I'll repeat it again. So as a frequent Yggdrasil author of many packages, I see the JLSec database publishing lots and lots of advisories, but I don't care about 99% of them because they're not my packages. But the ones I do care about, I don't know how to find them. Once I find them, I know what to do about it. So is there a recommendation for like what an Yggdrasil author should do?
Yeah. Let's see if I can change to my entire screen. Great. So I can go just directly to the Ecosystem Advisory Database. On the Packages page, this is where you can find the information about the packages themselves. So if you're maintaining some JLL in particular, you can find all the advisories that affect JLLs here. And the ones that I care the most about are the ones where there is not a fix available. So if we disallow this, you can see the JLLs for which we've not yet published an upstream patch. These are the things that a JLL author, someone who works with Binary Builder, can go and see, oh, I need to just have a patch. These are things that often the upstream have indeed published patches for, and we just need to rebuild a new version ourselves. I've been trying to do a lot of this. I've done a lot more Yggdrasil builds than ever before, and much appreciation to Mose and Eric and others there that have helped guide me and helped maintain this and helped keep tabs on this. But you can go through and find, for example, a particular package that you want to have. The other thing that we can do, though, is we have a new deprecated tag on the general registry. And so we know about packages that we've deprecated. So YASM JLL is a bundling of an upstream source that wasn't updated since 2014 and has advisories against it. So this is one that we know is not going to have patches for. So instead of needing to patch it, here we've gone to the general registry, suggested a deprecated tag. That tag can be removed if it ever gets revived, but this can be a secondary notification mechanism.
So quick follow-up is, if I click, let's say wget JLL, I don't know if it has any advisories, but let's say the first one, right, like it was fixed.
Yeah.
Is there like a concept of closing?
So once an advisory gets fixed, once a new JLL package gets published, those are the first that I search for in upstream advisory databases, and I compare all the version numbers again. So I have that information. So ideally, hopefully, the nightly bot would see, oh, there's now an upper bound on this, and we add an upper bound to it, we add a fixed version, and then it'll drop off of the unfixed page here.
I was curious how the JLSec stuff works with multiple registries and like the same package names with different UUIDs.
Yeah, so this is all 100% very explicitly general only. I've kind of considered everything else out of scope, and the main reason for that is because we need to be able to name what HTTP is. We need to know what that is, and if there are two registries that publish that package of that name, we would no longer know that. And in fact, it's really important that general itself disallows duplicate names for this reason. So that's a theoretical capability in the package manager that you can have duplicate names, but a policy on the general registry that disallows that enables us to do this kind of thing.
Thank you for this interesting talk. Coming back to the previous question, is there also a way to get like notifications by this advisory database itself, like an RSS feed for special packages or something?
Yeah, so ideally we would have integration with Dependabot. So earlier this year, Ian Butterworth did a lot of great work to integrate Julia into GitHub's Dependabot, which allows it to suggest updates. And theoretically, Dependabot can support advisory updates, but they do not have the ability to integrate with the Julia advisory database at this point. So that's something that we can't do. We need to pester GitHub and be like, hey, GitHub, there's demand for this. And we have our chops, we have our database, we need support for this. And so there's an issue that you can go find and thumbs up and rabble rouse about. And hopefully GitHub one day will support Dependabot updates for security advisories. What's that? Yes.
They've said very clearly they don't. Sorry, the GitHub people have said that they very clearly do not have any plans to support this integration at the moment, which may change in the future.
Right.
So I don't know if we should depend upon them.
I don't think we should.
All right. Thanks. Let's thank Matt for this amazing talk and QA session.
Thank you.
All right, so we have a little break coming up, about 15 minutes for coffee and cake, but please join us back again at 3:45 for the next talk. Sorry, I hope I didn't catch you. Good.
Yeah, thank you.
Do we have to return this for 15 minutes? pronounce your name. It's Jose Kenem?
It's Jose.
Jose.
Yes.
Okay. Jose Kenem?
Quinum.
Quinum. Okay, perfect. And your affiliation in
Namibia University of Science and Technology.
So, now, if I were to introduce you, is this the right way to do it, or should I just say the Namibia University?
Yeah, I mean that's good enough.
Okay.
Yeah.
Is a researcher at the Namibia University. Good. Good. Thank you. All right. Welcome everybody back to the talks. So we'll be starting off with Mose. He's going to be talking about running tests in parallel with Parallel Test Runner. Mose is a research software developer at UCL and is a popular figure in the Julia community. So let's welcome our speaker.
Yeah, thanks. So if you want to run the test of your packages, of your Julia packages, most people start with a test standard library, which is nice, it's simple to use. And if you have a extensive suite of tests, you probably split it over multiple files that then you will likely include one by one. So maybe you have like an overall test set, and then you include one by one all the files that you want to run the test, including all the tests that you want to run one by one. This works, simple, but this runs everything in a single process. So this means that the work clock time grows linearly as you grow the list of tests that you're adding. Also, if you use services like GitHub Actions, they give you machines with multiple cores, which is great. You're using only one when you run the test, which is less great. And also, since everything is in a single process, there is no kind of isolation between each test and file for the test. Basically, there is some leaking of global states. So, for example, if you define some function or some variable, this then may have effect on files and, that are included afterwards. And also, if you want to run only one of the files in this list of files, you need to go here, go back to your runtest.jl file, and manually edit the file just to run that single file, which, again, is probably not a great experience. So there are various packages in the Julia ecosystem which have addressed some of these issues, which is good. But then we developed a parallel test runner. So a little bit of history about this. So I don't know how many people know that actually Julia base has a function called runtest, which run the test of Julia itself is not for running tests of the external packages, but can run the test of Julia itself in parallel, which is something that we really like. And so Team Bezard adopted this infrastructure for running tests in parallel for CUDA.jl a very long time ago. Since it was such a great idea, this infrastructure was just copied in all the other packages of the GPU ecosystem. Of course, just copying the same code everywhere is not very maintainable. So I think at some point, Valentin was sick of having to copy everything everywhere. Maybe you make a fix and you need to copy in all the packages. So Valentin extracted this into a package, which is now Parallel Test Runner. And there have been other contributors since then. So this is purpose-built for running tests in parallel of the Julia packages, and especially for very compute-intensive, resource-hungry test suites, like packages like CUDA.jl, AMD GPU, Enzyme, and now I think there are more than 80 packages using it already. So if you want to migrate from the previous setup that I showed you before, where you use your package and tests, and you have this list of files, the migration consists in loading my package, parallel test runner, and then call the function run test with first argument, the name of the module of the package that you want to run the test for, and that's it. You don't need to list the files manually one by one, because what parallel test runner.jl does is to discover the test file in the test directory, excluding run test.jl itself, and then it under the hood run tests for all the test files that are in the test directory in parallel. So it spawns multiple processes to run the test in parallel, so you don't need to have new macros, new annotations. You don't need to rewrite the tests themselves. So like the content of these files doesn't need to change. So the migration is very easy. It's only what's in the run test.jl. And so I already mentioned that the tests run in parallel by spawning a process. And for this, we use Molt from the Pluto developers who developed this for Pluto itself. The tests are run inside a sandbox module for each file, so there is a sort of isolation and no leaking of global state. You can control the number of jobs that you use using a flag, minus jobs equal to the number of jobs. But by default, we try with some logics to use as many jobs as possible. And also, you can filter the test that you want to run. So if you want to run only one or a subset of tests of the entire test suite, you can pass it as argument to the test, during the invocation of the run test script. Other packages like red test items have a finer granularity, because you can even specify the test set, but we have like a file level granularity, which is not ideal, but still better than having no granularity at all by default. Also, the runtest.jl becomes a script, so you can invoke it from the command line. You have also help information. You can list all the test files that will be run automatically if you don't do anything. You can specify the number of jobs. You can enter the verbose mode to print more information. You can also choose the quick fail mode. So as soon as one test fails, the entire test process stops. Otherwise, it will keep going until all of them run. And yeah, so for example, here you can see that you can execute the run test file as a script, and then pass arguments like, for example, the name of the test file that you want to run. And PKG test also is able to forward arguments to running the test, so you can do the same as this one with a pkg.test and then using the test args argument. So what it looks like when you run the test, you have the information about, this is wrong because these are two. Oh, no, sorry, these are running. So, okay. So this is running 3 tests using 2 parallel jobs. And you see that these 2 jobs already finished, and then there is another one still running. You also get a status bar with an estimated time to finish the test, because we record the historical time to run all the tests, so we kind of can guess how long it will take to finish the test. And yeah, all the output of the printed during the test is collected and printed only at the end, so that you don't have any interleaving, and I have an example about this later. Yeah, so I already mentioned that we record in a scratch space the duration of the test, so that when we run again, we can run first the test files that historically lasted longer, so to have a better scheduling strategy for like better load balancing. And also recently, Christian introduced a feature to run first also the test that previously failed, so that there is more likely that they're going to fail again, maybe. So you want to, anyway, have a quick feedback of, oh, now this is actually passing, no, this is still failing. Also, you can control when the processes are recycled, when they get over a certain memory threshold. In general, there is next to no configuration that you need to do. Maybe there is something about the memory usage of the workers that need to be tweaked. I don't think the defaults are perfect, but they're in general okay. But still, we have some escape hatches in case you don't like the default setup of the test. For example, if you want to run a different set of test files because you don't want to run all the test files but only a subset of them, you can pass your own dictionary with the test suite argument. You can pass a keyword arguments also specify some init code to run for all the tests or all the processes that we are spawning. Or you can specify the name of the executable. Maybe it's not called Julia, it's called, I don't know, Julia debug if you want something else. You can pass flags to Julia itself, set environment variables, and these are applied to all the workers. But if you want to specify different of these options only to some test, you can use the test worker argument, which takes which is based on the name of the test file. So it's basically a finer control of these previous options. And to do a very quick demo, imagine a package called demo, which is the structure. You have the source file, the project, and then in the test directory, you have a bunch of files, including the run test, which looks like this one. And then, yeah, a bunch of files. But in the run test, we don't include manually anything. Then when you go and run the test, sorry, here the color is not great. But when you run the test, you get something like this. So I'm running this with a verbose mode. So you also get more information, like how long it took to init the jobs, to compile the code during running the test, so you can get a feeling of how much time you're wasting or spending in compilation when you're running the test, which may be a good information if you want to improve something. Also information about the garbage collector, how much time and what percentage of the total time has been spent in the garbage collector, allocations. And this is the memory usage at the end of the test of the current worker. And also, if one of the workers printed some text, this is printed only at the end. As I mentioned before, we don't print while the tests are running so that you don't have interleaving of possibly very long text. And then you get also a summary of all the jobs, so you can see how many tests were run, or how many maybe were broken, and how long each of them took. Yeah, and in terms of other packages that are in the ecosystem that address the issues of running the test, there is a safe test sets, which only creates a sandbox module but doesn't do any filtering or any parallelism. And then there is a test item runner for, again, no parallelism but isolation, and that's the filtering. Retest items also for parallelism using procs, like multiple processes, like a parallel test runner. But you need to rewrite the test using a different macro. It does have isolation, and you can do the filtering with a finer filtering compared to parallel test runner. Also, XUnit, which has parallelism but based on threads, not multiple processes, and so on. So here I have another quick page about if you want to choose the runner for the test for your package. You have some indications like what you need and what package you may want to use. But also, if your package has a very fast test suite, the test standard library sometimes is even fine. It's not a problem. Just to conclude, parallel test runner brings parallelism, isolation, and also a command line to run the test at the price of just deleting some code. It's already used by over 80 packages, including 2 standard libraries. In the future, we may have automatic retries of Flaky test. And yeah, if you want to try, you can have a look at this package. Yeah, thanks.
Are there any questions from the audience?
Okay, I have 2 questions. So you mentioned this filtering capability. Was it on the level of files in the test directory, or can you also somehow filter specific test sets inside each file?
No, with parallel test runner, only test. Only file. But there is test item runner and red test items that have a finer level of filtering.
And then the second question, is there functionality to include some kind of header file for each tests. So you might want to set up, I don't know, a list of types over which you want to run your tests.
Yeah, so this is a init code. It's a keyword argument that you can pass to the run test function. So this will be run before each test file. Otherwise, if you want to specify some code which is run at the beginning of each process, you can use init worker code.
Okay, thank you very much.
All right, let's thank Mose once more. Okay, so our next talk is going to be by Jose Quenem. He is a researcher at the Namibia University of Science and Technology, and he's going to be talking about implementing AI workloads on Ray in Julia. So let's welcome our speaker.
Good afternoon. So before I discuss what I'd like to talk about, I would like to acknowledge Paul Mkondo, who implemented some of the workloads that I discussed in this presentation. So really, the context of my presentation is trying to do data science or AI implementation, mostly workloads on commodity cluster. So I've heard a lot of talks this week about, improving HPC adoption in the Julia community. But if you want to just use AI algorithms like search algorithms or some data science, data analytics in a commodity cluster that you just assemble a couple of virtual machines and then you just want to build the distributed analytics, it becomes really complicated. I know that there are libraries like Dagger and distributed, and I've had some discussions with Julian about how to use Dagger, but imagine for a minute that you're dealing with, students who are not, don't have a background in computer science, and now you're taking them through the whole hassle of having to implement all these complicated distributed and parallelism directives and procedures. It becomes really cumbersome, right? And the same goes for distributed. So the idea, so I chose a couple of workloads to show how painful it can be to actually go through that exercise. I've selected 3 for this example. The first one is actually all 3 are related to distributed clustering in this case. The first one is just building a parallel k-means. And what they do is actually, we didn't propose any of these algorithms, actually. We chose algorithms that have already been published, right? And the first one is from Huang and Zhang. And what they do is actually partition the data on multiple nodes and do the clustering locally, and then just use MapReduce to synchronize the centroid update. The second one is a partition-based agglomerative clustering. It's just a hierarchical clustering, but it's the PAC algorithm. And it's actually using mutual nearest neighbor to do it. And they use the distance-based partitioning and the distance-aware merging technique just to make sure that the merging remains consistent when in the cluster, that you don't create dependencies between nodes outside the same cluster. And then the third one is a TMFG a filtered graph, right, that uses the distributed bubble hierarchical tree algorithm. And so the idea for us is to take all 3 algorithms and try and implement them in a cluster. Originally, what we wanted to do is to implement all these algorithms both in Spark and Ray. But we finally decided to go only for Ray. And for the test, we use the typical, we just pulled a Kaggle data set 1 million record from the US accident data set. So the results are here, and actually I showed this not because I want to discuss these algorithms here, but just to prove that yes, it has been implemented and it's yielding results, although we can argue about the quality of those results. And I'll come back to that in a minute, because it depends on the infrastructure you throw at the result, the execution time, and most importantly, the quality, the silhouette quality of the clustering. But let's look into our environment, our execution environment. So we use a array cluster, and array cluster is a typical master-slave cluster. So you have basically the master node that's usually referred to as a head node, and then a bunch of worker nodes. And the worker nodes will depend on your infrastructure. And the cool thing about Ray is that it gives you some kind of shared memory access through a distributed object store. So you can then, once you finish your configuration, you can access memory to memory, and you don't have to do that implementation. It's already provided for you. You can just access your object automatically. And so in our case, what we got was just 3 VMs, right? We had our head node on 1 VM and then 2 worker nodes. But sometimes we'll modify the configuration to use even the head node as a work node. But nothing stops you from extending the cluster. You can just throw more nodes. Actually, we had to do it to improve the result a little bit. But the basic setup was to just use 1 head node and 2 worker nodes. And so to implement your workload in Ray, you had a couple of options. One of them is to Dockerize your implementation, and then you just throw it and then call it within Ray. The other way is to just implement it through Python. So that means that you have to build a Python wrapper around your Julia implementation. And that's what is interesting to us, just to show the pain point of how you get your implementation across the Ray cluster. And I must say that at the very beginning, when I got the idea, I noticed that there was a package, ray.jl. And during the experiment, I noticed that the package was archived. That means we didn't have the option of using that package and invoking our code directly into Ray. We had to go the basic way of running some Python code and calling Julia from Python. So typically, when you're running your processes in Ray, it's a cluster, right? So first you have to start the cluster. And to start the cluster, basically, it's a master-slave, right? So you start the master and then start the slave. So you start the master, right, and just specify that this is the head node and give the port number where that process is running. And then you specify on each machine where you're running the worker process, then you just have to specify the address of the head node and the port number where that head node is running. Typical master-slave. And then you submit your job, right? So overall, our implementation is that we use some YAML code for some configuration. We used a driver code in Python, which then hacked, because Ray uses an actor model for communication. So to support the communication between the workers, we just added an additional driver implementation, which is in Python. And then we had the actual worker implementation, which is in Julia, but invoked from Python. So you see those 2 codes, the worker implementation in Python, which is just an envelope calling the worker implementation in Julia. And this takes me back to a previous experience I had with dealing with clusters, data science applications with clusters. And this time around, it was with Spark. And at that time, what I was doing was real-time data analytics, right? Throwing some data from a database through Kafka And it worked well until I had to deal with real-time data. And once the data comes from Kafka, Spark just doesn't return it to Julia. I've talked with the package developer, but I don't know what's wrong. It just didn't work. We looked for every possible option, but it just didn't work. So the reason I'm giving the presentation is sort of a rallying cry. Could we just join our hands and fix this and find a solution to this? Because there's a place for Julia in data science and AI, and particularly for cluster computing. And I think we should use it. Thank you.
All right, do we have any questions from the audience? Actually, I had a question. It's pretty interesting to see these algorithms get run on distributed clusters. What challenges did you face trying to get Ray working on Julia, but also like the specific clusters? Were you able to find all the libraries and such that you were looking for, or was it like a difficult job working with, these distributed systems?
In terms of distributed systems, Ray works fine. You just have to configure it following the documentation. Actually, there was more or less no issue on that side. The challenge comes from the Julia implementation. If your code is in Julia, it is the integration, because if your implementation is in Java, Python, or C++, for example, it goes fine. But because there's no native environment for Julia in Ray, we had to almost hack the code. So you actually write in both Julia and Python at the same time, right? You write your implementation in Julia because you still want performance, and then you have to put a wrapper in Python because that's the only way you can get Ray to talk to your Julia code.
We have time for a couple more questions if there are any. Oh.
Do you think that Ray.jl should be unarchived?
I would really like to. I think my point is, this should be the conversation, that we have two options. Either starting something from scratch, building on distributed or Dagger, or take advantage of, because these other systems, they have been tested, and they have got the adoption of a fair share of the data science and the AI community. So having a way of integrating Julia into those tools would just be an advantage. So either on archiving RAID or JL or building something similar, I don't know the trouble that the developer went into and decided to archive it. Good.
All right, let's thank Jose for the amazing talk. And if you have any questions, you can find him around in the conference. How should I introduce Dimitri?
Dmitry, or Dima. I'm not sure.
No, but he has no affiliation listed.
With?
Anything.
Yeah, that's fine. He's in Julia Hub.
So I'm just going to say, I think, engineer, software developer.
Yeah, software engineer.
Yes. Hello, everyone. I'm Panayotis, and I will be presenting work me and yes, of course.
Okay, so our next speaker is Panayotis and Dimitri. Panayotis is a developer at Julia Hub. He works on Dyad, and he's the Pluto maintainer. And Dimitri is a software developer at Julia Hub as well. And they're going to be talking about the making of advanced Pluto, the VS Code extension. So please, let's welcome our speakers.
Hello, everyone. Welcome to this talk. I'm going to be presenting work me and my colleague Dimitri did around the advanced Pluto extension, which is a nice new way to work with notebooks. So before I dive in the VS Code extension, which will be a small part, let's try to answer, what is Pluto? What does everyone have in their minds when we talk about Pluto? Pluto is a notebook system, obviously, but let's break it down. So what is Pluto? So Panayotis loves you to use tight integration with VS Code. OK, that's not Pluto. But what is Pluto? Pluto is not only its user interface, right? I think the user interface has gotten the most discussion, whether it's dark mode or light mode, and whether the output is on top or the bottom. But in order for us to be discussing that thing, there is really a lot going on in the background. So Pluto is a system that manages the code, the status of a Julia process that is not in the browser, that captures the logs and the standard output and the standard error, that shows the HTML output and the running status. Right? I can repeat that. It's a lot of things. If you think to make this from the ground up, it's actually a lot of things. It's a lot of things going on. So Pluto is more than a notebook. It's a reactive execution engine, loved and hated. It has a robust remote protocol that actually captures all the aspects of what I just described. It does code analysis, and that is a lot of things, right? That's a lot of things. So why only have one way to interact with Pluto notebooks, right? Why stay in the HTML world? And one motivation for that is that the AI agents that everyone is using for the last 7 months, they can't really see, they are not native browser things, right? They are CLI things. So I'm going to rephrase this a bit, and I will say that Pluto is an ecosystem of Julia-related, web-friendly, I would even go to web-native tools, right? So let's let this sink for a bit. This is, but OK, isn't using Julia through the web an easy problem, solved one? Why do we care? We have HTTP.jl, right? We have Bonito. We have all these things. Why bother? So who thinks this is solved? Hands. No one. OK, we agree. Who thinks this is not solved? OK, more hands. Thank you. Thanks for the interaction. So it's a solved problem if you account for these things, right? Connections over the internet are ephemeral by default, and you should not have data leaks in your server. Julia sessions are ephemeral. Julia sessions die very often, out of memory is the usual one. We should be able to cancel something you send over the web, even though we should wait until 1.14 for that. You should secure your communications. You should not block when you send a request and Julia decides to precompile. I'm looking at you, MTK. You should know what the server is doing, like what the process is doing. That's really important over the web. Like people get bored in milliseconds, right? Cloud code is tinkering all the time. There is a reason it's tinkering and it's galloping and everything. We should efficiently render all the meme types we can think of, also not trivial, and we should be streaming logs, output, std error, std out, right? What I just described is not an evening project, even if you are Claude. It's a lot of things going on. So yeah, it's trivial. It's easy, if you account for these things. So how did we think to put Pluto on VS Code? So I was hanging out with Dmitry, who's a colleague on Julia Hub, and we were making Dyad Studio, and we were having all these problems. Like, look at this list. And I was like, yeah, we're just rebuilding Pluto, so why not bring Pluto in? And he was like, yeah, that's a great idea. Let's combine that with VS Code's Notebook API. And OK, how would we do that? And did we actually end up shipping this in Dyad Studio? No, but it was a great exercise to account for these things, which are important. And if you want to take something away from this talk, this is a list of things your web services that are based on Julia should account for. So yeah, we ship this mentally, I would say. So advanced VS Code extension, how did it come to be? This is a screenshot from the marketplace, by the way, and thank you for the thousands of downloads. So the main ingredient is a thing called Pluto.jl Rainbow. And what is Rainbow? Rainbow is Pluto's frontend bundled as a JavaScript library, right? And that's pretty much it, right? Instead of relying on the editor.html, which encodes all the logic, we extracted that logic and made it possible for a Node program or another website to use it, right? And VS Code is a Node program, so it can use it. How does the API look? I'm pretty sure that's illegible. But basically, you wrap a Pluto server and you create a worker, which is a notebook. And then there is some API for each one of the commands. More of that, like I won't insist too much on what the API looks like. It's for your agents to read. On top of that, the first thing we built, actually the second thing we built is a CLI, because it turns out that people don't live in VS Code either these days. Some people just live in their AI agents. And what is the best way for an agent to interact with anything? Probably a CLI. So npx at pluto.jl/CLI does help will teach your agent how to use it. So if you want to make a notebook, that's it. So I'm going to try to quickly show you the notebook. I'm not sure if that will work, but let's try to duplicate my screen. Am I still on the screen? No? Perfect. OK. Then I don't know how to do that. OK, so I will just go on this screen, and I will show you what my prompt to Claude was. I hope that shows. So I just asked Claude, let me see how that looks. It looks terrible. Great. OK. I asked Claude to, using npx pluto.jl/CLI, connect to my Pluto server and make me a nice notebook. And what did it do? Well, it made a nice notebook. You will have to believe me. But here is the notebook. Is it there? OK. So this is a notebook that Claude made only with that prompt. Is it scrolling? Perfect. Thank you for being my eyes. And that is basically and one shot from Claude. Like, Claude now knows how to build a notebook through the CLI. And what does the VS Code extension, that is the eponymous presentation, look like? Basically, let me see. So this is the native VS Code notebook API, the visualization of a notebook. The cells are pretty much the same as Jupyter cells. There is a terminal, which is basically a terminal connected to the Pluto state. And every time you evaluate something, what it does, it sends a new cell, evaluates the cell in the scope of the session, gives you the result in a way that you can actually play with it, and then it deletes the cell, because you never asked the cell to be there, right? So you cannot define things there. But all of the other, like everything else in the Notebook API that you expect from Jupyter notebooks is here, because the Notebook API is actually a good technology that VS Code has made to make these things work. So with the help of Pluto Rainbow, we took all the good parts out of Pluto, and basically we put a new face on it. And we also build a bridge to AI coding agents. And that's my talk.
All right. Do we have any questions from the audience?
No questions?
Actually, I had one. So what do you think you would do differently if you had to start sort of thinking about how to do this kind of integration from scratch, from now?
You mean without using the Pluto engine, or?
With basically tracking for the agent use, how would you actually make it such that those things can work more efficiently if you had to start from scratch?
I think that's a good question. I would start from this list. I don't know if you can see the list. Come on, PowerPoint. OK. Is it up? No. Anyway, I would start from the list that lists what you need a Julia process to be doing. Yeah, it's not helpful. So there is a small list up there. My computer doesn't help very much. But basically, the agent needs to know about the same things you do when you're running something. Like, is it stuck? Is it precompiling? If I press refresh, will it get stuck? What is the standard error? What is the standard output? Can I cancel it? Like, you would start the design from that list. And that's what I do. These are the primitives. These are the fundamentals. Everything else should go on top. And note that this is not opinionated on how you or an agent interacts with it. Right? This is the building blocks. Pluto is a lot of things that are behind the facade. The facade is very beautiful, and big thanks for all the style. But apart from that, there are real lessons about the architecture of wrapping a long-running process that may or may not behave very well. And that's Julia, right? OK. We have some questions. And is it up?
So why not just embed a browser window in VS Code and just use the normal notebook?
Yeah, that is actually a great question. We had that 4 or 5 years ago. The reason is because communication does not natively flow to the web view. The communication still needs to go through some APIs. And also, people don't really want, like if someone is in VS Code, they do not want the Pluto UI. They want their tools and their completion and the Julia language server, like everything you see on the Notebook API, it's still running all the VS Code integrations in it. So the code that VS Code shows you in the Notebook API gets checked by the Julia language server, and you can hover over it, and it will suggest, Copilot. No one wants that, but it would still do it. It's very integrated. Like the colors will be what you want, the font will be what you want, the size is the same as everything else.
So you're editing a Jupyter notebook, but you're doing it essentially in a VS Code native way as a text file.
Basically, I'm using the same renderer that VS Code uses to show Jupyter notebooks, but I plug the Pluto system behind it. That's it. And by the way, sliders and everything works on the notebook, right? So you can move the slider. Unfortunately, I could not show it, but have fun with it. That's all.
Okay, let's thank our speaker once more. All right, so our next talk is by Theo Galli-Fajou, and he's going to be talking, he works at Planting Space, and he's going to be talking about Test Picker, bringing modernity to Julia testing in the terminal. So let's welcome our speaker.
Hello. So same problem as everyone. What do you see? Yeah, but I don't see anything. Yeah, that's good. All right, so I want this in here. Oh, come on. Ah, here, okay. Here. No, you don't see. It's time. Sorry, here. Using Wayland is always a pleasure. Can I? Huh? Yeah. It's gone? Okay, now that's better. Here. So you see, do you see Google Slides now? Okay, great. Yes, thank you. Sorry for the delay. Hello, hello, hello. Welcome to this talk about testpicker.jl. I'm Theo Galli-Fajou, working at Planting Space. So a short word about Planting Space. We are a software company building a product which aims at basically building some kind of prompt system that represents knowledge and uncertainty. We basically do program synthesis based on people's queries by introducing concepts coming from category theory, graphs, but also Bayesian inference and other interesting aspects. Still a work in progress. We're getting there. But please check out our website. I have a recruiting slide at the end. But if you want to talk more about it, don't hesitate to come to me. So what's the topic? Testing. We already had a great talk by Mose earlier. Testing is a major part of any software engineer. And in our own workspace, we do have a lot of files, around more than 520. And as Mose also put it, test.jl is pretty good. You can run package.test, it's going to run everything. If you use Parallel Test Runner, it's even better. Test macros and its friend, test throws, they do their job. Like, there's nothing to complain about. And there's even like interesting stuff that keeps coming, like the let that allows you to create context to get more information, nested test sets, which are great to test different interfaces and all. Yeah, so it is a great thing. So the main problem that many people complain about, and you're going to find a lot of posts on Google about this, is that you cannot run a specific test set easily. The option is basically copy-pasting. Even if you use VS Code, it's virtually copy-pasting to your repo. So what are the problems? You might be in the wrong environment. If you want to have a project TOML specific to your test, you need to activate that first. maybe you need to first run some specific helper functions at the beginning of your file, or some dependencies. And if you want to run a block, like if you use a classic Shift-Enter, or whatever is your shortcut on VS Code, it might just run the top-level test set, which is not necessarily what you want. And of course, it was mentioned again, but we can have namespace splashes, polluted workspaces. Generally, it's not a good situation. There are solutions existing already, like testenv.jl and self-test sets, but they kind of focus on very specific problems and yeah, help only partially. So that's not a good situation. What was the other options? Again, a few were mentioned, like test items or retests. I talked with people, and the main gripe that people have is that you need to kind of refactor your test for this to work. And they have their own advantages and inconvenience, which can be generally a problem. So what is missing? Personally, I like to live in the terminal, especially in the REPL. The REPL is great. All hail the REPL. So how can we just run tests efficiently directly from there? So I got inspired by another package called Terminal Pager, which allows you to print any kind of massive data structure already this, and you can just iterate it like with using less from the Unix command line. So let's get a live demo. Okay, I'm going to get again another problem here. So I'm going to go here, 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 and here. Now what do you see? Nothing? That's not good. That's a light theme, yeah. But I don't see it, so I will bring it here. OK, this one here. Yeah, that's going to come. Just 1 second. And here. And here. OK, do you see a white test thing? Nice. All right, so I just made a quick demo package for this, toll picker. So now I just activated the package, and that's basically all you need to get all the information required. So what it's about. First, I'm going to place call exclamation mark, like your classic prompt trigger. And I'm in now test mode. What is test mode? Test mode allows you to basically type any kind of prompt, like a talk. And what this is going to do is going to look at all the test files that match via fuzzy finding this specific query. So here I have two, talk scheduling and talk submissions. Automatically, we see a preview on the side, which we can also just scroll a bit. And of course, the whole point of that is to run this file. So I press Enter. It's a rather short and fast test, but I see I get a bunch of failure. OK, that's already nice. It means I can, if I have 520 files, I can already quickly filter through without necessarily call a big like run, test, filter, equal, blah, blah, blah. It's kind of very efficient. If I want to run both, it's the same. I can just press Tab, select multiple ones, and press Enter. This is now going to run both tests. So far, it doesn't really, it's maybe practical, but it doesn't beat a quick include on a test file. Where it gets interesting is that you can also filter via the colon character for test set. So now I can run a specific test set part of this talk file. So it's basically, again, a fuzzy find on the files and then a fuzzy find on the test set names. OK, let's run this one. OK, this one also errors. That's good. And if I want to repeat running this thing, I can just press minus, kind of like CD minus, if people are familiar, which will just repeat the same action. So I can just quickly iterate, try to fix something, go back to my test mode, minus, again, and this kind of creates a very fast and efficient workflow. But that's not everything. So once I've let's run the first one again. Now run the whole test file. You see there's 2 failures and 3 errors. The test set results are actually captured. And I can now iterate through them and basically look at what happens. So this one was a test failure. This one had an error exception, and so on. OK, that's also nice. But the if you press enter on a failure, you can actually also iterate directly through the stack trace. Stack traces are notoriously hard to parse sometimes. So here we can basically view each stack element and see where it happened in the code at the same time. So here, OK, I see that I called square roots on something minus another thing. So maybe what I want to do is directly edit that, maybe with an absolute value, leave, wait that the language server is closing, maybe. Yeah, sorry. What I did was simply able to edit the file and just come back to my thing. So now I edited the source file. I can just simply rerun it. And I see that now I just have 4 failures. So this basically allows to kind of iterate back and forth between your test, your source, and quickly understand where the error comes from. If you might have noticed, there's also different colors to kind of identify. Blue is for source code, while orange is for a test code that belongs to your package. Right, that's it on this side. So what is needed for this? So you have like the usual suspects, testenv, Julia syntax, which allows to basically identify the test set. Something I forgot to mention, which is maybe the most important, you don't need to modify anything in your code. Like this is just an interface to the existing test.jl, so there's no specificity to it. How it runs, not through Julia. It's actually used this fzdef binary and the bat for the preview of all the files, all shipped as artifacts, so it's really easily portable. One only requirement is basically the self-test set requirement, which means that everything must be self-contained in the file. So all the using statements, all the helpers must be, you should be able to run the file as it is. And another important thing I didn't mention, which is I think the strongest part, is if you run a test set, it will run also everything before, which is not a test. So any preamble code that you might need for running this test will also be run at the same time. So you have this guarantee, almost guaranteed to work, unless your tests are mutating, which you should probably not do. It's also able to actually extend other things. I started to do naive support for test items, but it's still in progress. Yeah, and I've been experimenting also to kind of try to connect the AI train and connect it to some MCP server. But honestly, it's just like creating a new Julia session. So now what I recommend is just using some existing thing like this. Right. We're recruiting at Planting Space, so don't hesitate also to talk. Also in terms of everything we code is in Julia, so we welcome Julia developers. And that's it. Any questions?
All right. Do we have any questions from the audience?
Thanks for the talk. I just want to say that having your tests be self-contained is actually such a good thing. And I'm very glad that when I was working on Turing, we made everything self-contained so that we could use test picker. The real question, though, is when I type a name into the test picker mode, it'll bring up FZF, right? Is there a way to just say that I want to run this test with this exact name?
Right. So something I did not show is that there's also some auto-completion. And indeed, if you have one result, probably you want to run that. That's definitely something I want to implement at some point. Because yeah, if I this, it's like, do you really want this one? Yeah, exactly. Yeah.
Okay, so earlier we had another somewhat related talk by Mosé about the parallel test runner, and now of course I find both interesting. Can I use them together? I wonder. Do you have any insights?
I think I do want to bring parallelization. If you select multiple test files, makes sense. I have issue open if you're interested. But I think the use cases are quite different. The Perl test runner, we have something also in planning space like similar, and it's really meant for, I need, 40, 30 minutes of computations and, the heavy machinery. Here, I think the best use case is, you iterate through your test to fix things that you found, maybe via Perl test runner that reported that this file test are running or failed, and then you want to quickly iterate through them by looking at them. That's typically what I do, for example.
All right, let's thank our speaker once more. Our next talk is by Yanis Erdmanis. He is a full-stack Julia developer with a PhD in physics from TU Delft. And he's going to be talking about he's going to be talking about the Jumbo Julia distribution. So let's welcome our speaker.
Hello, everyone. So my name is Jan Erdmans, and today I'm presenting Jumbo Julia distribution. We are all familiar with the pain which comes from instantiating Julia projects in fresh Julia installations, especially when we depend on heavy packages like differential equations or Mackie GL. And this can happen in the classroom setting or in front of your supervisor, which makes it hard to justify using Julia to onboard new Julia users. So how can we actually solve this problem? So not waiting 7 minutes just to plot a Lorentz attractor. I mean, that's kind of ridiculous, right? So what if we would ship PKG images to our end users, and in particular, to make this problem trackable, what if we ship them just like Julia standard library PKG images? And that's what I'm doing here, using the app bundler project. We take a manifest file of the environment of the packages we want, and adds a tiny sprinkle of local preferences and pass it to app bundler, and we get our installation distribution. So the Jumbo is built like that, and what it includes is most commonly used packages, differential equations, Mackie, Jump, Enzyme, Reactant. So whatever I wished to add, I added. There are no once you install this distribution to on your machine, there is no compilation wait, so you can directly start using Mackie. It only costs load time for loading PKG image in the environment. And we currently offer, Jumbo is released in a MSIX format for Windows, DMG for Mac OS, and Snap format for Linux. And it's built entirely with App Bundler project. And the releases are available on the link below. So how Jumbo is built is that we have this local preferences file. We just say using App Bundler projects and specify option that we want a mainless option of the application. And we want whether adding pre-compilation cache to it. And that's basically it. And then we built it with Julia. And we built it in a reproducible way. So we want to maintain our distributions in a long time. So we reference App Bundler manifest files. So we know that the App Bundler doesn't change under the hood, which makes the life much easier in the long term. And that's about it. So let's go to the demo part. So let's see. Let's clear our terminal. So let's start our Jumbo distribution in a project file, in the Lorentz project. And what we have in the project we have some dependencies, as usual. It's just as Julia. We want to instantiate. It instantiates. Then we want to plot our Lorentz attractor. And now what happens is first it loads differential equations and MECI from PKG images. That's loaded. Now it's integrating ODE system. And the final part is building of the scene with a GL MECI, which takes a little bit more time. Let's wait a little to see it happen. And it happens. So that's a Lorentz attractor you can get by freshly installed Jumbo Julia distribution. So that's already significant improvement what we had with fresh Julia installation. And want to show another thing. So we have this manifest file. So we have manifest file created by the Jumbo distribution. You might expect to actually use Julia itself, for instance, to instantiate the project. But unfortunately, that doesn't work as expected. Perhaps that's something one can address in a hackathon project, since Julia versions are the same and the distribution just adds packages on top of it. So let's go back to the slides. So what Jumbo also includes is a custom startup file. So this custom startup file is necessary because it initializes base PKG origins, so it points to the right passes in the. So the distribution would be relocatable, and sets up a load pass, depot pass that's done at the runtime with a startup file placed within the distribution etc Julia that's at startup.gl. Then in the startup file also include revise and infiltrator, so the experience will be much nicer. So what are the challenges? So the first thing is that the Julia does not cross-compile. So every target, so how to solve this is, so every Julia distribution needs to be built on the target which you want to run this distribution. And to solve this issue, we use GitHub Actions, which already offers five different runners for Magier, Plotons, macOS, Windows, and Linux. And it takes about 2 hours per target to build, and the resulting products can be automatically added to the releases part of your repository. So and it works well. To build a distribution, we just go to the runner, build release assets, and just press a button, and we get our workflow started. Or we are also possible to initiate a new release, and the artifacts are going to be added once the build completes. So another challenge is that there are packages which lag with the compat bounds, for instance, and for instance, and this is harder to track because there might be indirect dependencies which hide the lag. And since we want since the latest and greatest is the greatest, so we would like to find them, and if we find them, what we would do. The question is, what would we do when it happens, the PRs, or perhaps the card perhaps evict them, so they would be so someone else would update them if they would want into the distribution, as they would get a resolver error there. Also, the problem for ordinary users is that the code signing is expensive, and also macOS notarization requires much more work, as the directory structure needs to be specified in a way, organized in a way that Apple accepts, and also code signing needs to be done in proper way, which is a bit like interacting with a black box and receiving errors from there. Also, Windows PFX certificates increasingly live on hardware modules. And this is going to be tackled with a bundler project in the future. But currently, the escape hatch is to use a car command with an installation script, which can download the DMG or MSIX and then bootstrap the trust, and then you can open the installer easily. So another issue is that some packages are not relocatable. I added recently Reactant, and it appears it has a hard-coded path, so that's something one can track on the hackathon. Another possible avenue is to ship jump distribution with a Julia app, and for that we need three things. We need a Julia app database package, so one could append new releases programmatically. We need compatible images coming from app bundlers, so the app bundler emits a tar.gc, which Julia app accepts. And then we need a bit of glue code. So the database that database can be hosted on GitHub pages and updated when the build matrix finishes. And we could point the releases to the versions we can point to the GitHub releases pages. So one wouldn't need to have some special infrastructure just using GitHub, and one can simply fork the Jumbo repository if they want different kind of set of packages for their setting where they want to use it. Another thing is convergence with the diet distribution workflow. Seems like it could be something to track. There's also Julia distribution workflow. Perhaps it can be, perhaps there is something which could be done in that direction. And then there is the work with the app bundler itself to restructure it so that the tarballs kind of are the primary targets, and that the MSIX DMGs or snap packages can be repackaged from the tarballs. So that's a new idea I have been thinking about recently. So to try it, download it from Jumbo releases page, or you can build your own using App Bundler project. Select your own packages you want in the environment only with a manifest file. Help is wanted as we saw with the challenges. I believe there is a macOS notarization pipeline, which is going to be difficult, probably. Well, the packages with the stale, compact bounds, and reactant seems could be added with the Jumbo distribution as well. So thank you for your attention. Now I can take questions.
All right. Do we have any questions for Yanis?
Hi. Thank you for your talk. I think it's really important, and also for students, like you mentioned. And I wonder if PKG understands this. So if you create an environment, does PKG understand that the versions are pinned? And what happens if you update or add packages?
Yeah, I forgot to add this thing. So you can actually start the project, and for instance, it works that you can, for instance, quantum optics. You can add packages on top, and they will resolve fine. So yeah, that's the important point.
But beware of all the sharp edges. There are many. If anybody ever yanks a package that's in a system image, you're out of luck. And it happens.
Yeah, but these are package images, so.
That's fair. One thing I was wondering, you were talking about signing and proposing spinning up your own sort of signing infrastructure. But if you use a Raspberry Pi for that, I mean, you're effectively still, you need the root certificate of, like a certificate authority. Have you, I imagine it's not that simple as being more of like an open source, from an open source perspective, but have you considered using like AWS provides, or yeah, AWS, I think.
Yeah, so I'm looking at the certificate providers, certification authorities, which are the cheapest. So,
yeah, just for what it's worth, that's what we do.
Yeah, okay.
All right, let's thank our speaker once more. Our next talk is by the Julia Gender Inclusive, Initiatives to Create a More Welcoming Community. Yes. So let's welcome our speaker.
You don't have to get all near my hair. Thank you. Okay. So, hi everyone. So unfortunately, our two speakers were not able to make JuliaCon this year, so I am neither of the two people listed on this slide. But nevertheless, we did want to allow the Julia GI talk to go forward, so I hope you'll bear with me replacing them for the next 15 minutes. And at the end, we'll have a way to get in touch with you since they are the experts on what Julia GI is doing. But with that, we wanted to talk a little bit about diversity and inclusion efforts in the Julia community, especially as it relates to people whose gender is underrepresented in our community. So we're going to talk a little bit about the various activities and opportunities that the organization Julia Gender Inclusive is involved in and organizing. There's a range of things that the org is doing, from virtual coffee meetups, so you can participate if you're anywhere in the world, to hackathons, funding of opportunities to allow people to travel to JuliaCon, and also there's a call for volunteers. So what is Julia Gender Inclusive? If you haven't heard about it, it's an initiative to promote gender diversity and inclusion within the wider Julia community. This is obviously a work in progress for our community, and it's something we've been discussing over a long period of time. So the organization was created to try and sort of provide like a meeting ground for anybody in the Julia community who sees their gender as underrepresented. And since this is sort of a multifaceted process, it's really sort of, I guess, something that we want to maintain the openness, and we want people with a variety of gender identities and presentations to feel welcome. So if you're interested, we have a website, juliagenderinclusive.github.io. And we also have a logo and stickers. I think the registration desk still has stickers. If you're interested in getting a Julia GI sticker, it's the one with the little umbrella, and it can be used also by people who are not members of Julia GI or who don't feel that their gender is underrepresented. So one thing that the community has been doing, one piece of feedback that we've gotten over the years is that sometimes, obviously not in every case, people who are underrepresented in Julia don't feel as confident in their Julia skills, and they want an onboarding process to learn Julia that is maybe a little bit less overwhelming, or involves other people who are new and underrepresented. And so there's this also initiative that the group has been doing, Learn Julia with Us. There's a tiny URL at the bottom here. I hope the font size is big enough for people to see. And we'll also hopefully post these slides later so you can see the URL. But if that's something that interests you, obviously you're welcome to participate. Also, in the past, we've had some hackathons. Some of these have been entirely online. So again, no matter where you're located, something that folks can participate in. One other piece of feedback that I think we've gotten in the past is that it can often be the case that in someone's physical location, they're the only underrepresented person. And so having a hackathon where folks can connect, you know, if they feel that their gender is underrepresented, can be valuable for folks. So this is also something that's on the website. And in general, that's where events like this are advertised and organized. So if you're interested in participating in a future one, definitely check it out. It's also sort of something I think in the past has kind of happened in response to user demand. So if there's a signal from folks that they would like to have a hackathon under the umbrella of Julia GI, then getting in touch with people so that we know how and when to organize it obviously is helpful. One other initiative that the community has been launching is, so anybody who was a participant in the JuliaCons during the COVID era probably remembers GatherTown, which is a free sort of like chat platform where you can make a little avatar. And then if you're located close to another person in the virtual world of GatherTown, you can choose to have like basically a sort of shared AV call. So there's like your camera and your microphone. And so we've had sort of community meetups or community hangs in the Julia GI GatherTown. I don't think we've settled exactly on when the next one is going to be or who is maybe going to be a speaker. But also, you're probably going to be tired of hearing me say this. All the information's on the website. So if you're interested in participating, definitely keep your eyes open for that. And in general, Julia GI sort of has a bunch of these different activities, kind of a summary here. So we have this long series that are actually all available on YouTube and might be restarted. And then we've had these day-long hackathons and also the community hours. I also think it's kind of cool that indeed, like the hackathon, which I think didn't have that many people, did result in some PRs. Having participated in many hackathons myself, this is like way more productive than most of mine usually are. So. And if you're interested in participating and you see your gender is underrepresented, some good ways to do that are to join the next community hour, which again, we're going to decide the time on relatively soon. And the main venue folks use for communication is a Slack workspace. So there's a URL here that I won't ask you to actually like write down. So the reason we have a form is just to ask some folks to fill out a few simple questions, just to make sure that everyone who's participating knows what Julia GI is. And in general, we just want to emphasize that we hope folks will join. We would like to meet other people in the community who see themselves as underrepresented and share ideas on how to improve gender diversity in the community, support people whose gender is underrepresented, and provide more opportunities for people who would self-describe that way. So if you're interested to join the Slack, there's this very large QR code that hopefully is scannable even from the back of the room. So this will lead you to the Google form that then leads to the Slack. And again, if you feel that your gender is underrepresented and you want to hang out with other people who feel the same way, you're more than welcome to follow through. And this ran a little short. Again, I apologize that it's short. We kind of got drafted last minute into presenting. So if you have more questions about the organization or what they're doing, I think both Letitia and Feruza are available on Slack. And I can also take any questions here now. That's it.
All right. Thanks, Katie, for the amazing talk on the importance of gender inclusivity in the Julia community. Do we have any questions from the audience?
Oh, on the left.
In what kind of ways can people support your community?
So, I mean, one way, again, I don't want to make it sound like if you feel that you're underrepresented in terms of gender in the community, you have to join, but certainly that would be one way. If you don't feel that way, sharing Julia GI events, letting people know that the community exists, sharing ideas you might have for how to increase inclusivity. Let's see. I think also, I mean, just in general, you know, promoting the atmosphere that this is an important topic, that it's something that the Julia community cares about. And I think also one thing that's nice about Julia GI is, like, as I kept saying, it's like kind of transnational. Like people from all over are participating, but then in more local meetups, there's also a lot of opportunities there to promote folks who are not necessarily equally represented in the community. So if you're interested in discussing how to do that, that might also be a better topic for not like yelling at the entire room, but it would probably be a good discussion to have.
Okay, good, thank you.
Any other questions? If not, let's thank Katie once more. All right, that brings us to the end of this track. Thank you everyone for attending, and thank you to all the speakers for their talks. We will have a short break, but please do join us for the keynote that's also happening over here. Thank you.
Good afternoon, good afternoon. Welcome to the final talk of JuliaCon Global 2026. I'm very excited about this year's State of the Julia. And most of these people don't need any introductions, but I will give them anyways. We have with us today Jeff Besançon, one of the original creators of Julia, Keno Fischer, long-term core contributor, and Tim Hawley, general, madman in the ecosystem. The stage is yours, folks.
Sorry?
Is this on?
Yeah.
Mine's not on.
Oh, can we get the other microphone?
Hello? Hello, test. Okay, great, thank you. All right, hello, JuliaCon. I hope it's hot enough for you. Is it enough? Is it enough? All right, welcome to State of Julia. So we like to do this with a changing and rotating cast of performers. So Tim and I are returning after a few years of hiatus. Keno did this last year, so we may normally have had someone else, but we really, really needed him this year for reasons that will become clear. But if you want to do this, if you like keeping your finger on the pulse of the language and everything in the ecosystem, and you want to do this, it's a possibility. So reach out. And with that, I will turn it over to Keno.
All right, excellent. Welcome to the sauna, everybody. Thanks for being with us. It is my great pleasure to announce that Julia 1.13 RC3 is finally released. Now, you might be wondering, RC3, didn't RC2 release 2 days ago? And yes, it did. But we are back, and we are on a roll with RCs. Now, as you can see, it did take us 107 days to release RC2 since RC1. So I thought we would start off with a little bit of an apology and an explanation for what happened. So what happened, we had some CI troubles, as those of you who follow the discourse might have seen. In particular, some security researchers assisted with some AI models, did some exploration and found some compromises in CI systems for a bunch of languages, including us and Go and Python and Flutter. And as a result of that, we had to basically, on short order, rebuild our entire CI system with more robust secret management. But as part of that, we also had to rebuild images and compiler binaries. Needed to be upgraded because the version that was running on CI wasn't supported anymore, and that needed bug fixes, and it sort of spiraled into a whole thing. But as you can see, we can make releases again. So very happy, and if you want details of that, there'll be a write-up, but there's also a Black Hat talk by the researchers that discovered this if you want the real nitty-gritty. We had some more CI troubles. As you may know, we run package eval. We test all of your packages with every release to make sure that the releases are good. That used to run on one machine at MIT. That machine died, so we couldn't run that for a while. But brave new world, we vibe coded a new one that runs on AWS Spot and has a bunch of extra nice features, including a dashboard. So if you submit a package eval job, you can now see where it is in the queue. So hopefully we're 98% back on CI and can start making releases again.
Wait a minute. I love how Julian suggested to fix this by reseating an SSD. It's like all along the fix for Julia CI was to take out the cartridge and blow on it. It's great. It's great. Oh, okay. So aside from that, though, we had a really, really big year for new features and bug fixes. There's really a lot of stuff. So Julia lowering now basically works. We're going to have much better location info. A lot of latency and compiler performance improvements. We have robust cancellation, so now Control-C will finally actually work reliably. Labeled blocks, mutually recursive structs, @threads works on comprehensions. Selectable syntax versions, so you can use old versions of the syntax if you need to. And this is kind of a small one, but I actually really like it. This was done by Max Horn, odd bit size primitive types. So we have these primitive types, but previously you had to pick a number of bits that was a multiple of 8. And so it's just really nice to have that feature feel, just complete in general, and now you can have whatever number of bits you want. So I find that satisfying, small though it may be. There's a lot of progress on GC. There were some long-standing type system issues that have been fixed. And now we can also infer the task result type. So the way task works, we've never been able to infer its result type, which was kind of a glaring gap in type inference, and that has at long last been fixed, so that's pretty good. And we've done several LLVM version upgrades. which give a lot of improvements. I understand the vectorizer is supposedly a lot better now. So some of these things are kind of self-explanatory, and they're just sort of one-liners. But for some of them, we're going to drill down and go into some more details. So here's what you can look forward to soon. So this is available on a branch. It hasn't landed yet, but it's going to be real soon now. So I'm just stealing one of M's slides here. So as you can see, in the near future, you will have column numbers in addition to just line numbers. And of course, and you can also see that we can underline the particular sub-expression or argument on the line that led to the error, not just the vague line that it was on. So this is one of these things where it's like there's a gigantic iceberg underneath. To get that one little column number on there, it's just get those 2 digits on the screen. Takes this just gigantic amount of infrastructure to plumb that information from the source all the way through the compiler. So that's finally been done, which is absolutely great. So we've had Julia syntax, which is the Julia implementation of parsing, for quite a while, done by Claire Foster. The lowering, which is the next stage of the compiler, which is kind of semantic analysis, is way more complex and difficult. And it's just much more complex. And it's also not just a matter of taking the existing code and rewriting it in a different language and just translating it, because it needed a redesign as well, because we needed to be able to do way more things with it. So it was a big project. But what this amounts to is that pretty soon you will be running Julia, and there will be no femtolisp, and there will be no scheme running, which is very sad. But I can handle it. And we expect this to have lots of benefits for tooling like Revise, JetLS, interpreter, debuggers, it goes on. So this is hopefully going to be really helpful.
All right, I'm going to talk about a topic near and dear to my heart, which is latency. It remains one of the sort of areas that is most frequently mentioned as a point of concern about the use of Julia. So we thought we'd give a bit of an update on this. So many of you know, I think in terms of latency, the high watermark was the Julia 1.10 release, and we've actually seen some worsening in recent releases. And so there's been a lot of interesting stuff going on, and we're going to sort of walk you through that. So there's been major work. So the thing that ultimately sets the experience is how fast the compiler is, right? And everything else is, other than speeding up the compiler, is a workaround around the fact that compilation is just an extremely expensive operation and takes some time, right? So anything that speeds up the compiler, makes it better, is a big win for everybody. And so this year has seen an enormous amount of work on the compiler. Kano has landed something like 20 PRs just addressing sort of type system issues, and he's going to sort of highlight a couple of nuggets from that, but it's a much larger pool of things than we have time to cover here. There have been 2 major LLVM version bumps and 1 more in the queue. There have been a ton of inference and code gen improvements contributed by a whole sort of, cast of people. One that I want to highlight in particular, because I think a lot of us think it accounts for some really exciting things, is some work by Sam Schweigel, in which he set up a way to cache the output of LLVM. So our compilation pipeline after the lowering, which you heard about with Julia lowering, there's a type inference stage, and then there's an optimization stage, and then we pass off to LLVM. And so we generate LLVM IR, as it's called, the language with which you talk to LLVM. And LLVM chugs and chugs and chugs and chugs and chugs and spits out optimized code at the end of that. And what Sam has set up is essentially a database for the result of that. And what we now have the capability of doing is computing what is the IR that we would like to pass to LLVM, what are all the flags that would affect the way in which that gets compiled, and if there's a match to that in the database, we just pull the result out of the database. And so the consequence is that time to first execution is no longer the only metric of interest. Also, time to second execution in a fresh session after you've deleted the precompile file is also a relevant metric. And so as an example shown here, if you take a blank machine and you install Julia on it and you install plots and you compile it for the first time, it might take, say, something like 44 seconds. And then if you wipe all of the package images out of your .julia directory and recompile everything from scratch the second time, it might take only about 36 seconds. And that's because because of this work of caching the output of LLVM on there. So that's a really exciting, set of change. Other things that affect the sort of latency experience in practice are things like the amount of time it takes to load packages, the invalidation. So when you are bringing in streams of two isolated branches of code and bringing them into a common session, because of some aggressive optimization that Julia does, we sometimes have to throw away compiled code and generate fresh compiled code. That's what invalidation is about. And then pre-compilation, when we save the results of compiling a package to disk so that you don't have to wait as long to use it in the future. So there have been several changes, maybe somewhat fewer, that affect this area. One of them is a set of body work I'm extremely excited about because I think it's going to be really transformational when it gets finished, and that is the ability for us to recognize that when you invalidate one thing, it may not need to propagate all the way outward to everything that calls it. And that's sort of deciding that there's an equivalence between, again, something you've generated previously and the ability to relink a copy that's essentially just change all the pointers, basically. And so at least a few steps in that direction have been taken this year. There's a long ways to go before that can land. There are also some more focused changes and all this kind of thing, and it's particularly with regards to how abstractly, the results of abstract inference work, and for certain workloads, especially those that are, for instance, broadcast heavy, there are noticeable speed ups. And Ian Butterworth has tamed the thread conflicts in parallel package precompilation so that the different workers don't get in each other's way nearly so much. And so this is a graph that I believe was generated by Ian Butterworth that sort of shows a summary. It's a bit of a busy thing. Let me walk you through it. I would say that the two cleanest panels are the middle and the one that's on your right. And that the middle one measures just pure load time. How long does it take to load? And what you'll see, much to your delight, hopefully, is that the upcoming 1.13 release is about 5% faster on load times, which is great. There's a very concerning large regression on master, but do keep in mind that master has not been performance optimized in the way that something that's getting ready for release undergoes, right? So we don't know where that's coming from currently. We don't know whether it's fixable, but it's not something to get too concerned about yet.
Also note it's a log scale.
Yeah, this is a log scale, right, exactly. So on the right-hand side, what you can see is the amount of time that it takes to actually execute just the workload, ignoring all of the time to load the packages. And what you can see here is the extraordinary result that, in fact, it's cut in less than half of what it was in the 1.10 era, okay? So if you combine these two in terms of nightly, some current regression in load time and some significant speed up in the actual compilation and execution of a script, you get us basically back to where we were in the 1.10 days. That alone is great. If we manage to also fix the load time regression, then I am really looking forward to 1.14. So when Jeff asked me to participate in this, I said, I'd love to, but I've sort of been sitting a little more on the sidelines in recent Julia development. Other people have done all the work. And he said, well, I'd value your experienced but outside perspective. And so I'm here to tell you, as a person who cares a lot about latency and who hasn't really done any of these, that I'm more excited about the 1.14 release than I have since we got package images. So I think this is, all the developers who've done this deserve a huge round of applause.
Okay, so I want to drill down on GC just a little bit. So there was one good change by Cody to avoid scanning system image objects. So especially if you have a big system image, GC should generally be faster now. And also, for a few years, we have been collaborating with this project called MMTK, the Memory Management Toolkit, out of ANU. And so they have this suite of garbage collectors written in Rust, which are, some of them are the, pretty much cutting edge, top-of-the-line GCs, and their intent is to have them be reusable and used by multiple languages. So we've been working with them to do Julia bindings so Julia can take advantage of them. And now, just recently, this project has kind of gotten to a kind of exciting point where it's starting to sort of work. And we have 3 of their collectors actually working. The one that's most interesting to me is the concurrent collector, because it has the promise of giving you a low latency GC. And that's of interest to many people in the Julia world who want to do things like controls software. So There's a lot of numbers here, but the most interesting one to me that I highlighted is the P99, which is the 99th percentile pause time. So that means 99% of pauses are that or smaller. And so you see the stock GC, which is our current one, all the way on the right, there's some kind of big numbers there. It's a little bit worrying, in fact. Those are pretty big pause times, but those, only a small fraction of pauses are actually that long. Most of them are actually less. And you can also see on the left that our stock, our RGC is typically is faster end to end, but the concurrent collector puts up some very amazing 99th percentile pause times that are generally much, much lower. So that's very promising so far. There's one outlier in there that's kind of big. Well, that's going to be upcoming performance work. We'll probably be digging into that. But yeah, this is fairly close. So we're really starting to get there with this. And you can actually try it now. This is on master. And to enable it, you just need to set to build environment variables with third-party GC equals MMTK, and MMTK plan equals concurrent IMIX to try the concurrent one, which I think is the interesting one. But there are a couple other options as well. But, so it's ready to try if you want.
OK. Now to get to a feature that I promised last State of Julia. And very happy that we managed to do that. As always, all promises of future features come without guarantee, but this one we did manage to do. So the basic idea is that we would like to keep improving the syntax of Julia, but we are obviously not in a world anymore where we can just arbitrarily change the syntax. So what do? Well, we now have a feature where newer versions of Julia can run different versions of the Julia syntax for different packages. So, for example, in Julia 1.13, there is a bug or a misfeature, or people are fighting about whether we should have just fixed this. But regardless, you can go to out of a try finally and thus bypass the finally clause. And this obviously is a little bit uncomfortable because finally is supposed to be guaranteed, and in this case it's not. So in Julia 1.14, that becomes an error. But if your package did not opt into Julia 1.14 syntax, thus staying on Julia 1.13 syntax, this does not become an error. It just keeps working as it did in prior syntax versions. So I said it has to opt in. So how does it opt in? In your project.toml, there is a new key called syntax.julia-version. Which you can explicitly set to 1.13 if you want to keep that. You can explicitly set it to 1.14 if you want to opt in. And it's also tied to the Julia compat. So if you're upgrading anyway and need some new Julia 1.14 feature, then by default, you are going to get Julia 1.14 syntax, although you could explicitly overwrite that and go with an older syntax. The idea behind that is that we would like everybody to eventually upgrade to the new syntax so that we don't diverge the package ecosystem into n different versions, but sort of provide this mechanism to let you upgrade at your own pace. So this is more of an evolution mechanism than us wanting to maintain 10 different language versions at the same time. But this is how it works. And in particular, all of the new syntax features that I'm going to talk about, including type group, are gated behind Julia 1.14 syntax opt-in. So if you have the REPL, you just get it automatically because the REPL always opts into newest syntax. If you want to use it in a package, you need to put the compat on there, which you probably need to do anyway, since if you run it in 1.13, the feature doesn't exist, so it's going to crash. But OK, so let's talk about these new features. This is one that I've wanted for a really long time. As just a general annoyance, but also it's very helpful for modeling object hierarchies in other systems, like WebAssembly, like some of the serialization formats like protobuf, Captain Proto, and so forth, where they have mutually recursive struct definitions, and that now works. So we have a new top-level syntax feature called a type group, and all the structs that you define within that type group, their names become available for field type declarations. So you can say something like, in this example, a node has a bunch of edges, and each of those, the edges is a vector of edge, and edge is itself, has a bunch of nodes in it. So that
that now works. And it also fixes a bunch of crashes. So you could sort of do some of these things before, but the system doesn't really support it. So it's not just syntax, it's also making this well-defined. But yeah, OK. Next syntax feature is labeled blocks and break with value. So again, one of those long requested syntax features. What happens if you want to break out of multiple for loops, or what happens if you have some sort of search loop and want to say, OK, hey, I found this value, please give it to me. Obviously, you could do this with variables and flags and checking them. But it's much nicer to just say, hey, I want to break out of these blocks. There was a lot of discussion about how we want to do this. Do we want to have break? Do we want to have break with a number? But what we ended up settling on is that you can label arbitrary blocks, including for loops, including just begin end blocks. And then we have new syntax for break with a label. And whatever the label is, break will break out of the blocks to that label. So nothing special there. The second part of the new syntax is break with value. And they sort of go hand in hand. But whatever block it's breaking out of, the second argument is the value that that block will take if you break out of it. And this also obviously works with regular for loops. You just have to say it's the default label, which is just represented as underscore.
Oh, yeah, so this one. There's two kinds of bugs that get fixed, right? Ones that are easy to fix and ones that are really, really important. But the ones that don't get fixed are ones that are kind of tricky and only not that important. So this is in that category. And just recently, it has become much easier to fix bugs of this kind. And I'll give you one guess why that might be. But so this is something that's been an annoyance for many, many years. So we have this, as you know, you've probably all used it. It's the capital T type curly to specify a particular typed value. But that has sort of two jobs. It does that, but it's also, bizarrely, the super type of data type and other type kinds. And what's worse, the super type, the type variable in there is a free variable, which is just very bizarre. It's not even a well-formed type. It's just very strange. So this is a historical artifact. It's just very weird, very unsatisfying and ugly thing to have in the system. So this has finally been fixed. So now the super type of data type and the other kinds is this new type, any type. Pretty much tells you that you've got any type. We don't know which one. Name works. And now when you do type int, you get a new thing called type EQ, meant to evoke that it's the type of types equal to int. So the syntax still works, of course, but the underlying name has sort of changed. So this has now been cleaned up, and this is all very nice.
Excellent. OK. Now, this is a feature I've wanted for like 15 years. So I'm very excited about it. But the headline feature here is that Control-C is now supposed to work. And it's supposed to work the first time, and it's supposed to work immediately. Thank you. Thank you. So this has lots of details. This is, again, one of those things that is very simple description and tens of thousands of lines under the hood to actually make this work. But one thing I want to say is that it's cooperative cancellation. So cancellation only happens at well-defined points. Various functions in base will have those points, in particular anything that does I/O, some things that do particularly heavy computation, like matrix multiply, like big int operations. But if you're writing a package that does some sort of heavy numerics, you may need to insert explicit cancellation points at points somewhere in the middle of your heavy numeric loops. Don't put them right in the inner loops. I mean, we do our best to try to optimize it, so it should be OK. But it implies some bookkeeping. So put them somewhere in the middle. If it's executed every 100 milliseconds, that's perfectly fine. But yeah, it is cooperative, and there is the base.add_cancel_check macro that supports this. There's lots of details. What happens if you want to cancel an external C library, and what happens if that external C library doesn't support cancellation. And it's all kinds of details which are in the manual. But yeah, the headline announcement is if Control-C doesn't work, we now consider that a bug. Before, it was just sort of, OK, we tried to cancel it, and if it didn't work and crashed your process or hung or whatever, couldn't do anything about it. But now it's a bug. It might be a bug in base, might be a bug in the cancellation system, might be missing cancel checks in packages. But when 1.14 is released and Control-C doesn't work for you, please feel free to file that as a bug.
Oh, and this feature is actually kind of arriving in stages. So in 1.13, there are already some fixes around this. So 1.13 should actually be better already. And then 1.14 has the full cancellation system. And then there's another round of planned improvements to make it even better that are coming later.
Yeah, I think those will probably be in 1.14, so I hope it'll be complete in 1.14. But yes, this particular example, 1.13, should be better. Some other examples won't work in 1.13, but 1.14 is the version that you can start filing bugs against. Okay, oops.
All right, so one of the other sort of, I think, really important areas and potential sort of future growth areas for Julia is the ability to deploy applications and shared libraries. So there was a talk earlier this week from Jeff, Gabriel, and Cody on Julia C and the trim feature. That's about building, by and large, well, it's the foundation that underlies, trim is the foundation that underlies everything. Julia C is a package that helps you essentially deploy complete applications as small compact binaries. There have been a couple of features added that are going to also help other consumers, like private Julia runtimes, and the application deployment, like bundling and pruning native dependencies and static linking. And there was this JuliaCon talk on that. I highly encourage you to go look at that if you want any more details on that. I'm also going to say that those of us who want to deploy isolated libraries to our colleagues who are using other programming languages, that is getting a lot better as of Tuesday. And that is that with the release of 1.13 RC2, which had some critical fixes to the way standard libraries were handled, I'm pleased to announce the release of Julia lib wrapping. And what this is designed to do is to take a Julia package that you've set up the trimming entry points into, and again, that's something you should go and learn about if you want to do this. It will generate the information that needs to be generated to and create the shared object library, but it will also generate information that is needed to create a nice wrapper. And so, currently the only polished target is Python, but I have done this now in real life, and the documentation contains a non-trivial example of creating a Python package that is using compiled code that was compiled from a Julia implementation. So if you want your work to be more publicly visible, I encourage you to see that. Now, there's one very important limitation. For the time being, you can essentially only have your Python friends use one Julia package at a time, but this private Julia runtimes is...
That fixes it, yeah.
And is that in 1.13? I'm actually forgetting. Or is that only upcoming in 1.14?
Do you remember? It's in 1.13.
Oh, it's in 1.13.
Thank you.
Never mind. You can tell your Python colleagues to go nuts and load all of SciML into Python. So,
okay. Yeah, I want to highlight another great development in the ecosystem that I feel helps a lot with the maturity of the platform, which is this new package, securityadvisories.jl by Matt Bauman. He had a talk on it. So this is a package that's basically a database of security advisories, like CVEs that are known against Julia packages or Julia. So it's got a whole database of them, and it has a companion website, security.julialang.org, that gives a convenient interface for browsing them, searching by package, severity, et cetera. So this is a really nice resource to have, to make sure you're keeping on top of these things, and we respond to these things. So this is a really nice development.
Okay, sort of continuing on the security track, there's been obviously a huge increase in AI-driven security reports. I think if you're not maintaining a big package, this is going on a little bit behind the scenes, so I thought I'd sort of give an example. Here on June 8th, email from Anthropic, hello, we've run our new model against your packages. Please see attached, here's 155 security vulnerabilities you might want to check. And oh, by the way, our new model is releasing Tuesday. So, good luck. So they've gotten a little bit better about it. so they don't send quite as many duplicates anymore, but obviously the Julia security team looks at each and every one of these, and in this case, we identified of the 155, some duplicates, some that we considered bugs, but not security vulnerabilities, but in the end, we allocated 16 real security advisories in this database that Jeff just mentioned, addressed them, put out a new HTTP.jl version to fix those. HTTP.jl, there was one in package and one in Julia up or something like that. But yeah, so this has been sort of going on behind the scenes. I thought I'd give you a little bit of a taste. Still going on, so we've been very busy, in addition to the CI issues mentioned earlier. But obviously, we want to make sure that the Julia ecosystem is well secured in this brave new world. And hopefully, we are continuing to be able to do that. OK, so it's been a weird year in general with all of this AI stuff, right? So last year, we sort of very last minute added a slide. Hey, we should maybe talk about this AI thing that's happening, starting to become kind of something that people use. And yeah, it's something that people use. So this is a graph of Julia pull requests and which AI model it discloses to have used. So if you used one and you didn't disclose it, we didn't try to figure that out. But on this graph, the sort of orangey colors are Claude, the blue colors are Codex, and then the remaining colors don't really matter. But as you can see, we are mostly a Claude shop, apparently, with the exception of that 3-week period where Fable was banned when everybody switched to GPT 5.5. But as a result of that, Claude, according to our GitHub contributor metrics, is the biggest contributor. Whether you count that or not, a little bit up in the air. But I think what really viscerally drives home that there has been a phase change in how software is developed is the second graph, which is of the merged PRs, what percentage of them has an AI attribution. And you can see in the past 2 weeks, it's been sort of like 85 to 88% of merged PRs have AI assistance. But overall, there has been a very steady upwards trend to about 60% in the trailing 4-week average.
Well, at least we know the second graph's not going to go up anymore, because it's already at 90%. So that's leveled off.
Excellent. OK, so given this development, I thought we needed to spend some time talking about it. That said, not everybody agrees on where things are going, on where things are. So this section is very explicitly my personal thinking. I am not necessarily representing the opinions of the project. But I did want to talk about it because I think it's affecting the way that we're writing software. So as you probably know, I am heavily using these things. I pulled my Claude usage this morning, and at API prices, sort of since June-ish, I've used $45,000 worth of tokens. Now, I didn't pay for that. I have subscriptions. But I use these things heavily. So that is where I'm coming from. I find these very useful. But I do think that we've reached the point where they're unambiguously helpful tools. And I think we've reached the point where if I see a PR that somebody hasn't at least run through an LLM and done an initial review, that might indicate that there's still some bugs to be found there. These tools have become unambiguously helpful. That wasn't true 4 months ago. I think this has sort of or in my personal opinion, it's become true with Fable and with GPT 5.6. So it's just become true. That said, even the frontier models still make a lot of mistakes. And worse, they make very subtle mistakes. So we need to be very careful in PRs that come in, even if they look beautifully done and fix a real issue. And the person who did it is very excited, myself included. The PR might still be wrong. So we have to figure out how to use these things effectively without letting them completely take over the code base. Another thing that makes this tricky is that the capabilities are evolving so quickly. I think the rough recommendation that I have is like every 2 months, you need to completely relearn what these tools are capable of because of how quickly these models are evolving. And I think that's certainly been true over the past year. Now, one thing I said last year that I think has not turned out to be true is that I don't think we have yet needed to do AI-specific modifications to our tools. And we have not yet had to do like fine-tuning environments for specific Julia application workflows. I thought that would be something that would become important. I think the general pace of improvements of the generic models has outpaced that as a useful thing. That said, one workflow that several people in the Julia committer ecosystem have found useful is to ground these models in formal methods. So most successful among those have been using TLA+, which is a verification system for state machines. So you can use it for things like weak memory orders and distributed computing protocols. So on the left-hand side, this is something that's actually checked into the Julia base repository, where Ian Butterworth did some fixes to our scheduler wake-up protocol and asked Claude to generate one of those TLA+ proofs. Didn't look at it, but it helped ground the work of the agent to make sure that what it was doing was actually correct. And on the right-hand side is a bug in the Linux kernel that I found while working on our obj cache. I said to Claude, hey, make sure our obj cache is good with all of the interleavings. And it said, yes, it's good, but there's a bug in the Linux kernel. Would you like me to fix that for you? So we fixed that also. So coming to a Linux kernel near you. But I'm not here to give any prescriptions, but I think this is something, if I'm making another guess, I think this is something that we'll see a lot more of over the next year. I'll tell you, next state of Julia, whether that was accurate. OK, those are sort of the technical points. I do briefly want to talk about the community points, because I do think it's a very weird time. I mean, I started this with saying it's been a weird year. I still think it's a weird time. I think it's weird for all of us. I mean, the way we're doing software is changing. I can't tell you what software will look like a year from now. I can't even tell you what it'll look like 6 months from now. Yeah, so it's weird for all of us. Different people still have different preferences, different levels of comfort, different levels of annoyances with the way that Claude talks, which is very annoying. But I think it's been mentioned in the previous keynote, we are here to get things done. And unambiguously, these tools help us get things done. So I think we have to figure out, as a community and as a project, how do we use these tools effectively without getting so annoyed? So, and I think we do have to do this, because if we don't, there's plenty of people who get less annoyed by it, and they'll write Julia 2.0 without us if we don't figure out how to do this. And that was us 15 years ago. Everybody else was moving too slowly. We want to create something new. I'm hoping that as things are changing now, we as a community are able to embrace the changing tides and are able to use these tools. And I just wanted to say that I understand everybody who's feeling uncomfortable, but I also want to encourage people to engage with this, to figure out, OK, where are these tools helpful? What can they do? So I thought to myself, OK, how can I make this point a little bit more punchy? So I have decided to award the inaugural annual Julia Dev AI Tool Prize to our most active contributor, Claude. If you want your AI model to be here next year, release a better AI model and we'll use it. I hope this crystallizes a little bit the importance of this. And if it's one thing you take away, is please see how these tools can help you do better science, do better language development. And I did want to hand it over to Tim for a little bit of a different take on the same subject as a final note on this.
Yeah, so I have also enthusiastically braced these tools and used them heavily in my own work. That said, I am a university professor. I view the fundamental role of the university is to train the next generation, and that is the one thing that universities may never let go of, right? And so I view that as a more important mission than getting things done. At the same time, my lab runs on taxpayer funding, right? And we owe it to the taxpayers to deliver exciting new findings for them. So we see this conflict, even aside from our own dreams and desires, just in terms of what our mission is, I think, on a daily basis in the university system. And one of the things that I want to say is, I don't know fully how to solve this, but I firmly believe that we can do both, right? So one of the things, I've had 3 new people join my lab this year. I've told all 3 of them, I don't know where this is going. As of this moment today, I still value the fact that I know how to read and write code. And I want to make you an offer. And the offer is entirely yours to accept or turn down. And the offer is, if you would also like to learn how to read and write code in the progress of doing your own science, I will grant you that grace, right? And I will say, my advice to you then is to use the AI tools only to improve your understanding. Have them quiz you, have them explain things to you, but do not let them write one single line of code for you. And the idea, the bargain basically is you do that for a year or so until you gain at least some basic fluency in these things. And then towards the end of your PhD, when you've been learning lots of things, including coding, and are ready to reach that productivity peak that occurs to many aspiring and ambitious young graduate students towards the end of your PhD, transition to leveraging these tools, crank out an enormous amount of new exciting discoveries, and then you'll also be prepared to compete in this world in which people are using AI tools. And to my great joy, all 3 of these young trainees have elected to take that path, or they want to take the hard road and invest in themselves, learning these skills on their own, and then you start deploying some of these AI tools from a more experienced standpoint. So I don't know what the answer looks like in anybody else's group but mine, but I do think there is room for both of these things. And I, for one, am not that afraid of where things are going.
Yeah, I love that. It sounds like a great approach to me. I think that sounds great. But, well, on a lighter note, Andy Deans and Claude made a great Julia ecosystem stats dashboard. If you use that QR code, it should take you there. There's a lot of fun stuff to browse through there. I won't be able to read through all of it. There's a lot. Yeah, it's got some of these fun so-called paper plate awards. We've got like Rookie of the Year. We've got the freshman class, people who put their first contribution this year. Well, let me just highlight a few things in here. So this is a list of open issues and PRs. So something interesting happened this year, which is it's been trending basically up, except for a few blips, for a really long time. And over the past year, we had the first kind of extended period of the issue and PR count going down, which is kind of nice. So the issue file rate has actually gone down a bit, which could either mean the quality's getting better or we have fewer users. I'm not sure. But the closing rate is also going up, so that's good. Oh.
You mean light mode?
Yes. Light mode? Okay.
How do I do that? Does anybody know? Oh, God. Okay.
Ask Claude.
Claude would know, I'm sure. Appearance? Okay. Light mode.
There you go.
Okay, great.
We don't need Claude. Unless it's for writing code, then.
All right, so yeah, number of issues and PRs trending down for the first time ever. Yeah, close rate is up. Another interesting one is if you look at new packages registered per month and package versions released per month, they both just ticked up very sharply. So I have a guess as to why that might be, given what we've been talking about up here. And then there's lots and lots of stats. I'm not going to go through all of it. But yeah, we've got some trophy case, most upvoted PRs, closed the most issues. And there's lots and lots of awards. Yeah, fastest merged PR, a revert by Christopher. Merged 32 seconds after opening it.
Excellent.
The most reacted to PR was Keno's strict mode mechanism, 25.
Which did not get merged.
Didn't get merged, but had the greatest reception. This one is great. The Shipped It Anyway award goes to Andy Deans, the author of this dashboard, who PR was merged despite having a record 2 downvotes. We don't get that many downvotes. It's a pretty positive community. Downvotes are rare, so 2 is like a lot. So there's a lot of these you can look through. It's pretty fun, and I really want to highlight and give a shout out to all of the 90, which I think is a pretty healthy number. It's pretty good. 90 people who made their first contribution to Julia in the past year. There they are. And with that, I just want to give some acknowledgments because several people contributed to content and slides in this talk. So here they are. Thank you to all of them. We usually crowdsource this to some extent. So yeah, thanks to everyone who helped, and thanks to all contributors, issue filers, and Julia users. Thank you for another year of Julia.
Yes. I want to point out, I got a note to refresh the slides after the talk had already started because somebody had made some edits. So as is tradition, these slides were edited until past the very last second. So thank you again to everybody who helped. This is, as usual, a group effort. And I think with that, we'll do Q&A?
Yep.
All right, Q&A. Please ask easy questions. It is very warm. My brain's running at 50% capacity.
We don't need anyone to turn on the grill.
Yeah, no grilling.
Hi, so the syntax versioning looks pretty cool, but my question is, what effect does that have on the continued maintenance burden as you add more syntax versions, like in future, like 10 versions down the line when you have
Yeah, definitely a good question. I mean, as I mentioned, we sort of want people to upgrade their packages. It obviously gives us the option to make breaking changes that remove syntax versions. So, if we ever release Julia 2.0, one easy way to do that would be to say, okay, as of Julia 2.0, syntax versions older than 1.13 are no longer supported. But in general, these syntax features are not that big a maintenance burden. They're usually just a couple lines in the parser, a couple lines in lowering. So that's usually okay. So I'm not super worried about it yet. But if you ask that question in 10 years, maybe we start talking about doing a breaking change just for the purpose of removing.
Ask M.
Yes. But yes, good question.
For the cancellation work,
yes,
can we also cancel the compiler? Because that's where I usually crash the entire thing when I try and Control C.
Not as of right now. In the future, maybe. So the system is set up to do that. That was one of the design goals. We ended up changing the API to this cancellation source mechanism. So there's not really the notion of canceling a task anymore, which is sort of where, whether the current task is canceled, that was sort of where the compiler cancellation had hooked in. But in general, it's a goal. It might, however, be solved by moving compilation to a separate thread with some sort of tiered compilation mechanism so that compilation just doesn't block the task anymore. And then you also don't need to cancel it. But yes.
Somewhat relatedly, how far upstream have you pushed cancel checks? Like, are they in OpenBLOS or GMP or these other libraries?
Yes. We added cancellation support to OpenBLOS upstream as a supported feature. For GMP, to give a little bit more color, we have 2 mechanisms for canceling calls to external C libraries. If your external C library is doing pure computation, we can just jump out of it and completely ignore all of those stack frames because they're not holding any locks, they're not doing anything that would be unsafe to jump out of. So GMP is almost one of those, except for some allocation cases.
So we are carrying some small patches to GMP in addition to the other patches we're already carrying to make that safe. OpenBlast is different. OpenBlast is internally multi-threaded, so it needs cooperative cancellation. So we added a cancellation API to OpenBlast, and when you request the cancellation of a matrix multiply, that'll dispatch to the OpenBlast cancellation handler, run all of OpenBlast's cancellation mechanism, which is also internally cooperatively canceled, and then it'll return, and then it'll run the Julia cancellation machinery. So the answer is yes, it's been pushed upstream into OpenBlast and GMP and libuv.
Does the change to AI change our thinking and our discussion and prioritization of interfaces, right? Because AI really loves things around being able to get good and early error messages inside of its agentic loops. And I get this feeling that's just like, oh, maybe that means that we should be doing some more static things within the language to be able to force the more things into compiler errors or force more errors to come early. I wonder what the thinking of the core team is around this topic.
Yeah, I have thoughts, but Jeff, do you want to chime in, or?
That may be true. I'm not sure we should make changes like that to the language for that reason. I think if we like those changes anyway, we can do them. But I'm not sure that's a great reason to make those changes. Also, AI seem to be pretty good at reading and writing Julia already, so I'm not sure there's a big problem to solve there. But I think those kinds of features should just be discussed on their own merits.
Yeah, I'll give my opinion. So I think as I showed on the slides, we've had very good success with using TLA+. And I think what that shows is that it's not so much about the particular mechanism as it is about grounding the AI models in a notion of correctness. So anything that we can do at the language level to specify what correctness looks like, and certainly interfaces could be one of those mechanisms. But something like state machine declarations that TLA+ is doing could be something in that direction. Something like more formal methods could be something in that direction. So to me, it's not entirely clear which ones of those are core language features and which one of those are tooling improvements that we just give to the AI and say, hey, if you make a change, this is what you can use to ground your correctness. But I definitely think it's something that we're going to have to keep thinking about. But also, again, we don't know what the capabilities of these systems will be in 6 months or a year. Maybe they'll just write it themselves if they need it, right? I think that's perfectly plausible. So, all right.
I know that you only show it on passing, but I saw this strict mode and it got me really, really excited because having very interested in having a strict mode for the last 3 years or so. So I'm wondering, what do you have in mind and how can I help?
For strict mode in particular?
Yes.
So the decision on strict mode was to defer it to a package. There's a few flags that are needed in base and in lowering to opt into any particular feature, but we didn't necessarily want to constrain how the interface to that looks. So the decision on strict mode was to provide an external package for opting into those, and it's on the to-do list to actually create that package, but we just haven't gotten to it yet.
Please keep in the loop. I'm very interested.
Yeah.
Any more questions? No? Then let's thank the speakers again.
All right. Thank you, everybody.
Thank you, everyone. Thank you for coming.
And now let's skip ahead and not wait for 7 minutes. I think we are all ready to get out of the sauna and out into hopefully slightly cooler air and maybe to a beer. Thank you all for coming to JuliaCon. Organizing has been a major project over the last year. It's been a lot of work, but it's also been a lot of fun. And it's been really great to see you all in person here in Mainz. Just a very... Yay, Linux. I love systems. Yes, this is the setup minutes, right? We have all the time. But now I don't see them, so that's problematic to me. This should work. No, yes, perhaps. It's Google Slide, it should work. Well. And this is how pre-compilation. And this is how pre-compilation feels like in the classroom. Okay, so this is the 13th JuliaCon. I think it's the 10th one since I started attending. We had 461 attendees. That's pretty close to a record. We've been debating whether or not it's the biggest not or yet, but you know, numbers from previous JuliaCons are hard to come by. We have attendees from 30 different countries. We had 19 mini-symposia, and a big thank you to all of the mini-symposia organizers. You've taken a lot of the groundwork off my shoulders. I could trust that something was happening. We had 280 sessions in essentially 3 days. And we had, I think, the biggest poster session yet, now with 90 posters yesterday. And I hope you all enjoyed the food. We have to thank our sponsors. Without them, this conference would not be possible. In particular, without them, we wouldn't be able to also stream and record all of the talks. And so thank you all for supporting JuliaCon for sometimes multiple years now. And also thank you to all of the local partners who've been making this event possible. I would also like to thank all of the volunteers who came out in droves to help us run a very smooth event, at least from my side, it feels like it. I would particularly thank Mariana and Brigitte. Both of them already went home, so we will give them an applause in absentia. How do I get back, Ray? So tomorrow we will have our traditional hackathon. It will start at the Alte Mensa, which is the building where the registration is, at 9 a.m. There will be no catering, so please eat breakfast beforehand. Do bring your own water and bring your coffee cup back. I will be making coffee for you all, or more or less I will help you all make coffee. And we have some lunch options available around the university, but as I said, no catering available, so that's all on your own. I suspect we will be done at 3, because afterwards it's going to get too hot and my brain will stop working. If you're interested what will make the hackathon, it's mostly an event where everybody can work together and you have a very short way to ask questions about why is enzyme broken again. If you want to create your own topic or you want to see what topics are available, there's a HackMD where we are collecting ideas. So, Avik, where are you? It is time for the fun part of the event. We have some community prizes to hand out.
Thank you. Valentin thanked a lot of people who made this event possible. But I do want to thank Valentin personally. He's been doing 14, 15-hour days for this last week and long days all year. So thank you, Valentin. It was also Valentin's birthday yesterday, and he worked. So everybody, please, 3, 2, 1. Happy birthday to you. Happy birthday, dear Valentin. Happy birthday to you. Now I would like to get Tim on the stage, please. Tim is one of our judges for the Community Prize, and he's been doing it for almost a decade.
Thank you very much. I'd also like to acknowledge my co-conspirators on the committee, Curtis and Alan. It's always a great honor to try to pick out of the enormous number of contributions that so many make a few that are noteworthy. And it's a very difficult task in many ways, but it's also a very pleasurable task because it's a time to reflect on the ways in which our community has grown over the past year. Our first winner is someone who got an absolute flood of nominations from the community. This is a person who has been the engine that has helped Turing.jl run over the past year, has reviewed, I believe, well over 100 and merged well over 100 in PRs, been incredibly responsive to user questions and comments and all this kind of stuff, and has recently turned her lens to Julia Formatter. If Penelope Young is in the audience, please come forward. Everybody congratulate her for her incredible work. Do we have a photo or anything? Ray, okay. You come on up, please, yeah. Oh, you are so welcome. Congratulations. Does Ray have a photo? Oh, very good, okay. Yeah. All right, thank you. All right. Oh, and Penelope, one more. Very good. If you'd like to make a speech. Do you want a speech? Go for it.
No, just to say thank you to the entire Julia community. It's been really wonderful.
Thank you, Penelope. Okay, our next award is also to, I think one of the most important engines that underlies the Julia ecosystem. In a sense, maybe you could say this is a belated thank you from us. The group of people, so how many of you have ever heard of this really unrecognizably obscure package called linearalgebra.jl? Anybody ever used that before? Yeah, almost every hand in the room goes up, right? So that doesn't just drop out of the sky for free. It used to live in base proper and then got moved out into a package, and there were just continuous, ongoing, over the entire time I've been involved in the Julia community, improvements to our infrastructure for linear algebra. Now, there have literally been many tens, I think well over 100 different people have contributed to that package, and I do want to thank everyone who has ever helped make that package better. That said, we are picking out 3 individuals whose contributions are especially noteworthy. One is Andreas Nowak. The second is Daniel Karash. And the third is Jishnu Bhattacharya. But please thank these three individuals and all of the other contributions. If any of them are here in the audience, please come forward. Thank you so much. Do you want to say anything?
Just very unexpected. It's been a while since I've been a regular contributor to linear algebra, but thank you very much.
We all are in your debt. Thank you. The other contributors will be receiving these in the mail. So, all right, back to you. Oh, Valentin, okay.
Thank you so much. And now, drumroll, please. JuliaCon 2027 will happen in Tallinn, Estonia. Tentative days, July 19th to 24th. The only promise I've made is that it will not happen during the eclipse again. And I was asked to include this slide as a preview on why we might be choosing this direction. Thank you all for coming to JuliaCon. Thank you all for being here. Without you, it would not be as fun. And yes, now I wish you a relaxing Friday evening. And for all of you who are coming to the hackathon, as I said, bring something to drink, water. We might be able to refill from the tap, but we will have limited services available. Thank you all. Yes, Katie? Maybe. Food arrangement are up to the attendees.